Okay, good morning again. So let's get seated. Welcome to ETH Seoul, the first ETH Seoul 2022. And good morning, everybody. Hello. So this is on live stream, so I should not mess this up. But my name is Erica from Crypto Seoul, and thank you so much for being in Seoul and in Korea for this whole experience. Biddle, ETH Seoul, and everything, and KBW, of course. But yeah.
Good morning. Has your morning actually been good? Okay, great. So since your morning is good, let's talk about building stuff. So things that, so this is just to kind of give a few different categories of ideas that I think are really worthwhile for people to start building and to start really concretely working on right now. And so in general, I think a lot of things have changed in the crypto space and in the Ethereum kind of development world in particular in the last 2 years. A lot of technologies that were really just thoughts and ideas and theories 2 years ago have slowly become very real over the last couple of years. And in a few places recently, I've talked about what some of those changes are, right? One is the fact that we have roll-ups, we have scaling, things are getting cheaper again. So a lot of applications are just much more economically viable than they were 1 or 2 years ago. And so when before you might even say, well, maybe DeFi is the only thing that makes sense to build because DeFi is the only thing where people are willing to pay $12 a transaction. Well, now transactions are cost much less than $12 and rollups are getting better every day. So there's a lot of other things that you can build as well, right? Another really big and really important thing that's been happening over the last 5 years is the growth of zero-knowledge technology, right? So I actually think that ZK snarks might be almost or even equally as important to the kind of privacy, openness, freedom, kind of alternative decentralized web tech movement as blockchains are. They're actually extremely powerful tools. They're extremely effective at giving us privacy, giving us scalability, and at the same time preserving security, which is a similar thing to what blockchains are trying to do, right? And in some ways, zero-knowledge proofs and blockchains are actually very good complements for each other, right? Because blockchains give you a lot of security, but in exchange, they sacrifice privacy and they sacrifice scalability. ZK snarks give you back privacy and they can give you back scalability. So build ZK apps, right? Basically, I think we've now gotten to the point where the tools for building a lot of ZK snark applications are just getting better and better every year. The protocols are getting better and better. Our ability to prove things, make proofs that you can actually prove on a computer in a reasonable amount of time is getting better and better. I remember in 2016 when the first version of Zcash launched, it took more than 1 minute to generate a signature. And today, all of these applications, they can generate proofs in sometimes 3 seconds, sometimes less than 1 second, depending on what technology you're using. So build zero-knowledge applications. Zero-knowledge applications are, I think, great for both privacy and scalability, right? So here, I have this link to a blog post. If you just go to vitalik.ca or vitalik.eth.link, either one, and you just scroll down the list. I wrote this post about 1 or 2 months ago, or just talk about some of the ways that you can use zero-knowledge proofs to actually build many kinds of applications that preserve privacy. And there's also a lot of applications of zero-knowledge proofs for scalability, right? So ZK rollups are a great example, and there's a bunch of teams building ZK rollups for the EVM, which I think is great. Privacy, I think, is still a bit less explored than scalability, actually. So just like some interesting examples of privacy-preserving applications that might make sense to work on. Privacy-preserving, like proof of humanity, or privacy-preserving proof of Pope. Like basically, like in Ethereum, we're starting to have like more and more of these protocols where they're basically issuing like some kind of attestation to at different like specific addresses to say something about the person who controls that address, right? So the proof of humanity protocol, for example, it's a protocol where if you have to sign up and there's like a DAO that verifies submissions, and if it accepts you, then it basically says like this address corresponds to some unique human, right? So it's not a bot, it's not like one person having 5,000 accounts, it's like one specific person that has one account. And if you have proof of humanity as an ingredient, then like you can start building a lot more powerful applications. You have like a lot more room to decide like what kinds of things you'll be building, right? So for example, you could build an airdrop where instead of like doing an airdrop just based on how many coins does someone have, how many transactions has someone sent, you can like say, I'm going to actually give like 15 coins to every single human, right? You could do like even NFT sales in a way that's more fair. You can do a sale, just create market mechanisms that try to be like more fair to individual people in some way. I'll talk about this later, but like there's also ways to make decentralized governance more fair if you try to like count humans instead of just counting coins. And privacy preserving proof of Pope. So Pope, the proof of attendance protocol, is a protocol that like basically lets you say this address belongs to someone who actually participated at some event, right? So like I went to a conference in Argentina last year and I got a Pope for it, right? So there is a Pope that got given out to everyone who visited this conference in Argentina. And so you don't just know that this person is a human, but you actually know like what kind of communities they're part of and like what a different, how much have they participated in different kinds of communities, right? So you get more of this kind of information. Now, one of the big challenges with both of these protocols is privacy, right? Like you're basically revealing to anyone who can read the blockchain like who you are. And this is a big privacy risk. But at the same time, like I think there's a lot of really important things that we can gain from having these protocols. And so the challenge is like, how do we get the benefits without the costs, right? And zero-knowledge proofs could actually help a lot here, right? Like with zero-knowledge proofs, you could do something like prove that you are a unique human without revealing which human you are. You could prove that you have a Pope and that you attended like 5 events from a particular list without revealing like which events you specifically attended and without revealing like what your actual identity is. So a lot of interesting applications there. ZK negative reputation. So this is actually one of the sort of more advanced examples in this post that I wrote. Basically, the idea is to have a reputation system where you can make attestations that are not just positive but also negative. So you'll be able to prove things like, I participated in some decentralized social media platform and I made these posts that got upvoted, but I also did not get downvoted, or like I also did not get flagged for abuse. So you can do like all of these things, but at the same time also preserve people's privacy, right? Zero knowledge and NPC data marketplaces. This is interesting. Like I think a lot of people have been interested in this idea of like creating like more fair marketplaces for data. And yeah, there's applications of this in healthcare, there's applications of this in like a lot of different spaces, but there the problem is that like it's not just a blockchain problem, right? Because you are trying to solve a trust problem, but the trust problem you're trying to solve is not just the kind of trust problem that a blockchain solves. You're also trying to solve a problem of privacy, right? A problem of like, I want to give a little thing about, a little piece of data about myself, but I don't want to give more data than that. I mean, ideally, like you want to even give data that contributes to, like, say, someone's machine learning model without actually like giving them the data directly, right? And if you want to do those kinds of things, then you need a different kind of cryptography called multi-party computation. So combine zero-knowledge proofs and multi-party computation, try to create better data marketplaces. I mean, this is a very advanced topic, but I think like this is the frontier, and there's a lot of exciting things that you can build here. So those are just a few examples of things that you can build with zero-knowledge stuff. I think building with zero-knowledge tech is still advanced, but it's getting less and less advanced, and the tools are becoming more accessible with every year. So I still encourage people to really look at the tech and really consider, like even now, using it to build something. Soulbound tokens. So this is something that a couple of articles, one that I published myself and a more recent paper that I co-authored about a month ago. Like basically the idea is of using tokens that are non-transferable, right? So the basic idea here is that like you want to have tokens that represent, like say, that you actually are a member of some community, that you actually like learn, like prove that you know something, that you have some experience, you proved that you completed some challenge. Like, you want to like prove different things about yourself, but you want to prove that like actually you were the one who did those things, and you did not just like buy a token from someone else for $50. So basically making tokens that are like non-transferable. So Pope is actually a good example of this, right? Now, Pope tokens, like they are transferable in that like they are ERC 721s, and you can send them to someone else if you want to. But like you can look on the blockchain and see, right? Like, has this Pope actually been transferred? And if you like, you can treat popes that are still in their original address and popes that have been transferred differently, right? And I'm basically expecting that these kinds of things are going to become used for a lot more different kinds of projects. And I think there are a lot of applications of this, right? So one that I mentioned is what we call soul drops. So like basically airdrops where in order to qualify for the airdrop, like you try to use some of this like on-chain information to actually figure out like who is in the community that you want to airdrop to, right? Like a lot of different projects they want to airdrop, but one of the challenges that they always face is like, if you airdrop, then sometimes the airdrop just gets farmed by VCs, right? And VCs just create 100,000 accounts. Sometimes the airdrop, just give it to random people, and someone creates like a really efficient app where everyone can just like go and dump their airdrop on Uniswap for $32, and everyone does that, and like you've just lost a lot of money. So what you want to do is like I think you want to distribute your token supply. You don't want to have this kind of plutocratic dystopia where like 7 people and VC funds control half the supply. But you also want to like actually give the supply out to people who are actually in your community, right? And so how do you tell like in a very verifiable kind of automatic way that it gives you like some of what we call credible neutrality, some ability to like actually prove to the public that you were fair in how you allocated it, and that you're not like quietly giving lots of coins to yourself. Soulbound tokens might actually be a very powerful tool for doing this, right? So proof of humanity, you can like limit to individual people. You could even like, do interesting things with proof of humanity, like you could make a sort of fair ICO where if you want to, let's say, sell you could buy your first token for $1, but then buying your second token costs $2, buying your third token costs $3. And so the more tokens you buy, the higher the price of each one goes, right? So there's like different ways to try to create these mechanisms to sort of make them, less plutocratic and more fair. And things like proof of humanity could be a big part of it. Proof of attendance protocol can be good, and kind of similar ideas can be good for not just checking like who is a human, but also checking like who is actually a member of a particular community. And I think there's a lot of like good ideas here, but there is a lot of room still to actually build the infrastructure to make it really easy to do these kinds of things. So I think this is like another challenge for developers, like try to actually build more of these tools. Another interesting one is this concept of like soulbound token gated community forums, right? So like imagine a private chat where basically things that are said in the chat, they don't get automatically broadcasted to everyone, but they, it isn't like just a couple of people who decide who gets in and who gets kicked out. Instead, like say you have a DAO, and that DAO issues tokens, and even like based on some measurement of whether or not you're in a particular community, that determines whether or not you can get in. So this, obviously, like soulbound tokens and zero knowledge, I think like they're not separate, and there are really important synergies between them. And the reason why there are really important synergies, I think, is obvious, right? Because like there's a lot of really cool things that you can do just by having the ability to like know more things about the people behind the addresses that you're interacting with, and being able to say like, this person is from this community, this person is not, this person is a core developer of this project, and this person has one Ethereum address, but actually he's mostly involved in some completely separate project, in like being able to distinguish those things. But the more you gain that ability, the more you're like breaking people's privacy, right? And zero knowledge is a great way to get some of that privacy back. So a lot of interesting ideas here. Better public goods funding. This is something that I think we've been talking about for the last 2 years, right? Basically that like blockchain communities need ways to fund public goods. Public goods are important for everyone, but they're especially important in blockchain communities because blockchain communities are internet communities. They depend heavily on open source software, public documentation that gets written on the internet, people making translations, just all kinds of work that's completely done in the open, and it's extremely valuable, but there's not a good way to charge for it, right? So better ways of like funding it and of like actually using community pools of funds to support those things, and even to support public goods that go beyond the blockchain space, is something that I think is like really important to care about, right? Now, how can we do this? So quadratic funding is interesting. So the Gitcoin team has been doing these experiments for the last 2 years, these quadratic funding rounds. And at the beginning, it was like this thing where you had like a $25,000 matching pool, and basically nobody cared about it. But I think over time, we've seen it like really grow and balloon, and now it's this big, $5 million thing, and you have just these really big matching pools that happen every couple of months, which I think is amazing. But there is still like opportunities to improve quadratic funding and to try to make the mechanism better, make it more safe against attacks, make it more privacy preserving, and all of these things. So this is one part of the public goods problem. Another way to look at the public goods problem is to look at it from the perspective of like credit assignment, right? So let's say that someone invents some amazing new zero knowledge proof protocol. And this new zero knowledge proof protocol is like makes it, let's say, 10 times cheaper to scale Ethereum rollups and improve privacy, and it has some other magic amazing properties, right? Now, this is a public good. It's something that once you do it, it's in the open, it gets published, it benefits everyone. It doesn't even just benefit the Ethereum community. It benefits every crypto community, it could even benefit like lots of mainstream, industrial applications, lots of government applications. It can make civil society more applications more secure. So it's a very public good. But one of the ways of like asking what the problem is to look at it from the problem of like, well, who should get credit, right? And the answer almost never is one person, right? Because like it's easy to kind of tell who is like the last mile person who's responsible, right? Like who is the guy who actually publishes the thing. But the person who publishes the thing, like he did not invent, or she did not invent the idea in a cave, right? Like they read existing work, synthesized existing work, talked to people, created one version of an idea, found someone who broke that version of an idea, fixed it, created a better version of the idea. There's always this collaborative process, and each of the ideas that they built on are also ideas that themselves, built on other ideas, and like there's this big tree of like where the credit comes from. So one thing to think about is like people I think have for a long time been thinking about like the kind of the provenance problem, right? So this is like blockchain supply chain applications. Like people talked a lot about this in 2015 to 2017, right? Like basically, if you have like if you get some product, how do you tell like which country the different parts actually came from? How do you tell like what's trustworthy? Can you like put cryptographic links at every step in the supply chain, check them on chain and all of that? Like we could do that for public goods as well, right? We could try to like take the concept of citations and formalize it, make them cryptographic, make them more incentive compatible, have a kind of more this kind of richer information about them, and just like have more information out there that could actually be used to properly compensate sort of everyone all along the chain of like actually producing some public good. NFTs for public goods. So like NFTs have always been this sort of challenging topic for me because on the one hand, like I think NFTs could be like a really amazing fundraising tool, and they could really help in like raising money for things that really need it and things that don't otherwise have business models, right? And they kind of already do. There's like a lot of artists that are around the world, and even people in places like Southeast Asia and Africa and Latin America that like really do get included and find a way of like making revenue through the NFT ecosystem. But on the other end, like NFTs can sometimes become this sort of ridiculous thing where people are trading $3 million monkeys, right? So like to me, like I guess my ideal world is like not to like I don't want to hate NFTs, and I also don't want to uncritically like NFTs, but so like I want to build better NFTs, right? And it would be nice if we can like try to find a way to kind of get and make NFTs benefit public goods more, right? So if you produce some public good and then like find a way to kind of sell some NFT for it, and the public good, like, it could be some scientific result, it could be a work of art, it could be a blog post, it could be an idea. Basically, find ways to kind of create an NFT ecosystem that people want to participate in, and where at the same time, like you actually ensure that the people who get the funding aren't just kind of like very flashy and famous people at the end of the chain, but try to actually make sure that sort of the entire, intellectual supply chain gets compensated well. So a lot of like, I think, interesting ideas to work on there. Better DAO governance. So I think, DAOs are great and lots of people are doing DAOs, but at the same time, like DAOs have a lot of problems in governance. Like their governance is, in general, I think it's like either centralized or attackable. And like we see a lot, sometimes some pretty scary attacks, right? Like I think very recently there was like a stable coin that got drained because someone bought up 51% of the supply of the tokens and made a governance operation to drain all the money, and did that in like a flash loan in a single transaction. And these kinds of things, like they happen because coin-driven governance is like fundamentally broken, right? And I've written about this many times, so this is like, another post where I talk about this. And there are ways that you can improve it on the margin, but I think ultimately you need to have governance that is not coin-driven. So this is also where things like soul-bound tokens, things like proof of humanity, things like proof of community membership come in. Like, we need to have governance that depends on things other than just token ownership. And we need to even get away from this idea that the purpose of a DAO is like fulfilling the will of the token holders, right? There are other stakeholders that matter too. So one of the directions to go is kind of non-coin driven governance platforms. And I've talked about ideas for how to do this in a couple of places, but there's also the problem of actually building DAO governance tools that use those ideas, right? Today everyone forks Compound because there's just lots of really good tools that are make DAOs easy to operate if you assume that your DAO is a coin voting DAO and it forks Compound. There aren't good tools if you want to build a DAO some other way. If you want to build a DAO some other way, you have to do things yourself, right? And it's in the last century, we had nobody gets fired for buying IBM, and here it's nobody gets fired for forking Compound, right? But I think more people should get fired for forking Compound, and more people should get rewarded for actually trying something different. So we have to actually build those tools and make it easier. Direction 2 is better communication platforms, right? Governance isn't just about voting. Voting is the last step in governance. The steps that comes before is how do you actually create ideas, come to consensus on ideas, even improve ideas over time, and get feedback even before the final vote happens, so that you actually can better find an idea that makes, say, 90% of the community happy instead of just making 51% of the community happy. So better communication platforms, there definitely are projects that are trying to kind of do this decentralized governance communication thing. So Radical Exchange people, they talk a lot about Polis, right? It's this platform for kind of finding ideas that different subcommunities can agree on. And Audrey Tong from Taiwan really likes it, and it gets used a lot there. So that's one good example. But you can look at that, but I think there's also room for a lot more experiments here. But in general, I think DAOs need better governance, DAOs need better communication. So lots of things to do here. So those are just a few ideas. I mean, there's plenty more ideas that you can try, but I think there's a lot of really interesting directions to work on. There's a lot of very exciting potential in the space that exists now that did not exist 2 years ago, but there's also still a lot of stuff that needs to be worked on. And I hope that people here can be a part of the solution.
Wow, such an inspiration. Thanks, Vitalik. Thank you so much. If you're watching this stream, if your sound is too small, sorry about that, but we're trying our best to make it a nice environment for everybody. 너무 감사드리고 잘 들으셨는지 모르겠어요. 소리가 조금 너무 작으면 말씀해 주시면 저희가 좀 조정하도록 하겠습니다. 자, 다음 presentation, next presentation. All right, Alex is coming up on the stage and he'll be setting up really quickly. So let's give a round of applause for Alex.
Hey, everybody. I think I'm on the, okay, cool. Make sure I'm in the camera there. Good morning. It's really nice to be here today. I'm very proud and humbled to be at this event and share a little bit about the project that I'm working on called Aleo with you. So the quick TLDR is Aleo is a platform for private applications. We're going to talk about what that means throughout the course of this talk, and I'm the COO. But the first thing is we're going to see if the slides will move forward. And they may not be, so. Okay, so that was the first thing. The second thing is we have to address something right up front because ZK EVMs, all the rage recently, lots of exciting announcements, And understandably so, there's this question of like, can we use zero-knowledge cryptography, which, by the way, I should have mentioned that Aleo is a project that's leveraging zero-knowledge cryptography quite heavily. So can you leverage zero-knowledge cryptography to build a, build a better EVM effectively? So is Aleo a ZK EVM? No, it's not a ZK EVM. But what is a ZK EVM? At first, I thought I knew what that meant, but actually Vitalik, his recent blog post, he was just up here, but his recent blog post, it inspired me to change these slides a little bit because I learned from that blog post that the definition of a ZK EVM is a little bit broad, right? So it could mean a lot of different things, right? So this chart is not from Vitalik's blog post, it's from another great post that I've linked below. But you can see there's like the definition on the far right side of what the EVM or what Ethereum, the computing model of Ethereum kind of looks like. And you kind of have all these increasingly distant, different projects that have implemented what people term as ZK EVMs in kind of different ways and increasingly distant in terms of compatibility. Although I would say, in addition to you have the arrow on the bottom that goes to compatibility, I would also put an arrow that ran the other way about performance, right? And so the TLDR is, at least today, so as far as we know, the closer you try and get to a ZK EVM model that emulates exactly the Ethereum model, you pay a quite heavy penalty in performance. So that's why we at Aleo decided to build a new model from the ground up with this exact use case in mind, a ZK VM. And so the way our model works, and I'm going to go through all of this in detail in this talk, so don't worry, is we have a high-level language called Leo, which compiles down to an intermediate representation called AVM instructions, which get turned into AVM opcodes, which then get synthesized into what's called R1CS, which is effectively the stuff that proofs are made of. And okay, so why is this even a hard problem? Why are we sacrificing, why can't we just replicate the EVM exactly? And by the way, I'm going to liberally steal many other people's great insights throughout this presentation, but I will cite them. And this is actually a quote from an article written by a gentleman named Gautam Botral, who works at Consensus. And the TLDR is that the thing that the EVM reasons over are 256-bit words, and the operations there are bitwise arithmetic and Boolean operations. Proofs, what is a zero-knowledge proof? Well, it's a field element, or it's some group element of a field, which is typically a cryptographic field like this elliptic curve that I've shown there. And what is a program in that model? Well, it's a circuit on the bottom, encoded as a polynomial, defined over this field, right? So these are two very, very different things. And typically when you try and translate that into the world of a regular computer program, as Gautam points out, typically the blow-up is quite large. In fact, there is actually already some research that shows you can build effectively a CPU inside of a zero-knowledge proof. It's called TinyRAM. I highly encourage everyone to look it up. And basically, roughly speaking, the blow-up factor of any program is 10,000x in terms of the number of constraints, as opposed to if you just implement the program step by step. Okay, so this is kind of another way to say it. So this is the challenge here fundamentally, is like you have an idea for a program, you want to write it in some high-level language. It's like I want to prove that I know the sum of two numbers, kind of a silly program, but let's just go with it. And so you write it out in high-level language, and then what Leo and the AVM does is compiles it down, and it manages this problem of basically efficiently translating between the world of zero-knowledge cryptography, or the cryptographic world where things are all group elements defined over elliptic curves, and the world in which the program actually needs to be evaluated, what's actually being computed here. And to do that efficiently is why, again, we built our stack from the ground up. And this is why it's very difficult to do this from this is why there's all these different flavors of ZK EVMs. So again, this is kind of another model of how Aleo works, and we'll go through this in a little more detail. But the point I want to make quickly is, so today we have Leo that compiles to AVM, and then we have SnarkOS, which is basically our layer one, where we have validators that also serve as verifiers that can verify transactions were computed correctly. And the point that I want to make here is that, okay, so we have Leo that targets the AVM, but maybe in the future we could have other languages that target the AVM too, or even potentially a transpiler that targets Leo or the AVM directly. So there could be a world in which you could write Rust or Solidity or some other language, and maybe through some transpiler architecture you can just basically end up still being able to do all this. And so this is an interesting future direction. Very similar to, actually I'm going to go back, very similar to, I guess if you go back to the definition of the EVM, on the far left, this is what Aleo could potentially someday look like. But okay, so now back to the question, is Aleo a ZK EVM? Maybe, although I still would say not really, right? And the point is, it's like, okay, what's the whole point of a ZK EVM? What do we care about here? Why is the EVM important, right? The EVM is important because we want to be able to compute, we want general programmability on chain, right? And so what I define Aleo as is a platform that uses a ZK VM. Like again, the E part here I think is extraneous because what we ultimately care about is computing programs on chain using zero knowledge. So now I'm going to tell you a little bit about Aleo after this quick kind of digression. And the first thing I want to acknowledge is that Aleo is not an Ethereum killer, it's not a Bitcoin killer, it's not a Solana killer, it's not anything killer. Aleo represents a step along a path that had many prior steps before, and I think it doesn't get acknowledged often enough, especially in the modern world of crypto conferences, that for like 40 years there were all these failed projects that tried to build digital money and failed, but ultimately inspired Bitcoin, right? And Bitcoin, the key insight of Bitcoin was actually not cryptographic at all, it was cryptoeconomic, right? This concept that you could have miners, if you build an incentive structure a certain way, it aligns the incentives of the participants of the network and the miners and everyone, and then the whole system works trustlessly and permissionlessly. And so Bitcoin, that insight kind of inspired a lot of different directions from that same kind of turning point. And Ethereum, similarly, the insight that Vitalik and others had was, okay, well, we have Bitcoin and it's really cool, but it's not as powerful as it could be. Imagine if we took a computer and we put the computer on chain. And again, so we had that, if we go back to 2015 and 2016, 2017, you see all these different projects that take that idea and run with it, right? And so this is kind of its own direction, this on-chain VM model. And Aleo implements a model which is based on some research that was authored in 2018 called ZEXI. And the idea of this was to try and combine some of these past approaches and accept some trade-offs, but to be able to have an off-chain computing, basically where you compute program transitions off-chain and then verify them on-chain. So we view this as a step in a different direction that gives you some kind of cool new powers. So we're going to talk about that through the rest of this talk. And maybe I'll just highlight to me the two best parts of this potentially is that, again, as we all know, on Ethereum you need gas. And why do you need gas? To make sure that no one can force the EVM into an infinite loop, right? So gas is there to make sure that effectively no one can DOS the system. And that's because every node is executing every single transaction to verify that it's correct. Now, in the world of zero-knowledge cryptography, as Vitalik pointed out in the last talk, is the beauty of this is you can cryptographically prove a statement without revealing why it's true. And if you accept that proof, well, the only honest verifiers will always accept that proof as valid. So therefore, you don't need to re-execute the entire instruction or the entire program. So that's really cool. So it's more efficient in that way. And also, in the additional thing, and we're going to talk more about this later because I think this is really an underrated insight, is that you have unlimited program runtime. So actually, a quick pop quiz. I don't know if anyone knows this, but does anyone know the stack size for the EVM offhand? Okay, so it's 1024. So the stack size of Ethereum is 1024 elements, right? So theoretically, you can write a smart contract that would overflow the stack size on Ethereum. So there's a limit, effectively, and I don't think for most programs it's of any practical importance, but the important thing to note is there's a limit into what you can do here. So in the Aleo model or in the ZK VM model, you don't have this limit because you're running a computation entirely off-chain. So you could, I don't know why you would ever do this, but you could do a protein folding algorithm for years, and at the end, you can come up with the result and then present that as a proof, and then that proof would be as valid as any proof. You don't need to do it within the window of a block. Cool, and then I have this kind of chart here which shows how I view Aleo as kind of a mishmash of something what Ethereum's trying to do and Zcash. Architecturally, and we'll go through this in the next slide, architecturally I think the way to think of it is a little bit closer to Zcash. In fact, I'll just jump ahead. It's a bit of an extension of Zcash, where if you think in the Zcash model, you have records, and these records basically are the fundamental unit of data on chain, and then the way state updates happen is people prove they have ownership of a record, that the record exists in one of these specific data structures, and that they have the key that allows them to spend the record, and then you can basically use that to create a system of payments, right? So there's a transfer. This is exactly how Tornado Cash on Ethereum works as well, by the way. And ZEXI, the model, is that exact same thing, except instead of just payments, there's this additional parameter that a record has, which is what program ID. And this opens up the door to being able to define basically user-defined, or you can have user-defined predicates or developer-defined predicates. So instead of just I pay you, you pay me, we can have more complex logic in there and have the proof represent that. So just quickly here, how this works is you do a one-time setup of the system in the beginning. You generate all the parameters you need to prove and verify, and then you have a prover, and we'll talk about the different parties in the system in more detail over the following slides. You have a prover, basically takes some public state, some private state, a user signature, generates a proof, and then submits that proof to the chain, and you have a separate party, which are the validators or the verifiers on chain. They verify it once, and then update state as a result. One thing to quickly note, which I'll mention a couple more times in this talk, is that the prover can be you, or it can be someone else. So it's a bit flexible, and depending on what trade-offs you want to accept. Do you want to share information about what you're doing with a third party, or would you prefer to keep that private but potentially do it in a slightly less efficient way? Okay, so this is maybe just a little bit fancier way to visualize that. So once again, we have developers in our system, and the point, just like in Ethereum, you have developers deploy smart contracts. In our model, you have developers that deploy programs to an on-chain program registry. So we have our on-chain registry, developers deploy a program, and that program is the compiled AVM bytecode that corresponds to the logic that they wrote. And now provers can, once they receive a transaction, a request from a user, or again, you could be the prover yourself, you take that AVM bytecode, you take the initial parameters generated during the setup, you synthesize all the information you need to generate a proof, you generate the proof, that gets wrapped into a transaction, and then that gets submitted on-chain. And then state updates occur. Okay, so actually, it's kind of similar to the way that rollups work. I think a lot about this. I think there's this concept now of modular blockchains that a lot of people have talked about. And in a rollup, it's kind of the same idea, right? You're separating the execution from the settlement, effectively. And so this is exactly what we do in Aleo natively. So in Ethereum, you have developers or users, and they're submitting intents to rollups, basically, signed, hey, I want to transfer from A to B. And then, yeah, I'm stealing some of Adrian's lines, so sorry about that. So anyway, the rollups execute these intents, and then the validators, the layer 1 validators, verifies that these intents were executed correctly. And this is the exact same model that we follow, although, again, it's a different architecture, built from the ground up to be slightly more efficient. Okay, so I kind of went through all this. I guess maybe instead of going through this all again, let me just say one thing quickly about what makes the architecture different than something like Ethereum or many other chains. Is that I mentioned a minute ago, when you deploy a program, you deploy to a program registry. So what that means is there's effectively a namespace that exists on chain that's tracked by all the validators, because this is exactly how you know what program you're interacting with. Because if I just give you a proof, you don't know what program it is, it's impossible to reason about a state update. So this is kind of an interesting thing and opens up a lot of doors to potential applications. So you could have a namespace and put anything inside the program ID. So this is in addition to being useful for programs, could also be useful for identity applications or other things. Yep, okay, and so we have this concept of callers and provers, where if the caller calls a prover to execute some function, again, in the real world, like these are computer science concepts of just we're separating these two agents, but in practice, you could be both the caller and the prover. You could synthesize, there's no reason why you couldn't synthesize your own proof yourself. And that's, I think, very important, because I think one of the, it implies decentralization, but I think decentralization is a very worn out word in the space, but I think more importantly, it implies permissionlessness, right? So that you don't need to ask permission for anybody to deploy a proof, which means there's a lot more opportunities to potentially compose and combine things. Okay, and then we talked about validators and they verify proofs. I think that's probably enough to say about all that. Okay, so this is what it looks like in summary. So let me just restate it all again from the beginning. So Aleo is building a new layer 1 blockchain using a proof of stake architecture based on a variant of hot stuff, which for any of you are familiar with that consensus algorithm. And it uses a computing model based on Zexy, which is a ZKVM. And in that model, it's defined by off-chain computation featuring unlimited runtime, where transactions are proofs, and these proofs are then submitted on-chain. Validators verify these proofs are correct, never have to re-execute them again, and then effect state updates, all in a way that preserves perfect privacy. So this is called decentralized private computation. This is the term from the 2018 Zexy paper, which talked about this primitive. And I think this is extremely exciting, because for the first time you have this permissionless system where you can deploy programs and interact according to the logic of those programs privately on-chain. And so we're really excited about this potential paradigm. Okay, so I'm going to go through I guess in more detail. I've talked a little bit about a lot of these points, but why does this matter? Who cares? What's good about this? Okay, so the first is, I think, at this point, we've all been to enough Ethereum meetups that we know that scalability can be challenging on Ethereum. And one of the reasons why scalability is challenging is that every single node has to re-execute every single transaction, right? And this is why rollups are oftentimes looked at as a really promising architecture, because it separates these two things, right? So when you separate execution from, from settlement, you get greater scalability and efficiency. So yeah, this is basically, I guess, maybe a picture that communicates that. You guys check the slide real quick. Oh, okay, there we go. Let me go back. Okay, cool. One thing I just wanted to take, and I know there's a typo on this slide, I apologize. One thing I wanted to just take a digression and talk about is Aleo is a proof of stake blockchain, and I was talking about efficiency a second ago. I already talked enough about how when you're a prover, you execute a transaction, it only needs to be verified once as opposed to forever and for all time by every node. One of the things that we have implemented, which I think we're the first team to implement, are frost signatures for our consensus algorithm, and this is what validators use in the process of consensus to sign basically that or validate blocks. But users or developers can also take advantage of this paradigm, and frost is basically a threshold signature scheme using Schnorr signatures, which recently got integrated or is being integrated into Bitcoin. So for those who aren't familiar, Schnorr is a really nice, efficient signature scheme. If you saw my prior talk on Thursday, you'll know that Schnorr is actually a zero-knowledge protocol called a Sigma protocol. And, but anyway, the point here being that it's much more efficient to aggregate several signatures together and cheaper, and so this is a way in which you can do things like multi-sigs in a way that's much cheaper in terms of constraints than you could do in potentially other systems. Okay, the other thing that I'm excited about, we could do a whole presentation on all the really interesting directions that zero-knowledge cryptography as a whole is developing, and kind of the ways in which this is getting better and better and better every single year, thanks to the contributions of many people, including some of whom are in this room. But we use a proof system called Marlin, which I probably should have mentioned a minute ago. Marlin is a universal zero-knowledge proof system, which means that any logic that you can think of, you can prove up to a certain size. So this is a relatively recent phenomenon, I guess since the post-2019. And originally Marlin did not integrate any kind of lookup table, which is a feature of another proof system called Plonk. And so one of the things we're very excited about with what we're doing is we're integrating kind of the best of both approaches here, and we're taking the lookup tables from Plonk and we're integrating them into the Marlin proof system to get much greater efficiency than you could in another context. And why is this important? I guess for those of you who aren't familiar with Plonk and like why lookup tables help a lot, so there's certain I mentioned a while ago, there's like computers and how we reason about programs and bitwise arithmetic and integers, and then there's cryptographic elements. To translate between those things for certain operations is really expensive. For example, Kachak hashing in Ethereum is very costly to do inside of a zero-knowledge proof because it's two different things. But you could implement a lookup table and make these. You could take the cost way down. So you can basically use it to pre-compute expensive functions, and then have that be much quicker or cheaper to prove. The other thing that this gives you is batch proving. And this is actually very similar to how rollups work. In Aleo, every transaction can consist of 64 separate state transitions, and these are batched together in a single transaction. And kind of the cool thing about the model that we have using Marlin is you can batch these together in a way that the cost increases sublinearly with the number of transactions. So, you have a single transition, costs, X amount, and then as you go up and higher, closer and closer to 64, it increases sublinearly. So it kind of really it encourages, batching of things together and makes it even cheaper for the prover to ultimately compute. And I think the crossover point is basically a 4x reduction in prover time once you reach 4 transitions. Okay, moving along. So again, I wanted to go back to program runtime and why this is potentially cool and important. I gave a couple of examples, but another example that I think is really cool that no one has talked about before is using ML potentially to define some program logic. So you could imagine a world in which and actually backing up, can you do ML on Ethereum, like a linear regression, for example? And the answer is, well, it's quite expensive, again, because of the gas limit that we talked about. But because we have an unlimited runtime here, ML applications are actually fine to do in ZK. And in fact, there's a lot of really cool, interesting applications. I mean, one that we kind of played with or talked about as a toy is using potentially an ML algorithm to define a bonding curve, right? So if you think about, you take prior trade data, you run a linear regression on it, you can maybe define and publish like some new parameters around some type of bonding curve where you could trade assets against. So this is like an example of an application that is really hard or even impossible to do in the model of the on-chain computation, but it's relatively trivial to do here. Cool, and yep, okay, I think I hit on this enough. The other thing is privacy. Privacy is an interesting topic in this space because a lot of people feel very differently about it. I think for many applications at scale, privacy will be absolutely essential. I mean, if we think about the model of just blockchains in general today, it's actually shocking how transparent they are for most financial use cases. I mean, if I send somebody USDC and they've given me their address, not only do I know the content of their account, I know every single interaction they've ever had with anyone, and then recursively can figure out all of those people's interactions in the state of their account, which is very, very unlike the traditional financial system. And I think as all of us in this industry think about bringing this to the world, it's incredibly important to keep in mind that privacy is going to be a really, really critical piece, especially for financial data that people really want to protect. And so I think it's why we built this in as a first-class citizen within our system. And importantly, in Aleo, and this is maybe a distinction from Zcash and actually from some of the lessons learned from that experience, in Zcash, privacy is opt-in. So and this is actually similar how to Ethereum and Tornado Cash work. So the Tornado Cash, actually let's use Tornado Cash because it's Ethereum related. So Tornado Cash, you have an anonymity set, which is basically everybody who's transferring funds on that platform. But that is a tiny, tiny fraction, typically, of all of the funds that get transferred overall on Ethereum. And I guess the TLDR on why this is important is the smaller your anonymity set, functionally, the worse your privacy. And conversely, the bigger the anonymity set, the more you can kind of mix things together, the better your privacy. And so in Aleo's model, we have this privacy by default. So privacy by default means every transaction is private. And if you want to reveal certain information, you can. I think I got my slides a little bit out of order. Here we go, yeah. So this is actually some Aleo instructions. And by the way, if anyone's curious about what the syntax or anything looks like, this talk is not a developer workshop. This is more of a high-level talk, but we have on GitHub a bunch of examples, what Aleo instructions look like, how to use them. But anyway, this is just a quick screenshot. So you see we have two inputs. One is public, one is private, and we can also output public and private values. And like I said, this is how you as a developer can define what is private and what is public in your application. And you as a user also have the choice to share a view key with different parties if you want, regulator, et cetera. And so I think this is really important. This privacy by default is important because, again, the anonymity set increases the security and privacy for everybody and ensures that this principle you're trying to achieve is actually maintained. Okay. Another thing I'm really excited about here is this concept of approving as a service, which is what we're trying to really encourage and incentivize. And I think as we look at a world in which roll-ups in general across the space are seen as increasingly important and ZK proofs are seen as increasingly the future of computing, you're going to have an entirely new class of infrastructure built around proving quickly and efficiently. It's kind of similar to the current client-server model of the web, where I have a mobile device, and if I'm interacting with some program, typically the way it works is I outsource, I send some instructions to a server which computes something and then it sends it back and renders a result. Similarly, in our model, like I said, we have this option for users to delegate proofs to a third-party prover, and in that model, we imagine there could be provers that are quite performant. And why would they be very performant at generating zero-knowledge proofs? Well, in Aleo, provers can actually generate proofs for the protocol for the purpose of earning some of the Coinbase rewards. So unlike some systems that are proof of stake, it's only the validators that get rewards. In our system, we actually split the Coinbase reward. Some goes to the validators for producing blocks and ensuring that they're doing their job of verifying transactions. But some of it is just paid out to the provers who are effectively doing some work, some proof of work puzzle. And the reason why this is important is because it normalizes the returns for provers. So it incentivizes them to build better and faster and more efficient hardware over time, which then benefits the entire ecosystem, which I might add extends even beyond Alio. Yeah, so the way this works is that the Coinbase puzzle is effectively generating a proof. It's not actually a full zero-knowledge proof. It's a polynomial commitment, which is part of the proof production process. But anyway, as I said, the point of this is really to make sure that provers on our ecosystem are incentivized. And we actually had, on our second testnet, we had actually the consensus mechanism we ran in our second testnet back in January was a little bit different. It was more of just a strictly proof of work. And it was a really interesting experience. But one of the interesting things that came from it was that at one point, our network was producing 20,000 zero-knowledge proofs a second, which is an astounding number of proofs if you look at, if you think about like what that means in terms of scale. And I think it really goes to show how powerful incentives are in proof of work systems. And so again, we are not a proof of work blockchain, but we've retained this kind of incentive compatible architecture because we believe that provers are going to be a really essential part of how the future of zero-knowledge cryptography evolves. Okay, and then the last thing is it retains composability. I want to go back here to the concept of the program registry, which I talked about in the beginning. And I mentioned this in one of our talks that I was giving last night, where it's always kind of funny to me to consider that, in Solidity, there's no way to import some program in like a library, similar to how you could do in Python or Rust or many other programming paradigms. You just import, someone else writes a code, writes code for, I don't know, a signature algorithm or, factoring or something, and you don't want to rewrite or re-implement all that yourself, so you want to import this in a single line. You say import X library is typically the syntax. In Ethereum or with Solidity, that's typically not how it's done, and actually I'm not sure, I don't know of any other language in which this exists for blockchains. Typically you have to copy and paste all of that program logic and put it in your smart contract. And for Alio, we are actually enable people to import programs from the program registry directly, and the compiler that we have basically figures out and inputs that it synthesizes those circuits directly into the compiled R1CS of the final program. And the cool thing about this is it retains composability. So you can take what different people have worked on, combine it into something new, which I think is one of the most powerful parts about crypto architectures in general. And then the second thing is you can potentially create a world in which micropayments to the writer or the creator of a library are possible, right? And this is, I think there's many, many examples of open source libraries that are very fundamentally important to the web in general, and the maintainers of those are highly undercompensated given that importance. And so we're kind of excited about this paradigm because we think it's a way where we can change that and make an incentive compatible model for people to do this really important work. Okay, I just told you all the reasons why Alio is amazing and why zero knowledge is amazing. What is it not good for, you should be asking me. And the reality, and I'm going to use, again, I told you I'd steal liberally from a lot of other people's work. I highly recommend you read Vitalik's blog post about this. I can't remember the title, but it was 3 or 4 ago, where he talks about zero knowledge proof applications. And one of the things that he mentions in that in that blog post, which I entirely agree with, is that it's difficult to create applications that require concurrent access of the same state at the same time. So, Uniswap, for example, is not impossible in this paradigm, but it's also not simple. Like, there's a lot of assumptions that go into it, and maybe this is an example of an application that is better on a transparent blockchain like an Ethereum or Celo or something like that. And this is why I go back to say, and my personal belief is, there's going to be many architectures that are purpose-built for different things at the product or user level. And so you'll have these different ecosystems in the future. And again, I think at the lower levels, different protocols are making different trade-offs. And so this is one of the things that is a trade-off that you make when you're using zero-knowledge cryptography. Now, one of the cool things about cryptography is there's other primitives, one of which Vitalik mentioned in his prior talk, like multi-party computation. I'm sure Adrian's going to talk about fully homomorphic encryption. There's other things, other tools we have in the toolkit that can potentially solve this problem. And we're at the beginning of the potential for this technology, and I'm extremely excited to see how things continue to develop there. Okay, and so I'm quickly going to, I should quickly mention that we had a test net that ran in January. We're launching our mainnet in December. Between now and then, we're running a testnet 3, which is the final kind of burn-in for our network. We just launched last week. The initial phase is focused on developers deploying programs, so if any of you are interested in this, highly encourage you to go to our GitHub at Alio HQ You can download all the repos. You can get a feel for what writing programs in Leo and the AVM is like, deploy those programs to chain, and we're incentivizing this process, and we'll be releasing some details in a blog over the coming days. But this is what we consider the first phase of our third testnet. The second phase is where we really open it up to provers. I mentioned a minute ago we have this coin-based puzzle that provers can participate in to earn credits, and this will be the focus of the second phase. So we want people, and potentially, for anyone in this room who is an Ethereum miner, who might be facing a situation where your GPUs might not be that useful anymore, you can take those GPUs and prove on Aleo to help earn, or to earn coin-based rewards, and then potentially with those rewards participate in the third phase, where we have validators, and who are, again, as I mentioned, we have this proof of stake consensus. So with the tokens that you've earned as a prover, you can participate as a validator, help construct blocks, and verify transactions. And with that, we'll take from the third phase, we'll go right into our mainnet launch plan for the end of the year. Okay, cool. I want to end, I have 2 slides left. I want to end on, and say a couple things, because this is an Ethereum meetup, and I want to talk about a couple, and I guess I should say, I myself, even though I'm working at Aleo, consider myself to be a member of the Ethereum community, have been for a long time. And there's other things that I work on, and we work on at Aleo, that I think are relevant for anyone and in the Ethereum community or even beyond. And one of them is zPrize. zPrize is focused on accelerating hardware for zero-knowledge proofs and ZK snarks. It's an effort that Aleo is part of, but it also includes 20 different teams from across the ecosystem, including Anoma, many others, Polygon as well. And this is really exciting because I think one of the things that people don't realize about the progress of the web is that one of the big turning points was adding in cryptographic instructions into Intel chips to make HTTPS faster from a human standpoint. So I remember a day or a time when I was much younger that to load an HTTPS website it felt a lot longer than it does today, and that was because these cryptographic operations that you need to perform when you're doing an HTTPS request as opposed to an HTTP request are much more expensive. And when Intel baked those directly into the CPU, that reduced the human time cost tremendously. And I'm hoping, I feel, and you already can see with the number of startups that are starting focused on ZK hardware, that this is the direction of zero-knowledge proofs too. So even though we have kind of this, it's expensive to compute these proofs in kind of the typical complexity model, in real-world human time, you can reduce that time tremendously by advancing and increasing the sophistication of hardware. And we're already seeing the progress. I mean, even in the last 10 years, it's astounding. If you look at Zcash, Zcash transactions used to take a minute or more, and now it's easily sub-second, right? And Aleo, similarly, transactions take sub-second. And with specialized hardware, we can take that even further. So this is an effort I'm really excited about. This is, by the way, I should say a little more about this. So the zPrize is a competition where 70 different teams from around the world are competing to solve these problems that are kind of really important with regard to generating zero-knowledge proofs on different hardware platforms, on servers for provers as a service, on clients, and on mobile phones. So all of the work is going to be open sourced when the conclusion ends in October, and I'm really excited to share a little bit more about it at that time. The other thing I wanted to tell you is I glossed over this in the beginning of the talk, but Aleo relies on ZK snarks, which require trusted setup. And obviously, this is incredibly important because the security of the system depends on the trusted setup. And so this is why we spent a lot of time, effort, and energy to run a setup ceremony. We actually ran 3 setup ceremonies. As I said, our proof system that we use is Marlin. There was one time when we were combining Groth 16 proof systems and Marlin together, and so we actually ran 3 setup ceremonies, one for Marlin for up statement size to the 28th, and then 2 for Groth 16 size to the 20 and to the 19th. So we ran a phase 1 for both the Groth 16 ceremonies, and we ran just Marlin setups only require 1 phase. So the Marlin setup has 137 contributors to it, so people from our community, from the Ethereum community, from around the world who participated and generated these parameters. And the Groth 16 collectively, both of those other 2 Groth 16 ceremonies have over 1,000 contributors each. Why is this cool? Well, there's no reason why anyone else can't use these setup parameters for their own zero-knowledge projects. So it doesn't have to be on Aleo, it can be on Ethereum, it can be anywhere. You can use any of the parameters that we generated, and you can take those and you can build your own circuits without having to redo a trusted setup yourself. And if you want to see, you can see Aleo or setup.aleo.org. You can see all the information about who attested to contributing and get a sense for in my opinion, the way to assess the security of these things is how many people contributed, and I'm pretty happy to say that we have the largest setup that I know of in history for crypto. So again, this is something that we view as a public good that we hope, not only do we hope, but we want people to take and use in their own projects. Okay, so if you want to learn more, I've got some links here. So aleo.org is our website, community where we put out most of the announcements with regard to testnet, et cetera, aleo.org/discord. And then we have a Twitter handle. I would encourage you to follow us if you're interested in zero knowledge in general. And thank you very much. I don't know if we have time for questions. Okay, I may have run over, so sorry if I did, but thank you very much, everybody. I really appreciate it.
Cool. Hello. Great. We're ready to go. All right. Great to be here. Thank you for inviting me, Erica. I'm Adrian. I'm one of the co-founders of Anoma. And today I want to give you sort of a brief glimpse of Anoma and what we are doing with Anoma, which is a unified architecture for full-stack decentralized applications. I'll start with a sort of brief historic recap here of where we started, where we are today, and I think where we're going to go in the future. The very first thing that we got was, and by the way, so like a lot of other people historically have used different delineations for how these, like how you think of generations, evolutions of blockchains, and I think what I'm presenting today is very different from this, but I think it's somewhat more sensical. So really the first generation of blockchains was scriptable settlement, and this is what we got with Bitcoin in 2008. Bitcoin was massively innovative at the time, and it was great at building things like cryptocurrencies. Interesting enough, people started to build applications like colored coins, Namecoin, and a long tail of Bitcoin forks on top of Bitcoin. The important thing to remember though is that they were incredibly clunky. Like colored coins weren't easy to use on Bitcoin. Namecoin wasn't easy to use. Namecoin even required a fork of the original Bitcoin client in order to make it work, right? But this is what scriptable settlement gave us. And to me, this is really the first generation of blockchains. Then we got Ethereum, and Ethereum sort of ushered in the second generation of programmable settlement. And Vitalik actually talks about this in the original Ethereum white paper, that like one of the motivations for Ethereum was that colored coins on Bitcoin was incredibly clunky. And we needed something that was more expressive, more programmable than simple Bitcoin script. So we moved from colored coins to ERC20s, we moved from Namecoin to ENS. But the really important thing to remember is that when Ethereum was designed in 2014, we thought of a couple of applications that you can sort of bring over and make more efficient, going from Bitcoin to Ethereum. But there was a host of other applications that we sort of discovered later on are actually incredibly powerful and can be built only on programmable settlement. These include things like DAOs, like NFTs, soul-bound tokens, what Vitalik just spoke about, right? So there was this host of new kinds of applications that were enabled by programmable settlement. And you see this nowadays, right? That there's a ton of more applications just outside of ERC20s. There is now we have modern applications like DEXs, AMMs, NFT marketplaces. But I would argue that they currently have similar downsides on Ethereum or on essentially programmable settlement layers than we had on Bitcoin with colored coins in the past, right? They're generally still clunky to use. They generally still require at least one centralized Web 2 component, which, for example, in the case of OpenSea is users, Alex mentioned intents, right? Like users don't send transactions on Ethereum when they interact with OpenSea. No, they sign a message and they send it to a centralized Web 2 server run by the OpenSea team that then does some compute and then ends up settling some output of that compute on Ethereum. This is the same for Xerox. This is the same for Kausop. This is the same for Optimism and Starknet too. It's always the same pattern. People don't directly interact with these systems because they require interactivity. How do you get interactivity in the current model? Well, you send stuff to a Web2 server that does some compute and then settles after you have done the interactive step something on a programmable settlement layer. And I mean, historically, people keep talking about like generation 3, generation 4, and like any upgrade in a consensus mechanism is a new generation of blockchain. And I would actually argue that in terms of what they fundamentally bring to developers and what kind of applications we can build on these systems, they're really, really similar to Ethereum. I call them second generation plus plus. So we've made some advances in, for example, proof of stake, Sybil resistance. We moved from proof of work to proof of stake, and that's now working really well. We also made tremendous advances in consensus mechanisms, like we have Tendermint now, we have Avalanche, we hopefully eventually get ETH2 single slot finality, right? But it's still fundamentally the same model. It's programmable settlement. It's the chain does nothing but settle some state transition. Yeah, so in the end, it's still programmable settlement. The important thing to remember, though, is that settlement is not sufficient. Settlement is sufficient if the parties already know who they are, what they want, and with whom to coordinate. This is generally not true for most interesting things. Like if you think you want to sell an asset, like you want to sell some ETH for Bitcoin, you need interactivity to discover a counterparty that has the inverse. If you want to sell an NFT, you need a counterparty. So pretty much everything that's interesting requires some amount of counterparty discovery. Like the only thing that doesn't actually require interactivity or counterparty discovery is if I want to send money to myself. Like if I want to send money to myself, I have all the state that I need. I know my addresses, and for example, I can use as a result like something like Tornado Cash on Ethereum. That actually doesn't require counterparty discovery, but it's a minuscule part of sort of what I would consider interesting applications at the moment. Yeah, so many applications actually need this kind of counterparty discovery service because it is really difficult to have a decentralized way of like, oh, I want to trade Bitcoin for ETH. Oh, Bob in San Francisco has the inverse of this transaction and is willing to coordinate with me. So you see this everywhere. You see this in marketplaces, like OpenSea is a great example here. You see this in quadratic public goods funding with Gitcoin. You have project donors and funders that all need to discover each other. You see this also in DAOs. Also, you see this in rollups. Like rollups also need counterparty discovery because this is exactly what a rollup server does. Like this is what the optimism server does. It aggregates a bunch of people's intents, does some compute, so like does the counterparty discovery and solving for this system, and then settles it on some underlying base layer, at the moment Ethereum. So how do we currently deal with counterparty discovery? Well, we have AMMs, and I would say AMMs are sort of the best answer we have to counterparty discovery if we live in a programmable settlement world, right? Like if the thing that you have available is programmable settlement, an AMM is probably the best thing you can do to enable decentralized counterparty discovery because you just treat the Ethereum consensus state as this is the main counterparty discovery point, and everyone talks to this and everyone sees the state updates. The problem is this is very expensive because everything has to be now globally ordered, and it's incredibly silly because you don't need a total global order to be established to say, oh, I want to trade some ETH for Bitcoin. This is mostly that like it's a side effect of just being stuck in this programmable settlement world. On-chain order books kind of do exactly the same thing where like the easy answer is always you just dump everything on-chain and establish a total global order over the transactions or the intents and then have the system figured out. But it's really expensive. So the other very common approach nowadays is single operator databases that just act as centralization points. So OpenSea does this with a centralized OpenSea server run by the company. 0x relayers do this. Flashbots, interestingly enough, it's exactly the same pattern. In Flashbots, people sign a message, they send it to a centralized Flashbot server. They call this the MEV relayer. That does some compute and then settles on a chain, right? Yeah, rollup sequencers do this. So these are always trusted parties. In the best case, they can't steal your money. In the worst case, they are effectively a centralized exchange that can run away with all your funds. This is why we've designed systems like fraud proofs and so on in order to like reduce the trust assumptions on these central parties. But in all cases, these trusted single operator databases can censor you, as in they can prevent you from interacting with the system because they have a single IP address that can just block your submissions. And now there are some other approaches like app-specific sovereign chains. DYDX is trying this out right now. There are a lot of other downsides because now all of a sudden you have to launch your own blockchain. It's a lot of dev work. You lose full composability across the ecosystem because all of a sudden, to be fair, you already don't have this on current programmable settlement architectures, where like specific intents are siloed in their little application. I can't build a new application that reasons over, let's say, the OpenSea and the 0x intents at the same time. So today I'm going to present ANOMA, which is, it's an architecture. This is sort of an important thing to understand. It's an architecture with many different deployment models. You can deploy, and I'll speak more in depth about this in a bit, but you can deploy ANOMA as an L1. Many people can deploy ANOMA as many L1s, like if a city wants to take ANOMA and deploy as an L1, that works too. You can deploy this as an L1.5 or as an L2. Yeah, so ANOMA is a unified architecture for full stack decentralized applications. What does this mean more in depth? Well, the really long but all-encompassing tagline is that it's an intent-centric, privacy-preserving protocol for decentralized counterparty discovery, solving, and atomic multi-chain settlement. I'll go through the first part of the sentence, not so much atomic multi-chain settlement. There are other talks. I don't have like 2 hours to explain atomic multi-chain settlement today. So what are the key design principles? Well, 1, it's intent centricity, and 2, it's homogeneous architectures and heterogeneous security models. And we've already spoken a little bit about what does it mean for something to be intent-centric. It's the idea that users express what they want and not how to get this. This is also honestly like the mental model that I think everyone has when they interact with a blockchain. But what you currently do effectively in whether this is the EVM or the Near VM or the Solana VM, it's always you don't actually express what you want. You authorize an execution trace. Like when you send a transaction on these systems, you authorize not a specific future result. You authorize there are these opcodes, and these opcodes can do arbitrary compute. As a result, this means as a user, you have to audit, honestly, every single opcode that you sign over, because otherwise you can have proxy contracts that steal your money. Because they can do arbitrary things, because as a user, you never defined what you wanted, you just defined on how to get it. This is also something that I think my parents will never be able to understand in terms of the security model that they have when interacting with blockchains. Like when someone taps their card in a store, they don't think I'm authorizing all API calls between all Visa servers, and they may do arbitrary things, and afterwards I should check whether they cheated me. Like the mental model is you tap your card and you're authorizing a specific state transition. Like you're authorizing that some money is debited from your account. So intents are binding programmatic commitments to state preferences. Once you think more about intent centricity and how you design underlying architectures, a really nice other feature is that it falls out that you can have a P2P intent gossip network that doesn't have to be globally consistent. As in, everyone in this room can have a different view of the current available intents in the world. So as a result, you can have like 100 billion intents floating around because they're not consensus critical. We don't need a globally consistent view of them. And different people can opt in to receive different intents, right? Because maybe I only care about the OpenSea intents because I am into NFTs and I want to see all the NFT trades. So I can only subscribe to the open. Is that a fire alarm? Okay, good. Right. So now you have an intent gossip network, right? You have 100 billion intents floating around. They're not settled, actually. Like, they're just like what individual people want. How do you actually end up combining these intents and creating transactions out of this? This is where solvers come in. They exist pretty much right now. Like an OpenSea server is already a solver for OpenSea. The optimism sequencer is already a solver just for optimism specifically. A Starknet prover is a solver just for the Starknet specific intents. But with ANOMA, you can have a generalized intent. And then you can have solvers that go, these 15 things are combinable. Maybe there are some fungible token trading, right? Because you can do things like, user A wants to do ETH for Bitcoin, user B wants to do Bitcoin for Near, and user C wants to do Near for ETH, completing the cycle. So you can settle an arbitrary number of intents in the same transaction. So solvers, they will most likely specialize in some specific intents. Building generalized solvers is very hard. This is probably an NP hard problem. So if someone can solve this, you will make a fuck ton of money because you can sort of solve over an arbitrary state transition. Practically speaking, different solvers can specialize for different kinds of intents. So for example, you can specialize for fungible token trading, you can specialize for NFT trading, you can specialize for like lunch date setups, because the important thing to remember about intents is that they're fully programmatic, as an intent is just code that you're trading with other people. It is not specific to actually like what you think of a financial transaction or trade. You can say that you can use the intent system to express that you want to meet someone that is into board games at a cafe in Seoul on like Sunday at 5 p.m. It's just whatever you can write in WASM, you can express as an intent. There are no restrictions here. Yes, and this leads to a nice feature that intents are fully composable. You can reason as a solver over the OpenSea intents, the optimism intents, and like normal trading intent at the same time, and figure out which ones are combinable there. Yeah, then solvers create transactions, and transactions are then settled on a settlement layer. And here it actually doesn't matter which settlement layer. This is why I mean that you can deploy an architecture like ANOMA to Ethereum as an L2, where Ethereum just ends up being the settlement layer. This kind of intent-centric design is what everyone is discovering at the moment, but for application-specific purposes, right? Like Optimism, Flashbots, they're all discovering that they should be thinking about intents, but people still think about transactions. But if you actually want to have decentralized counterparty discovery, you need to be thinking about intents. The other cool thing is that this leads to a very declarative paradigm for application development, where I said in the beginning, currently in transaction-centric designs, you authorize execution traces of how your smart contract is allowed to do compute. In intent-centric design, you don't actually do this. You just say what future state transitions you find with. As a result, you don't have to worry about the intermediate steps that get invoked and whether like a proxy contract is broken or not, because you never authorize a proxy contract. I guess as long as that proxy contract returns you the state changes that you are okay with in your intent, this is fine. And this is actually also how sort of the ANOMA settlement layer works, is that instead of doing arbitrary compute in the contracts, transactions define what the outcoming, like what the resulting state transitions are going to be, and then all the intents just verify that they're okay with the resulting state changes. For an end user, this has the really nice benefit that it's a black box. Like users author intents, then submit them, then magic happens because they don't care on how these intents get satisfied, and afterwards they just need to verify whether their intent was settled or not. So I'm not going to walk through this entire diagram, but this is sort of a high-level overview of the architecture of ANOMA, where on the far left you have counterparty discovery, where users actually write intents, and intents can be either transparent, shielded, or private. If they're shielded, they involve also the generation of a bunch of zero-knowledge proofs. If they're private, they also involve zero-knowledge proofs and fully homomorphic encryption. Honestly, FHE is like at least 5 years out. That's still very exploratory research. Then users sign these intents, they submit them to, their client submits them. Now it hits the intent gossip network. And the nice thing is the intent gossip network can span over many different blockchains at the same time, over many different deployment models of ANOMA at the same time. So you have one globally connected intent gossip network that can handle the intents for like the ANOMA L1 deployment, the ANOMA South Korea deployment, or the ANOMA L2 deployment on Ethereum. And because intents can just specify in which security model they want to be settled. Solvers look at a number of intents, maybe they take 15, combine them into a transaction. They submit them to a transaction mempool, but first they encrypt all transactions. So in ANOMA, transactions are encrypted against a public key run by the validator set. This uses a protocol called Fairview, which is a distributed key generation protocol. High level, this solves MEV. All transactions are encrypted. Validators only order and propose encrypted transactions. So in block N, you fix a list of, you fix the ordering of a list of encrypted byte strings. And in block N+1, the validator set jointly decrypts all the encrypted transactions and then executes them. But at that point, they can't sandwich, front run, or back run you anymore because the ordering has already been established. Yeah, now you have a finalized block. And then you go into the execution verification environment, which is a unified execution environment that you can be deployed to many different sort of settlement layers. This also allows you to, one of the very nice things about the unified execution environment is that it handles transparent, shielded, and private state at the same time. As in, you can write applications that are partially transparent and partially private, because this will honestly depend on the specific applications on how much privacy or at what level do they need privacy. And then in the end, users just can verify the settlement of an intent. How many? Time is fine. Right. Homogeneous architecture, heterogeneous security. So one of the important things to sort of realize is that protocols can easily be benevolent monopolies. Like, we all benefit from agreeing on TCP/IP as a standard. No one actually makes any money on this, but it's just nice that we can use the same protocols to talk to all the servers in the world. This is also why our phones are pretty cool, because we sort of globally agreed on a cellular backbone standard, and my phone that I bought in Europe works in Asia, as well as in North America, as well as in South America, as well as in Africa, right? Like, my phone can use the same protocols to roam in different security models. And the big thing to realize is like that the losses of protocol standardization are like very minimal. Like, sure, we could build a slightly better version of TCP/IP, but we would lose much more by the fragmentation of having a ton of different protocols than we would by sort of the tiny losses that we take because maybe TCP/IP isn't exactly optimal. The very important thing, though, is that security domains should not be monopolies, because security domains are, for example, a country is a security domain, right? Like, a validator set is a security domain. Like, Ethereum is one specific security domain, and it can charge rent, it can steal funds, it can collapse, right? Like, different security domains have different security properties, and they can fail independently of each other. And as users, we want to be very capable of not, like, this is not about telling people what kind of security they should be using. It's more that people should have a choice. As in, maybe to my parents, it's preferable that all their digital assets are secured by the 200 people in their village, because this is sort of their local trust zone. This is the people they trust. But maybe someone that lives in Argentina really wants to have their assets in the global Ethereum security model, because they don't trust their local government, but they trust the global Ethereum model. So yeah, we should be separating protocols and architectures from the underlying security models. Currently, we tend to very much tie them together. So this leads to the nice fact that you can deploy ANOMA as an architecture in many different ways. You can deploy this as an L1, as a sovereign chain. This is what we are currently doing as a first step. You can deploy them as community-operated chains where, let's say, the World of Warcraft community wants to have a financial settlement backbone. They can like take this architecture and run it themselves. The city of Seoul can do this to run the financial system in Seoul. You can also deploy this as an L1.5 if you just want to decentralize a specific dApp construction. So for example, you could have a specific deployment for, let's say, OpenSea. Or you can deploy this as a generalized L2 where you build the dApps, where you use the distributed decentralized counterparty discovery and solving component of ANOMA while keeping all the settlement to Ethereum. Yep, so in the first case, you just use the intent Gauss subnetwork only and sequence and settle elsewhere. The second model is you decentralize the solvers, i.e. you decentralize the rollup sequencers or the provers or the OpenSea servers, but the settlement still happens on your preferred security model, which I think for most people in this room, including me at the moment, is probably Ethereum. Or you can also use this to decentralize specific applications, or you can deploy ANOMA as a fractal instance with local settlement guarantees. So how do dApps on ANOMA actually look like? Well, they have intent formats. This is something people need to agree on. They have solver algorithms, which don't have to be optimal. They just have, like, most likely applications on ANOMA should just like provide a standard solver implementation so that at least there's some like baseline solvers available. But there's a huge incentive for people to build their own solvers that are, because you're competing effectively. You are trying to, the people that can most efficiently solve can settle most intents, and they can gather the fees from them. And then you also have validity predicates, which are settlement invariants for users or applications. For example, if you're transacting with Bitcoin on ANOMA, the settlement invariant for Bitcoin is that ANOMA cannot create or destroy Bitcoin. So like applications as well as users can have settlement invariants that need to be enforced. This kind of vertically integrated architecture means that you get end-to-end security, liveness, and privacy guarantees. And importantly, that like our phones, applications are portable across security domains, as in like your application, your wallet can start roaming between different blockchains as long as we all agree on similar kind of protocols. So what can you build with ANOMA? Well, you can build, and this sort of goes back to the earliest thing, which I said when we went from Bitcoin to Ethereum and now to sort of this ANOMA architecture, that we didn't think of all the applications that you could be built using this kind of architecture when we built Ethereum. And I think there's like a number of existing dApps that I can see using this kind of stuff. But I think there's also going to be a large number of applications that haven't been explored yet, because we're just starting to sort of think about what this generalized architecture means. So existing dApps you can build with full stack decentralization are like things like fungible token swaps, like 0x CowSwap, non-fungible marketplaces, Wyvern, Seaport, OpenSea. You can build a very capital efficient AMMs because you don't need capital locking. And you can decentralize the rollups using Anoma. You can do public goods funding. So Gitcoin without the semi-trusted multisig, where everyone's commitments to fund a certain project are just intents. And once you reach a threshold, a solver can figure out what is the best combination of these intents, which project should receive the right amount of funding. But there's also a ton of novel dApps that I can already think about that require more than simple programmable settlement. Things like private DAOs, private auctions. So Anoma also comes due to the fact that we have a threshold decryption system that prevents front running. We also get effectively a programmable threshold decryption where applications can say, here's a batch, all transactions for this specific application are encrypted. Let's say for the duration of this batch, let's say 10 blocks. And this is what you use in order to build like second price auctions that aren't front runnable, because everyone in the auction submits their bits. They're encrypted for the batch duration or for the auction duration. They can be defined by the application. Afterwards, the validator set starts decrypts all bits at the same time, and then the application just needs to verify what is actually the winning bit, but no one can inject new bits or remove old bits from it. Yes, you can build private games. I think the thing that I'm most excited about is multivariate, multi-party, multivariate private bartering. It's the idea that you can, I can say that I want to trade some Bitcoin against some CryptoKitties. Someone else wants to trade CryptoKitties against train tickets in Seoul, and a third person wants to trade like train tickets, if the weather is nice, against Bitcoin. As long as the weather is nice, all these three things are combinable and settleable, and this like scales to end-party bartering, as in you can have 1,000 individual intents that are all settleable together. Which means as a user, I don't have to worry about like figuring out the right route for my asset. I just say what I have and what I want, and as long as there's some sort of path, intents can represent this. And you can build on-demand runtime rollups, because what is a rollup? Essentially, a rollup is a computational compression. Once you have an intent that goes from A to B, and another intent that goes from B to C, and a third intent that goes from C to D, you can just collapse them to one intent from A to D. And this is so high level what rollups do. Yeah, so Anoma is built by Heliax. These are my two co-founders. So it's ours here as well as in the room. The team is much larger than this, so we couldn't build this with the three of us. So check out the team. Yeah, and this is Anoma for you. It's a unified architecture for full stack decentralization. Otherwise, you can also find me afterwards because we're 15 minutes behind.
Thank you. Before I get started, I just want to thank the organizers and the production crew and the volunteers and everyone who helped put this together. It's been a really great experience so far. My name is Camila Ramos. I'm a developer relations engineer at EdgeNode, which is a core developer of the Graph protocol. And a little bit about me, a quick intro. I kind of have a traditional and non-traditional path to kind of crypto and engineering in general. My background before I did computer science was in education. I've always loved teaching, I've always loved education, and I always thought I was going to be a regular kind of K-12 teacher. And then in high school, I got interested in computer science and coding once I kind of realized that teaching doesn't really pay well in the United States, and it's really just not a good path to go down in terms of quality of life. So I was like, hey, look, I live in the Bay. I see everyone has Teslas. Everyone here is an engineer. They do pretty well, so I'm going to learn how to code too. And then I did. I studied computer science in college and then started off my career at PayPal, where I worked on the checkout experience as part of the engineering team. So everywhere where you're checking out and you see the button Pay with PayPal, that's what I worked on for about a year and a half. And then today what we're going to talk about is the Web3 stack and kind of a more practical point of view. So when I was getting started building in blockchain and in crypto, it was kind of hard to understand how to make all the protocols, how to string them all together, how to make them communicate with each other, how to actually build something that works. So in this talk, I'm hoping to outline this in a really practical way and show you guys code and kind of very specifically and explicitly explain how you can build a full stack decentralized application. So a lot of these definitions are from a blog post which are linked in this presentation, and I'll tweet out the slides with all of the links so that you can read more about these and actually be able to check this out yourself. So the Web3 stack, as defined by this blog post that we're talking about, is a set of protocols that enables fully decentralized applications. So real quick, I'm not going to talk about these one by one because I think everyone here kind of is passionate and understands why we're here. I usually use this slide when I'm talking to newer audiences and maybe some Web 2 audiences, but I just wanted to add this so we can kind of capture what we're going to talk about in the next few slides and how these protocols enable these points. So when we're talking about building decentralized applications, and maybe if you're coming from a traditional engineering world, actually maybe I shouldn't stand here because I'm blocking, sorry. There we go. If you're coming from kind of traditional engineering, there's certain pieces and architecture that you're familiar with, right? We know that we work with APIs, we have this concept of a front end, we have this concept of a back end, we have this concept of a database, etc. And I found that it's helpful to kind of start by listing out what are the building blocks and the primitives that you need to keep in mind when you're building. So blockchain, your L1, your development environment, file storage, off-chain data protocols, API, indexing and querying, identity, client frameworks and libraries, oracles, and then kind of in their own bullet point is Web3 social protocols. And again, at the bottom, there's linked this blog post that was created by the research team at EdgeNode, and that was authored by Nader, who's sitting right there, where it goes kind of more into detail about all of these things. And then this image was really helpful to me when I first started building because it kind of visually lays out the whole stack, and then it allows you to kind of check this out and define for yourself what is an ideal stack based on my use case. So I'll leave this up for a second. And we're going to kind of go through this and talk about what my stack looks like and then go through some screenshots of some code for how to actually implement something like this. Okay, cool. I also have these up. So Web3 Social, I wanted to highlight Live Peer and Lens. They're part of this last bullet point, here about Web3 social protocols that kind of weren't captured in any of the other bullet points, but that I wanted to highlight. So Live Peer is a decentralized video infrastructure that allows you to integrate live streaming into your dApps. And then Lens is a decentralized, non-custodial social graph for building composable social applications. And in this slide, there are 2 resources linked, like a tutorial to get started with both of these, which again, when I tweet these slides out, you'll be able to actually click on these links and access those. So talking about kind of what a stack could look like, this isn't the stack for everyone. A lot of this is up to personal preference. It's also kind of where you are in your timeline of learning, and you'll notice that in one of these I have an arrow to kind of indicate that. So let's talk about this. So when I build on Ethereum, I use Polygon as my sidechain. And for my RPC provider, which is actually the way for you to write to the blockchain, it kind of provides that node, that access point to the blockchain. I use Infura, but the other ones out there are like Alchemy, Anchor, There's a bunch more. I use Infura. For my development environment, I started out using Hardhat. That's kind of what I used the whole 9 months or something up until this point. And then recently, I've started learning Foundry and trying to use Foundry. So that's kind of what I mean when I say this is really relevant to where you are in your journey. You might have started off with Hardhat because that was what was really popular a year ago, and kind of now Foundry is picking up speed and picking up adoption, and after you've worked with Hardhat, you'll be able to see okay, this is a better experience for XYZ, but for other cases, you might have a better experience with other tools, so it just kind of depends where you are and what you're working on. For off-chain storage, I use IPFS and Web3 storage, and recently I've started using Arweave. Another example of kind of just depends where you are in your learning. I started off with IPFS and Web3 storage, and then recently for an app I was building, there was something that was a lot easier to do with Arweave, so I kind of just tried it for the first time and realized that that was a better choice for this specific app that I was building. But they both do similar things. It's a way for you to store data off-chain such that storing things on-chain is expensive, so not everything has to be on-chain. But still, you want to be able to store these things, so you can use something like IPFS/Web3 storage and Arweave. For indexing, I use the graph, and that's where I do developer relations at, and we're going to get into that more deeply about what that means. For identity, I've been using Coinbase Wallet as my development wallet. Coinbase Wallet is, I would say, a relatively new wallet, but they actually have a lot of cool features for developers, and they're really good at listening to developer feedback, so I've been working pretty closely with the team to give them my feedback, and it's been pretty cool to see them implement some of this stuff. And then I use Rainbow Kit for that piece that kind of allows a user to connect their wallet, and we'll talk about that more later. And then finally, for client, I use Ethers and WagMe. So now, how many here have heard of the graph? By a show of hands. Okay, cool. How many people have actually used the graph? Okay, so not that many, so this is great. So I'm gonna kind of give you a crash course 101 for how to build with a graph, what it actually means. So the graph is an indexing and query protocol that allows developers to efficiently read data from the blockchain. So, as we're writing blockchain applications, a bunch of stuff gets stored on chain. And you as a developer, you might want to access this data for your own application. And right now, there's really no efficient way to make queries against the blockchain for things that are more sophisticated than asking single questions. For example, with something like Etherscan, you can go in there and ask who's the owner of this specific ID, or you can say what's the balance of this specific wallet. You can ask these kinds of simple questions, but for more complex things, like give me all of the wallets that have 10 Ether or more and own this NFT. You can't really do that right now without kind of writing your own indexer and going through this whole process. So the graph makes it really easy to do that. And at the time of writing these slides, this was the current block count of Ethereum, 14 million. I think now it's past 15 million. And in a block, you can fit an average of 70 simple transactions. So we're looking at least 15 million times 70 pieces of data that you as a developer might be interested in. So it's a whole breadth of data that you as a developer have access to, and the graph is the door for you to actually access that and build with it. So the data you want to query for is somewhere in the blockchain, right? But due to the nature and the structure of a blockchain, there really is no built-in way to identify, query for this data. And then, like I said, it's a querying and index protocol that allows you to read data from the blockchain. And the cool thing is that if you come from a traditional software background, you're probably already familiar with GraphQL. And the graph uses the GraphQL query API to be able to call this query from your front-end application. So for me as a developer, when I was first starting, it was a really cool way, an easy way to get started with Web3 because it was something that was already super familiar to me. And instead of reading from a database like you do in Web 2, you read from a blockchain. So some quick bullet points about the graph. It's chain agnostic, meaning that it's not built specifically for one chain. There's support for many chains right now on our hosted service, and then on the decentralized network, all that support will be coming over there. Now, instead of reading from a database, like I said, you're reading directly from one of these chains. And then you as a developer, you write these resolvers, which are just functions that apply logic to transform the raw data from the blockchain into these objects that you define in your schema. So we'll talk about this in a more practical sense in a second, like what that actually means. And then just a quick note on indexing. So indexing refers to the process of turning unordered data into an order that will maximize the efficiency of a query made against that data. So a real-life example is if you are in a library and you're looking for a book, I don't know, about World War II, you don't just walk around the whole library looking book by book, row by row, right? There's a system in place these books are indexed in such a way that when you walk in, you go, okay, this is where the history books are, and then on this specific aisle, it's where the World War II books are. So that's what the graph does with blockchain data. It indexes it so that you don't so you make very efficient queries against this type of data. There we go. So these things that you build with a graph are called subgraphs. Anyone can make one, and once they are published and deployed, they are open APIs that anyone can have access to. So if I build a subgraph for my project, all of you guys can see it, and all of you guys can call it in your application if you wanted to. And there's already a bunch of subgraphs deployed. So like LivePeer, Radical, Uniswap, a bunch of big projects already have a subgraph deployed. So if you were interested in the data that, for example, Uniswap is indexing, and you could use it in your application just by calling it in your front end. And this is just a cool little visual to kind of help you understand where the graph sits in the stack. Now, so to define a subgraph, like I said, crash course, we'll talk about this a little bit more kind of in a real world use case shortly after this, but in order to define a subgraph, you as a developer, you define a few things. So the first is the data source, or the data sources. So this means what contract address you're interested in indexing. So for example, if I'm building a dApp, I have to write a smart contract for it. Therefore, I'm interested in indexing this data, so I'd pass in my address. You could pass in multiple addresses. The second thing that you define is the data that should be indexed. So this is the actual data that you're going to be interested in querying for later. So if, for example, I'm going to show you later, we're building an application for event creation and management, like something like Eventbrite or something like Luma. People are able to create events like, ETH Seoul, and then users like you guys are able to RSVP to them. Me, as a developer, I would maybe be interested in knowing, who is RSVP to my event, who created different events. So the data that I would want to index is that specific thing. So who created events, what's the name of the event, what's the max capacity of the event, et cetera, and then similar information for who's RSVPing. The third thing is events you want to listen for. So the graph works based on events, Solidity events that are defined in your smart contract. So for example, I might create a custom event called new RSVP created that will be emitted every time someone creates an RSVP in my application. And this is kind of the hook or the trigger for the graph to know, okay, it's time to re-index because something new has happened. And this is the mechanism for you to ensure that you always have fresh data and that your data isn't stale. Because if, for example, you make a query in your subgraph to say, give me the list of people who RSVP'd to this event, and there's, say, 10 people. But in the next minute, 2 more people RSVP'd. How are you going to ensure that you have those 2 people, and how are you going to ensure that you have the most up-to-date data? Is through these events. So when someone RSVPs, it emits this event, and then the graph knows, okay, we need to go ahead and re-index and get the freshest data. So that's what that is for. And then finally, you as a developer, you write these resolvers that execute when these events are emitted. So when this event gets emitted, new RSVP created, something has to happen, some logic has to happen for this data to be indexed and then for this new information to be stored. And those are the resolvers that are written by you, a developer. And then this is just a screenshot of what it looks like to make a query in the playground. So it looks kind of blurry, but this is a lens subgraph. So here someone's making a query for profiles, the total number of followers, their profile ID, their handle, etc. So it just looks like regular GraphQL. And now we're going to kind of walk through an app that was built and kind of go through all of the pieces that we talked about in the tech stack and how they actually communicate with each other. So first I'm going to show some screenshots. I thought I was going to be able to kind of live code and live show you, but that was impossible. So I just put up screenshots and then we'll talk about it. So this is what the homepage looks like. Discover what's happening in the metaverse. The events that are shown in the front are kind of the events that are in your area or that you're able to RSVP for. This is the flow for creating a new event. So if you were like, oh, I want to host a birthday party or something, you could create a new event. You set the name, the time, the capacity, a refundable deposit, event link, and description, and then you create it. And then you have your own user dashboard once you connect your wallet where you can see both the events you have created and then the events you've RSVP'd for. So it's kind of like now, so when I say events, that's what I mean. We're talking about this specific app. Okay, so now I want to bring up this kind of architecture diagram, and I don't know if it's easy to view, but again, I'll post these slides and you can see, but for me, this was really, really helpful to start building dApps because it kind of lays out how everything actually communicates with each other. And don't worry if it's not quite clear from this picture, we'll kind of walk through it together in a second, but on the bottom left for you guys, you have your contract. And the contract that you wrote specifically for this that handles things like RSVPs, new event creation, etc. And then you'll see at the very top above it, you have your subgraph. So the subgraph, like I said, it gets triggered by events that get emitted from our contract. And then the subgraph also collects data from our off-chain storage, because although some of the data is stored on our contract, some of it is not stored on the contract, right? For example, something like the event name and description don't need to be stored on chain. It would be super expensive to do so, so stuff like that is stored off-chain. Then we have our front-end application, our client app in the blue right there, and you'll see that it reads data from our subgraph, and then it also sends queries to our subgraph. So you ask for a query, you say, hey, give me the, I don't know, the top 5 events in my area, and then the subgraph returns those that you can then display in your UI. You'll notice going from our front-end app, we have RainbowKit/WagMe, which is the way for users to connect their wallet. And finally, kind of below that, we have Infura, that's kind of the RPC provider that's connecting the contract to WagMe/RainbowKit to our front end. So remember, Infura is the RPC provider that allows you to actually make transactions. It's the entry point to the blockchain so that you don't have to run your own node. So that's kind of where the role that that's playing. Okay, so again, I thought I would be able to live code, so I just put screenshots and I tried to enlarge them as much as I can, but I'll kind of walk through these real quick. Can you guys still see me if I stand up here? Okay, yeah. Okay, so this is what it looks like to send data from our client application to Web3 storage via a Next.js API route. So I think pretty much, at least for me, my standard for building client applications is Next.js, and they have a really cool thing that they have these built-in API routes. So when you, as a developer, are writing and you want to say, all right, the data that I want to store in IPFS, aka off-chain data, this is exactly how you would send it. So you have a body that you define that's maybe gathered by user input, right? And then you just do, your classic kind of Next.js API thing where you say, okay, fetch this route, the method is post, and I'm sending in my body. Super easy. And then here's just kind of some error handling in case it doesn't go well. So the next thing is, how do you call the contract from your client? So in your client application, like aka your Next.js app, the thing that your users are looking at, that you see like the buttons and the events, how do you actually call the contract? So using WagMe, those are React hooks for Ethereum, and it makes it really easy by using this connect contract method. And then this is literally how you call a function. So the function from my contract is called create new event. So after creating my contract, all I do is I literally call the function create new event, and then I pass in the parameters, do some error handling, and then done. So now I've called a function on my smart contract from my client. Okay, and then here is the actual API route that's sending the data to IPFS. So in this slide, we're sending it from, createEvent.js, which is kind of like a form that you saw. Remember the form? So that's gathering everything in the body and then sending it to the API route. And then here is like, okay, this is how you actually store it and like persist it in IPFS. This is just some code that is from their docs. It's nothing really special. You kind of just copy and paste it from their docs. But here you'll see we're making sure that the request method is post. And then these are all literally stuff from their docs. So I'm passing in my body, and then the rest I got from their docs. So now that's done. Now, writing your subgraph to index and query events, so this is just a small part of it. There's more to it, but you'll see here we have something that handles a new RSVP. So these are resolvers. These are the resolvers I was talking about. So this handles our new RSVP, and then the second function handles the confirming of an attendee. So if you remember when we were creating an event, we asked for an event deposit. So you can set it to like 0.0005 Matic or something like that. And the idea of this is that if people don't show up, then you as the event organizer get to keep the money as kind of an incentive to make sure people actually are showing up to the events that they RSVP for. So the confirm attendee function is that mechanism to say, okay, you actually got here, I'm gonna confirm your presence so that you can get refunded. So this is part of the subgraph that handles that. I won't walk through the code, but these are the resolvers. It's only like maybe 10 or 15 lines for each one. Okay, cool. And then configuring the graph in your Apollo client file, super easy, 7 lines. You just are defining the URL for your subgraph, which for us, it's the graph/subgraph/web3 RSVP. And then how you actually make a query, how you actually fetch this data is by just using, like I said, a regular GraphQL query, where you can write it inside of your file, just like you would with regular GraphQL. You would save it maybe into a variable called data and then display that in your UI. Maybe you would map over it. If there's many events, you could map over this data, go to events, and then show a little box for each. That's what we did. And then, so Infura, how to configure Infura. In your app.js file, you literally, this is just straight from their docs. There's nothing kind of like unique about this, where we just set the Infura ID, which you get from your project dashboard. You configure your chains. For this specific project, we used Polygon Mumbai. We wanted to use a testnet. And then down here, we just defined the app name and the chains, which we defined earlier. And then again, configuring RainbowKit and WagMe. This is straight from their documentation. Nothing unique about this. So we just said we created the WagMe client, and then down in our app, we wrapped our app with Apollo provider, RainbowKit provider, and WagMe client, which is from their documentation. And then actually having the access to the Connect wallet button from RainbowKit is super easy. You just import Connect button from RainbowKit in any page of your application, so either in your index.js and then any other page as part of your app. And then how you use it is then you literally just use it as if it was a component built in. Super easy. Okay, cool. So that was kind of my, maybe I'll go back. I see someone taking a picture. Oh, you wanted this one? Okay. That was kind of my like practical crash course of how these actually communicate with each other. And now I have two quick starts. So this is a TypeScript front-end starter repo, which has RainbowKit, WagMe, Tailwind CSS, and a Next.js app already up and running. So all you have to do is fork this, clone this, npm install, and then you have something running. This is in TypeScript. And then there's this other one, which is in JavaScript that has a little bit more to it. So it has RainbowKit, WagMe, Tailwind, Next. It also has the graph and Web3 storage already built in. So you can look at the code and then just edit it based on what you're doing. So obviously I have, for this one, I have a lens subgraph just so you can see how you make a query. But now you know how to set it up. You can just change the URL, write your own query, and then your app will be up and running. So this is for JavaScript. And then a last thing, so for anyone who's still kind of like, maybe I don't feel quite ready to build a full stack dApp on my own, Women Build Web3, which is a DAO focused on high talent female engineering, female and non-binary engineers in Web3, created this open source course called 30 Days of Web3. It just launched last week, and there's over 3,000 developers taking this now. You can just go to 30daysofweb3.xyz, and here's kind of what people are saying about it, the T. And you don't really need to have coding experience. The goal of this course is not to teach you how to code. Like, we're not going to teach you how to map over an array, or we're not going to teach you how to write smart contracts. Really, the goal of this course is to give you an understanding of the architecture of Web3. So we give you the code, we walk you through everything, and then by the end of it, you'll have deployed a full stack decentralized application. And that's it. Thank you.
Awesome. Thank you all for coming out today. Really excited to be talking to you about Polygon. Today we're going to be talking about full stack dApp development on Polygon, and specifically how you can kind of use the overall Web3 ecosystem as different building blocks for building out like truly full stack, like robust applications. So a little bit about me. I'm Rahat. I'm a developer relations engineer at Polygon. Previously been a front-end engineer for a while, was a Solidity freelance engineer, and overall been an indie hacker / Web3 enthusiast. I've tried to build several failed startups. I can tell you everything I did wrong. I cannot tell you how to succeed because I've never done it myself. But you know, I can get you a little bit closer to there and tell you all the wrong things I did. These are some places you can find me. Always happy to chat, happy to go over any kind of like ideas that you have. If you want to bounce any ideas off or have any technical issues, always open to chat about that. So one thing that I kind of noticed as I was going through this specific presentation is that the title of this presentation might not be correct, and I'm not going to give you the title of the presentation just yet. We'll go through that later, but just to keep that in mind, although we're talking about full stack dApp development on Polygon, there is like a bigger kind of underlying message here that we're going to be building towards. So a little bit about Polygon. What is it? So Polygon is the leading platform for Ethereum scaling and infrastructure development. So we provide a whole bunch of different solutions for you to build on top of. L2 solutions, a lot of things on the ZK front that are coming up that I'll be talking a little bit about, as well as folks may already be aware of like our proof of stake blockchain, which is going to be one of the main focuses of our talk today. So calling those out again a little bit right here, proof of stake blockchain again, that's what we're going to be talking about today. One other solution that I really wanted to highlight today, though we're not going to go like fully deep into, is our ZK EVM, which we hope to release later in this quarter on like our testnet. So hopefully you'll be able to start building some test applications on that platform very, very soon. One of my favorite things about the ZK EVM is the fact that everything is EVM compatible. The Solidity that you may already know, that you're already building, will work. All you have to do is just deploy onto the ZK EVM. We did that just to make it easier for folks to like start, coming into the ZK realm, to make it compatible for dev shops who are already building in Solidity, who want to leverage the power of ZK proofs. So I will be talking a little bit more about that at Polygon Connect, so if you're going to be there, I really hope that we have more of a conversation on that there. Before I move on there, just also wanted to call out, like, we've got an entire suite of different solutions for scaling. We don't believe in just like a one-size-fits-all solution. There are different solutions for different use cases. So that's kind of what we're aiming for. We're trying to build use cases that make sense for you, for your specific, project, for your specific dApp. So what we're aiming to do is build that entire suite, so you can pick and choose what is actually useful for you to build out for your users. So building on the proof of stake chain, a few things to keep in mind as you're building on top of it. It is EVM compatible. Meaning you can leverage all of the tools that are currently available to you in the Ethereum ecosystem. If you've already been developing on Ethereum, you already know how to develop on Polygon. There's no difference in different things that you have to learn on like the technical level. All you have to do is switch your RPC endpoint of where you're deploying. Everything else just works one-to-one. A couple of differences, the token, which is the Matic token, all fees and interactions are paid on the blockchain with the Matic token. And rather than ETH, this is how you're kind of like paying those fees. It's accessible, very much like super low fees compared to Ethereum, and sustainable. The POS chain is carbon neutral, and Polygon as a whole is striving to go towards being carbon negative. So here's a little bit about the overall architecture of the proof of stake chain. At the bottom with those nice little purple blocks, you have the Matic sidechain. This is where you will be doing most of your interactions as a developer. This is where your users will be doing most of their interactions, where their wallet is going to be connected to. This is where most of the magic happens, right? You'll see up top, though, that everything is connected to the Ethereum mainnet. Specifically, we refer to the Ethereum mainnet as our root chain. In the middle, we have a layer called the plasma layer. What the plasma layer does is that it has these specific checkpoint nodes that are going to be looking periodically at the state of the Matic sidechain, and is going to be saving a hashed value of that to a smart contract that lives on the Ethereum mainnet. So a good way to think about this is like maybe you're playing a video game. Certain parts of the video game, you're saving your state so you can come back to it at a later point in time, right? That's essentially what the plasma checkpoint is doing. It's saving a hashed value of whatever the current state of the Matic sidechain is to Ethereum, giving you essentially the ability to inherit some security from Ethereum. Everything is backed up on Ethereum, and transforms this from just being just like the Matic sidechain into what's called a commit chain. So one thing that I mentioned during that whole spiel there was that POS is accessible. So I wanted to give you a little bit of an example of that. I have a little bit of code up here. This is a very bare bones smart contract on building your own ERC20 token. There's nothing fancy going on here. I believe I copy and pasted this from the Open Zeppelin documentation. So this is just creating a token called Gold Token. In the constructor, it just takes an initial supply for however many tokens you want to mint. Nothing fancy, right? Just mints a bunch of tokens. So a couple of lines, an import from Open Zeppelin. Here is me trying to deploy this using Remix. So Remix is an online IDE for quickly building out your own smart contracts. Once I tried to deploy it in my MetaMask, I see that the cost for me to actually deploy just, 2 or 3 lines of code is $76.42. Same thing now, except I've switched everything over to being on the Polygon mainnet. On Polygon mainnet, now this was about, we'll say a month and a half ago. It's about 0.0029 Matic to send this out. It's like a fraction of a penny. So you're going from 76 bucks to a fraction of a penny to deploy just 3 lines of code, right? So now imagine I'm actually trying to build something in production, an ERC20 token that has more functions, like I want to add things like a tax on transfer. I want to add like an allow list. Maybe this is part of an ICO. Maybe I have an additional contract for like an ICO. The more logic, the more state variables, everything I add, the higher the cost of this smart contract, right? Because storage is expensive. So if I were to go through this very, very quickly becomes expensive, beyond this like $76.42. So that is one of my favorite parts. One of the reasons I actually joined the Polygon team in the first place, when I was first learning about smart contract development myself, it was during the height of like the NFT craze when everyone was just like minting everything and all these gas wars were going on. I wrote a very, very sloppy smart contract. It was like the first one I ever wrote. And I was trying to be a hotshot and like put it out onto mainnet. And when I saw the cost, I said, never mind. So I wanted to go back to this point here. Building robust decentralized applications requires a combination of tools in the ecosystem. So I want to go over a bunch of the tools in the ecosystem that I like using for building out apps. So first, we have just a list of like your developer tools. Smart contract development can be done with a few different things. Hardhat and Truffle are very popular, especially if you come from like a JavaScript background. These are JavaScript-based tools. Brownie is a good framework if you're more of like a Python person. And then Foundry, relatively new, built with Rust, but it allows you to kind of like stick to your Solidity and not really care about anything else. Haven't done Foundry too much. I'm really excited about what that team is doing, so hopefully I'll be able to build a few things in that sense. Some front-end tools that I really like using, WagMe hooks. Although it's in beta, my personal opinion is it's one of the best tooling for front-end developers in the Web3 space, so definitely check them out. Rainbow Kit, which gives you an awesome UI for just like connecting not only to a MetaMask wallet, but you have to make sure when you're building out your front ends as part of your dApps that you're being as inclusive as possible to as many different users as you can. Rainbow Kit makes that very, very easy because out of the box you're able to connect not only to a MetaMask wallet, you're able to connect to mobile wallets, you're able to connect to Ledger hardware wallets, etc. All kind of like done for you very quickly without a lot of configuration. So Wallet Connect is also a good way to go about things and is one of the underlying parts of Rainbow Kit as well. Ethers.js is what WagMe hooks is kind of like built around, so I definitely recommend also checking that out. One thing I wanted to touch on, at least for a little bit, is security. We do not talk about security in smart contracts enough. And I mean, over the past couple days, weeks, you've probably seen some of the messes that occurred. So it's very, very, very important that you take security seriously when you're building smart contracts. The move fast and break things culture in startup world does not always work in Web3. When you move fast and you break things and you break people's money, people get mad. So it's very, very important to understand what tools are available to you as a developer on the security side of things. Some of the things that I like to use are Slither and Mithril. So Slither is one of my more kind of like favorite ones. It goes to kind of like does an analysis of your code and kind of like flags different potential security vulnerabilities. For example, maybe you have a reentrancy vulnerability in your smart contract when you're withdrawing funds. It'll be able to kind of like let you know, hey, there is potentially a vulnerability here, please look over this code. This alone is not going to be enough. It'll give you an idea of like where you kind of need to go, where you kind of need to look at for your code, but it is important to go beyond this a little bit and if you're going to be putting something out into production, especially something in the DeFi world, especially something that deals with people's money, to get your smart contracts audited by a third party. Slither will get you kind of like the base of like what you need, get you start thinking on like the security side of things, but it's very important before you go into production, you get things audited. So now I'm going to be talking about specific things that you do inside of your applications to make them a little bit more robust. First, reading data. It's really awesome that I got to go after Cami because I don't really have to explain the graph too much. So everything in Cami just explained about the graph is really helpful for like reading data. No matter what type of application you're building, you're going to need to read some sort of data from the blockchain. Reading data from the blockchain is not the best thing in the world, you don't want to be sitting there writing a whole bunch of like getter functions here and there until you get all the data that you need. The graph makes it super, super easy to like get a lot of that information indexed and sent over to you through a GraphQL API, just like Kenny mentioned right before me. So we'll move into like a little bit of file storage. File storage, there's a couple of different options. Filecoin or IPFS is a really good one, as well as Arweave. I've used Filecoin and IPFS specifically, their Web3 storage and their NFT storage projects. Those are really good, have generous free tiers for just like, putting up, like if you don't even want to like have anything to do with like uploading anything directly from your dApp, you can just like drag and drop, upload assets if you need marketing assets available or anything for like static websites. All of that can be done really quickly through Filecoin using like Web3 storage. Arweave, very similar, has a lot of really cool toolings in that sense. One of my favorite things in the Arweave ecosystem is Bundler. Bundler allows you to upload and keep like storage on the Arweave blockchain without the need for Arweave native tokens. You can even use Bundler and use Matic to actually pay for storage on the Arweave blockchain. So Bundler makes it really easy and accessible to use the Arweave blockchain. Definitely recommend checking that out for your storage needs. One thing I wanted to add on top of the storage side of things is a really cool protocol I've been like looking into called LIT protocol. So they provide decentralized access control for Web3, for apps, private data on the open web. So let's say you have some, some assets that you have put on like Filecoin or on Arweave, and you want to make sure that not everybody has access to it. LIT protocol can actually help you with encrypting it, making sure only specific people, maybe certain allowed users and their addresses can access to it, maybe certain people in specific like NFT groups. Maybe you're trying to make like an NFT gated blog or something like that. LIT protocol is really good for use cases like this and providing that level of access control. So now we kind of go into different like off-chain data protocols. Two of my favorites in this area are Ceramic and ThreadDB. Ceramic is doing a lot of really cool stuff in this sense where you can have like these different data streams and profiles, because like not everything needs to be saved on chain. Not everything should be saved on chain, but it should be saved in some type of decentralized manner. So I definitely recommend taking a look here. I really like Ceramic because they're also doing things in the sense of like improving on top of like different ways of doing sign-in with Ethereum, identity as well. So check out Ceramic for that type of thing. Now, one thing I wanted to stress is this is not a complete list. There are like tons and tons of protocols out there that are going to help you make it easier to build, actual robust decentralized applications. So definitely check out all of the new things that are kind of like always popping up. It's hard to keep track of things because I feel like every day on Twitter you see this new protocol with this new thing that you can do to add to your app, but you've got to like kind of like vet them to see like what's useful for you, what's useful specifically in the application that you're building. Now, what I want to mention here is like Web3 protocols, again, they're your building blocks. It's kind of like how you use them together to build that gets you to that eventual final state of like a full stack decentralized application. But what about the cherry on top? How can we tie everything together? We can use Polygon to supercharge your decentralized applications UX. And I'm going to go into what I mean about that. But I mentioned all these different protocols, all these different building blocks and tools. You can use them all together. You can use them all on top of your dApps that are built on Polygon. I want to show you this tweet from a while back from my friend Dennison. He is working at Tally, and this tweet always it was funny to me at first, but it resonated with me a lot. So he says that the biggest UX fail of Ethereum is gas. I absolutely know why it's necessary. Please, fam, I get it, I know. But regular people absolutely do not get it, they do not care, and they do not want to care. And they quite frankly hate it. So now we're in a bit of a conundrum, right? How do we get regular people who don't care about why you need gas, why you need this level of decentralization, to start using your applications? In comes something called gasless meta transactions. So I have a little bit of a diagram here. I'm sorry, I'm not the best person at these diagrams, but I wanted to first kind of take you through the flow of what a gasless meta transaction would look like. First thing would be doing something, and I'm going to break these down, so there's going to be further slides on each of these points. But the first thing you do with a gasless meta transaction is you sign a transaction using your wallet, using EIP 712 with structured signed data, and we're going to break that down a little bit further in a second. You take that signed data, you send it to a relayer, something like Open Zeppelin Defender or Biconomy. That relayer wraps the request into a transaction and sends it to that into the contract, right? But what happened before this relayer received that transaction? You, as a developer, might have loaded up that relayer with some Matic, right, to cover some potential gas fees that your users might incur. That relayer is going to take the inputs from your signed data as well as some loaded up Matic and send that transaction to the contract to be executed on the user's behalf. Now, let's say you're minting an NFT. You have an actual free minting NFT experience with someone who doesn't have to pay anything to mint, someone who doesn't have to pay any gas to mint. You now have the ability to onboard someone who is completely new to Web3 without them having to go to an exchange, buy some Matic, buy some tokens, make sure it's not a good user experience as much as we like to pretend it is. So let's break this down a little bit further. Signing, EIP 712. This builds off of the concept of don't trust, but verify. We verify that the user has access to their wallet because they're the ones signing specifically this cryptographic signature. You design some data structure on your front end, could be a JSON object or whatever, with specific inputs that whatever end function is being called needs. If you're using something like Ethers, the implementation is this signer.sign type data. This is in the Ethers documentation. You can take a look at how to build out this signature using that functionality. And from a JavaScript front end, this creates a signature and makes it ready to be sent to some HTTP endpoint for a relayer. So we're going back to Web 2. You're just sending a request to some endpoint using the relayer. Like I said, we're making an HTTP request to that relayer. Relayers can be loaded with funding for gas. Again, Open Zeppelin Defender, Biconomy, Ethereum Gas Station Network, all great options here. And we just make these requests we sign the data, make the request, it executes the contract on the transaction on our behalf. This is implemented by Lens protocol, and I think this is one of the best examples of how to use a full, robust, decentralized protocol without paying any gas. Because if you use any of the projects that are built on top of Lens protocol, like Lenster, et cetera, a lot of them are using Lens's GraphQL API. And the GraphQL API that they built uses a relayer. I believe it's on Biconomy. I'm not 100% sure. So that you don't have to pay any gas anytime you like a post, anytime you comment, anytime you make a post or whatever. Because all of these things change some state on the blockchain. All of these things, all of these interactions would use some level of gas. But now you don't need to do that. As a user, you don't need to care about that because we have the relayers acting on your behalf in the background. This improves your UX by a very, very large amount. People don't need to care, especially folks who are not native to Web3. Because if we're going to be going for mass adoption, we need to be building our decentralized applications in a way that is inviting to people who don't understand how this kind of works. And you don't have to do this for your entire application. If you think about like how certain software and everything works in the Web 2 world, you have like your 30-day free trials or something like that. That doesn't exist in Web 3. You don't have a free trial. You just have gas fees that you have to pay. Now all of a sudden, you don't have gas fees you have to pay. You can front run and like pay for at least your users at the beginning to like get used to how your applications work. They have a way to actually try your applications in a real production environment without having to spend any of their own money. This is economically viable on Polygon as a chain because of our incredibly low gas fees that I mentioned kind of at the beginning. We're a lot more of an accessible blockchain versus, imagine doing this on Ethereum mainnet, especially when there's like a huge NFT gas war going on, right? So what should the title of this talk actually be? Title of this talk should actually be Building Better User Experiences in Web3 on Polygon. That's what we really care about. We really care about making sure your users are able to benefit from your services, use your applications in a way that benefits you and benefits them. This entire ecosystem is built on folks like you, the builders, and the users who are using your applications. So we're aiming to make sure that the experience is as good as possible, and hopefully what you can take away from this is one way of doing that for your applications. So again, I'm Rahat, developer relation engineer at Polygon. A few places you can find me up here again. Really enjoyed talking to you all today, and thank you.
Hey everyone, it's very glad to be here and see so many people on this stage or the stage over there, and very excited to be here talking with developers or hackers about IPFS and Filecoin. So my name is Long Fei, and I work with Protocol Labs as a developer advocate for Filecoin and IPFS. So today I'm going to basically give a technical introduction about IPFS Filecoin. Basically, just trying to give enough knowledge and about how you're going to build application during the hackathon for on top of the IPFS and Filecoin. And so let's first talk about how everything gets started. So as I mentioned earlier, that I work with Protocol Labs. So Protocol Lab is an R&D team which is building open source toolings and services for the Web3 services. And the first protocol that we started building is IPFS. It's back in 2014, 2017. It's the peer-to-peer network and for sharing files over the distributed network. And then after that, we start building the Filecoin on top of IPFS. And it's a decentralized storage that we intended to store the valuable humanity data on Filecoin. Because Protocol Lab is more of the research and development team, so we need a Filecoin foundation to push forward the Filecoin community ecosystem growth and then the marketing. So that's all we're working together as the open source team for the IPFS and Filecoin. So the agenda today, I'm going to focus on first give a little bit introduction about what is Filecoin and what is IPFS. And because I know the hackathon is coming for the next couple of days, I'm going to talk a little bit about what's the current use case of our ecosystem and some of the possibilities and then the future plans for Filecoin and IPFS. Hopefully that will be some of the reference or inspiration for the hackers to know what you can build on top of IPFS and Filecoin. And obviously you need to know how to develop on top of it, like what tools you can use. And thanks for Polygon, thanks for Graph. They already introduced some of the NFT storage, Web3 storage, and ceramic. I mean, that's great. I like to see that all the projects are still building things together. That's good to see. And obviously, I'm going to talk about them a little bit later as well. And eventually, like we have a lot of events, a lot of hackathons going around globally. So if you're interested, and you can know more after you know about toolings or even after this hackathon. First, let's look at the IPFS. So what is IPFS? It's we call it interplanetary file system. So it's basically a peer-to-peer network that you can share and pass all the files across the, we said, interplanetary. But like why we say it's interplanetary? Because originally we all believe that we want to build a network that it will work, we'll upgrade the network that will work even when the web stretched across global. And that's what the team's vision and goals to build. And in nature that IPFS is designed as distributed, which means you don't need a central server and you don't need to download your files, download your website from a central server. So obviously it's going to be more resilient and there's no 404 anymore. So in order to understand how IPFS work and why IPFS is decentralized, so it's better to understand how to adding and getting a content over the IPFS network. So the process is different because on IPFS network, we're basically obtaining and getting a content by CID, so which is a content-based retrieval. And it's more of a resilient against what you can get is what exactly you want. So the process is first you upload your content to the IPFS network, and you obtain a unique ID, which we call a content ID. And then you will publish all this information, content, along with the content ID over the network. It will be stored into peers, DHT table, which we call distributed hash table in each peer. And eventually, when you're trying to download that data, DHT table is where you go to query how to get your content and where to get your content. So obviously, I've been talking about this peer ID a lot, and it's actually, I mean, the content ID a lot. It's an essential part of what we call content addressing. And IPFS is addressing your content by what it is instead of where it is. So if we think about like how we upload the content, how we retrieve the content currently in the Web2 world, so you will see first, let's look at if you're looking for the content on your computer locally, you basically go to a certain path in your C drive, whatever the drive, to look for the content. It's basically where you're storing that content. And it's the same thing for the Web 2. Like, think about if you go to the website, if you act downloading some content, obviously you go into the URL, and that's which server is storing your content. But you don't really know that your requested content is the same as what it was storing before. But with IPFS, it's different. We basically accessing the content by what it is. So you're passing the CID, which is a unique identifier for the content, and retrieving it. You don't really care where it's stored because in the distributed network, it could be stored in one or multiple nodes. So eventually, you will get exactly what you ask for by the content ID. So and then the content ID obviously is very important for content addressing. It's actually, you can think of as a unique cryptographic hashed fingerprint for your content. So because we say it's a fingerprint, it's unique. And whenever you want to retrieve the content, you can grab the original content and use the same cryptography hash function. You will get exactly the CID as you uploaded before, which means it's verifiable. If you have original content and if you retrieve it using that CID, you know and you can verify, is this what I'm requesting for from the IPFS network? And also in the peer-to-peer network, the peer is the essential part of the network that for nodes to be able to discover each other, to be able to share and then store the content across the network. So all this achieving by adding the different module to the peer. So for example, that it's because it's a peer-to-peer network, we have an essential part was lead P2P as part of the peer that handling the networking into all the peers in the whole peer-to-peer network. And also, I mentioned earlier that how to discover content and how to download content is actually achieved by the DHT table, which is also part of the feature of peer. And eventually, you need to download the content over the peer, which is achieved by the bit swap protocol in the IPFS peer. And then we're putting all this together in the IPFS peer, so to achieve the distributed file network. And I want to take a little bit of time to talk about DHT because it's very essential to store and then to discover content over the IPFS network. So DHT stands for Distributed Hash Table. And then it's actually essentially just a key value pair that's stored in each node or each peer. And you can associate it as a photo book. Then you can go and look at how you can connect to certain people and then like what the ID for that people. The difference is in the distributed network, every nodes maintain that DHT. And that will be used whenever you want to download data. So think about I said earlier that it's a key value pair in the table, and it's essentially just a peer ID and a content ID. So if you want to looking for content over the IPFS network, you need to do two things. First is you look into the DHT table and then find out who has. So you're looking for the content ID, and you find out who has this content ID. And then you are looking for the DHT table and see how do I connect to this peer ID. So essentially you will know where you can find your data and how to connect to the peer to get your data. So that's a very essential part of the content routing in the IPFS network. And the way that we use IPFS network now is very easy, but it's also very different. You can basically choose to use IPFS according to your own needs. So first, you can run your own nodes, host all your content, and then serve to your clients. But you have to maintain the infrastructure. You have to make sure that your IPFS node is keep running and then serving the content to your clients. And also, if you want to increase the usability and increase the efficiency of the IPFS network, you can run a IPFS cluster of nodes. But also maintaining the infrastructure will be a little bit challenging for the team. So for some of the team that you don't want to maintain the infrastructure, you don't want to making sure that all the nodes are running and connecting well, you can use the pinning service. What is pinning service is you can ping your file to the pinning service of the IPFS node. So they will make sure they serve your content over the network. But it also means that you need to rely on those pinning service. Or otherwise, you can just throw the content into the IPFS node and then hoping that your content is super popular and then everybody accessing it. So it will be expressed into the network and it's easy to retrieve. And these are the options that you can use IPFS. But because I mentioned earlier that you need to use all this or that, but it's not essentially very verifiable or reliable. But maybe we were wondering, is there any other options, like any alternatives that's more reliable and then verifiable? And that's Filecoin coming into the picture. So Filecoin is the storage network that we designed for Web3 and then for Web2. So essentially, we built Filecoin compatible with IPFS, and so it will be utilized the advantage of content addressing over the IPFS network. And we're also integrating Filecoin with a lot of the Web3 blockchains like Ethereum, Polygon, and Near, and we're also working with a lot of Web3 teams that you making Filecoin IPFS available if you're building your application with any of the stack into the Web3 world. And why is it different? Why is Filecoin different as IPFS? Is adding another layer onto IPFS, which is the crypto economy incentive for the storage providers in the Filecoin ecosystem, making sure that they're saving the content over the Filecoin network and it's be verifiable and reliable. And we're also growing Filecoin massively because now we're almost reaching like 18 gigabit of capacity across the network, which is huge, and then means we're ready for the massive adoption on the either Web2 world or Web3 worlds. So how it's different for Filecoin and IPFS to store content? Because in order to provide the verifiability over the Filecoin network, storing data on Filecoin is a little bit different as IPFS. So basically, the storage clients are making storage deals with miners or storage providers. So the storage provider has to make sure that they constantly saving the data, constantly providing the verification for the clients, so they will be ensure that data is safe and secure. All those is achieved first by storage provider needs to stake certain file token, which is filled as collateral, so they can be ensure to providing the verifiable and reliable storage. And then also, storage provider need to provide the proof, the cryptographic proof that they are storing the unique content, a copy of your data, which we call a proof of the replication. And then also over time, the storage provider need to be able to provide that they have been storing the content constantly over the time. And so they submit the proof of space-time to chain. So all these proofs are going to be recorded and be able to verify it over the Filecoin blockchain. So I've spent a little bit of time talking about what IPFS and Filecoin is. So IPFS essentially is a protocol to share your files and your data across the distributed network. And it could be work with any distributed network, any like storage network. Obviously, Filecoin is going to be the best match with using with IPFS and Filecoin. So you can take advantage of the faster retrieval over the IPFS, and then you also be able to use the advantage of long-term persistent and the verifiability storage on the Filecoin network. So by saying that, I will highly recommend all the hackers, developers, if you're building during this hackathon, use IPFS and Filecoin together, then you'll be able to take the full advantage of the features, the features from both protocols. And I'm going to introduce some of the tools that you can use without actually touching the IPFS and Filecoin, but be able to store your data over the two networks. All right. So next, I'm going to go through a little bit of an ecosystem use case. Hopefully, that's going to be some inspiration for the hackers to know what you can build over the Filecoin IPFS network. Let's look at the picture first. And then we have a growing, very fast ecosystem around IPFS, and a lot of different projects are building on it. For example, the web hosting services and the NFT and gaming metaverse, and also some of the content creation are created over the IPFS network. Also, Filecoin network is also growing very strong. And we have a lot of data set onboarded on Filecoin, either through the Web3 applications or Web2 data set. So for example, in Web3 applications, there are like NFT platform and content live streaming and music platform are built on Filecoin. And then for the Web2, and there are a lot of the enterprise company, they are storing their large data set on Filecoin. And I will give a little bit introduction later on the slides. So overall, that Filecoin storage has been growing for Web3 and the Web2 worlds. I will just go through a couple of the use case. For example, that obviously NFT and gaming, metaverse are growing super strong over the Filecoin and IPFS network. And we have a lot of application building on top of it. For example, Mona is building a marketplace for the 3D artwork. And OP Games, it's a gaming platform. They're building the gaming community to bring all the game builders or gamers together, so to explore more opportunity and a more interesting game. Metaverse AI, so they're using the AI technology to bring the VR and then to bring all the metaverse together to the users. And also, obviously, NFT marketplace and NFT content creation, as well as some of the NFT infrastructures or toolings to make NFT developers easier, are all building on top of the IPFS and Filecoin. And apart from NFTs, there are also a lot of other content creation platform. They're storing the data on Filecoin and IPFS. Hadoop 01 is one of the live streaming conference that are using IPFS and Filecoin, and also a couple of the platform that's like live streaming music and the music sharing platform are also building on IPFS and Filecoin. Also, FM is storing the videos and everything on IPFS and Filecoin. These are the use case that you can use to take the Filecoin IPFS as decentralized storage. Also, I mentioned earlier that not just Web3, but a lot of Web2 companies are storing the data on the Filecoin network for the long-term and safer verifiable storage. And for example, Internet Archive, they are storing and backing up the data for the website, public website, and documentations on Filecoin, so to be able to provide to the public access. And then Zora is also storing their climate data on Filecoin, so it would provide it to the researchers to access. And also the Seoul Foundation is storing the testimony data over the Filecoin. All this are data set, and then we also have more use case that I didn't put it on top of. For example, that we are working with New York City Public Data to store the data on, back up the data on Filecoin as well. So all this are example of Web 2 of use case, or as well as Web 3 use case. But apart from the use cases, I want to also talk about some of the social goods initiatives that from Filecoin that I think is very, very important, because it's going to essentially bring a huge impact into like Web3 or maybe our society in general. Filecoin Plus is the program that incentive that we're storing the valuable and on Filecoin. So here, because Filecoin is incentive a storage provider to verify, to accept the valuable data sets for humanity on Filecoin. So we give them 10 times of the possibility to claim rewards to get the block reward from Filecoin storage provider. And also it has the console to constantly verify and ensure that your valuable data are storing on Filecoin Plus. And another very interesting and program that I'm very excited about is Filecoin Green. Filecoin Green is the initiative that's trying to make a Filecoin blockchain as carbon neutral, maybe eventually carbon negative. So Filecoin Green has this kind of a Filecoin energy dashboard that will display all the electricity consumption from all the storage providers over the Filecoin network. So we bring up the bar that make it transparent for all the storage providers, all the miners in the network about the electricity consumption. And besides that, Filecoin Green is also partnering with storage providers as well as the renewable energy company, because we're trying to encourage the storage provider from Filecoin network to use more of the renewable energy instead of like electricity and everything. So essentially, Filecoin Green program is trying to make Filecoin as sustainable as possible. And I also, because we have a lot of hackers and developers here, I also want to talk about what's coming next for Filecoin. And then essentially Filecoin is building the foundation for decentralized internet. We're achieving that by making the 4 key components. The first obviously is providing the verifiable storage. And we have been doing that since the mainnet launch, and then we're reaching to the 18 gigabyte of storage, which is already massive. And then the second is retrieval. Because the team is trying to building and then providing the CDN quality retrieval market over the network. And currently we have a Saturn network is already launched the testnet. And I think programmability over the Filecoin is the most looking forward features that over Filecoin. And I will talk about next slides. And eventually is the computation of the Filecoin, and the team is working on that as well. So this is the most important part that Filecoin team is keep building and working on. So I will just focus on the FVM a little bit here, because it's one of the most looking forward features on Filecoin network. So essentially that FVM is going to bring the programmability to Filecoin network. So either with the EVM compatible smart contract development or a native Filecoin smart contract system. So eventually Filecoin storage providers, Filecoin developers can build everything on top of the Filecoin with storage, with smart contract, with computations over the data. All this is going to become possible over the Filecoin. So the team behind it, our core team, is actually splitting the development process into different milestones. And recently we released the first milestone, which will give the Filecoin node the ability to run our native actor, which is smart contract over the FVM. And by the Q3 of this year, the FVM will bring the ability of writing the EVM compatible smart contract and deploying to the Filecoin network. And by the Q4 or maybe early next year, we will have the ability to support both EVM compatible smart contract as well as native Filecoin smart contract. So I think those FVM is the most exciting things that are happening in the Filecoin ecosystem, and all the partners, all the ecosystem are looking for it. So stay tuned, and I think by Q3 you'll be able to try smart contract on Filecoin. All right. I hope all those use case and all the initiatives that we're doing will give you guys enough information on how or what you can build on top of IPFS Filecoin. And if you need more inspirations, you can also check our website, Hackathon website, hackathon.filecoin.io, to look at there's a part we call a Hall of Fame. It's all the winners from the past hackathon. And then you can get more inspirations on what they are building and what's the whole ecosystem of building on Filecoin and IPFS. So we know what we can build. I think it's time to look at how we can build on top of the IPFS Filecoin. Then I'm going to talk about some of the toolings. I think you probably already heard a lot of like NFT storage, Web3 storage, and I'm going to cover it here. So basically, there are many ways to use IPFS Filecoin. For example, you can directly communicate with IPFS node and as well as Filecoin nodes. But those will require you have a deeper knowledge about IPFS Filecoin and how to communicate with them over the APIs. But there are also other options that you can use is the storage helper, what we call storage service. Storage helper and the storage service will give you the ability of use IPFS and Filecoin just over the single core to store your data on both network. So IPFS, you can get the faster and the flexible retrieval, and then using Filecoin, you will get long-term verifiable storage. So I would highly recommend hackers or developers are building for this hackathon, trying to get to know some of the storage helpers instead of going directly into Filecoin and IPFS nodes. So let's look at a couple of them. The first I will introduce is Fleek hosting. Fleek hosting is a decentralized way to host your website, so you can fully make your application, your website, go decentralized. So you can think of it as a CI/CD tool, and then it's super easy and simple to use. So if you deploy your website in the Web2 world, use Vercel and other platform, you will be able to use Fleek hosting very easily. But the difference is Fleek hosts their website on IPFS, so it's completely decentralized. And then the process of using it is very similar as Vercel. Basically, you just connect to your code and then adding some configurations, and eventually, if you have any push, they will deploy to IPFS immediately. And then Web3 storage. I guess you guys already heard about Web storage a couple of times. And Web3 storage is building on top of both IPFS and the Filecoin. And it's giving you the ability to use the decentralized service. And it was very fast and then very good UI UX, as Polygon mentioned, that UX is very important. So it's super easy to use, and you basically just integrate either JavaScript library or Go library into application. And then you'll be able to use the APIs, simple code, like for example, Web3 storage .store, and then putting your files in there, it will automatically store your file on IPFS and Filecoin. And if you are building an NFT, and NFT storage is the best option to go. It's the free service that you can use currently thanks to the Filecoin Plus program. And it's also storing your content and your NFT asset over the Filecoin and MPFS network. What is different as Web3 storage is it takes care of all the dirty works to upload your content on the IPFS and also creating the metadata compatible with ERC 721 or ERC 1155. So you will be able to use single core to upload your asset to IPFS and Filecoin network and getting your metadata, which you will store in the smart contract. And also, NFT storage provide the fast speed of a gateway. So then you retrieve you'll be able to use that gateway to retrieve your NFT way faster than any other NFT gateways. I mean, another IPFS gateways. Currently, we have a lot of data, a lot of NFTs stored over NFT storage, already over 60 million. And then NFT storage are being used by a lot of projects like if you mint your NFT on OpenSea, all the data of the NFT will save to IPFS Filecoin automatically through the NFT storage. And also like Magic Eden and a lot of the NFT platform like Metaplex on Solana is also using NFT storage to store the data. So if you're building an NFT application, you can look up on NFT storage. And if you are developers that are looking for more flexibility, more control over your nodes, over IPFS selection or Filecoin storage provider selection, you can try PowerGate. PowerGate is more developer friendly, and then it's essentially a Docker image which bring the IPFS and Filecoin node together. But instead of wrapping around the service, it also gave developers the options to configure the network. For example, like which storage provider I want to use, how many copies I want to store on IPFS and Filecoin, and then when do I want to renew my storage deals on Filecoin. All this can be configured through PowerGate. But with NFT storage and Web3 storage, you're losing those flexibility because they will take care of you. But if you want to have your own control of the storage deals and then storage over the IPFS, PowerGate is the option to go. And apart from that, we have other tools like Astray is also building on top of IPFS Filecoin, but it's meant for more meaningful data because they will verify your usage and making sure that you store a meaningful data on IPFS Filecoin. So if you want to use a decentralized database, you can go with the OrbitDB. OrbitDB is a key value pair database built on top of IPFS to provide a peer-to-peer decentralized database. But if you're looking for more complex, more structured and a relational database, you can try with the Tableland. Tableland will provide the relational and the highly structured database on IPFS and Filecoin, and also it's going to be used EVM compatible layer 1, layer 2 smart contract to record everything. And also Ceramic that Polygon also just mentioned earlier that you can have ID and then computation data if you want trying to use Ceramic. And I think those are the tools that I want to introduce, and I highly recommend all the hackers and developers to use to build on top of the IPFS Filecoin during like a couple of days of the hackathon. And if you want to keep learning or keep building after the hackathon, we have you can check our Slack or Discord and then go to the website of IPFS.io and then Filecoin.io to look at the document. And we also have a protocol school which will dive a little bit deeper on different knowledge like how P2P work and how content addressing, how DHT table work. And also if you want to learn more about NFT, we also have NFT school giving you basic information, knowledge about NFT and how to mint NFT on different blockchain. And if you want to keep building, and you can look up at our website, hackathon.filecoin.io. We are sponsoring a lot of the hackathon cross globally, and now we are here with ETH Seoul. And at the same time, we have like Infinity Hackathon happening in Singapore, and we just finished a great hackathon with HackFS. If you're interested in building with Filecoin and IPFS, definitely go check out the hackathon website. And we have a lot of exciting events are coming up. All right, thank you very much. I'm very glad to be here, and hope you guys have a great building during the hackathon. Thank you.
on this mic, huh? Okay. Yeah. Okay. Hi, everyone. My name is Nicholas Kunkel. I'm from MakerDAO, and I'm the Oracle's core unit facilitator. I want to talk to you guys today about something I came up with called community consortiums. And like everything else in the space, right, there's something familiar, but they're also different. And I think the way that they're different makes them fundamentally different to what they're based off of. And I think the way that I want to do this is I kind of want to start with 3 stories. So I want to tell you about like 3 different kind of scenarios that come up in crypto a lot. There's certainly other ones, and you know, we could be up here all day and talk about dozens of different ones, but these 3 are just kind of examples. And so as I'm talking about these 3 stories, I want you to kind of think about what are the underlying trust assumptions that are happening in each of these stories. So, story number 1. Imagine a blockchain that has validators. And these validators decide, you know, which transactions are included in a block. The validators, you know, decide and reach consensus on if a block is valid or invalid. And the nodes on this network, you know, decide what is the canonical chain by looking at the chain which has the most blocks. Right, so this is known as like a Nakamoto kind of longest chain rule. Okay, story number 2. You have a oracle, right? So the oracles are, right, the way that you get data off-chain, right, on-chain, right? Typically, right, you see this in DeFi, right, where an oracle, you know, represents the price of some kind of asset, right? So if you're a DeFi protocol and you're generating loans, right, you need to know what is the value of the collateral so you can make sure that the loan is sufficiently collateralized, right? So how does that oracle work, right? Well, typically there's some kind of price kind of submitter, right? So someone who submits the price, right? And typically it's not even like one person submitting the price, right? It's a group, right? And we say that this is some kind of like distributed consensus, right? Oh, we have 20 people, we have 30 people, right? You know, submitting this price, right? And we take, I don't know, the median, or we take the average, right? Or we do some kind of outlier analysis, or we take a TWAP, right? But the point is, there's a group, and it reaches some kind of consensus around what a price is. And then story number 3, think of a DAO. So a DAO that, you know, with your token, right, you can vote, but the vote is a snapshot vote, right? And these are very popular, right, because they don't require, right, you know, users to pay transaction fees, and we think this is very, very inclusive, right, because no one is, blocked out from participating in governance, right? We've removed all the cost barriers to participating in governance. So the token holders, right, they vote on governance proposals via the snapshot vote. And then typically, you have a developer team, right, that has some kind of multisig, and they then execute the transactions that were, represent the proposals that were ratified by these snapshot governance votes, right? But it's important to note here, right, it's the multisig, right, that has control of the smart contracts, right? And so today I want to convince you of of three different things. The first is I want to convince you that from all these three stories I just told you, they're exactly the same. They're not different in the slightest. They work on the exact same mechanism. Second thing I want to convince you is that this is absolutely terrible, and we need to, we can't keep doing this. I mean, this is, in light of recent events, which we'll talk about later, right, it's just showing flaws and cracks, and we can do so much better. And then the third thing I want to convince you is that, well, actually, it's not that bad. It's just being misused. And that if you use it in a different way, it actually becomes a really, really powerful primitive that not only is not that bad, but like you actually do want to use it because it's so useful. So, first thing I want to convince you of, everything is a multisig. And as soon as you accept this great truth into your life, you start to see them everywhere. So every application you look at, every mechanism design is around this multi-sig type of concept, right? In the blockchain story, right? You have a bunch of validators and some subset of these validators, right? A subset of the signatories of a multi-sig are reaching some kind of decision, are reaching consensus, right? In the Oracle story, you have some subset of this, signatory set that we call the price submitters, and they decide that, this subset decides this is the price, right? In the last story, right, you have a multi-sig, right, that's actually has all the administrative authority over this crypto protocol, right, that's executing all of these state changes, right? It's literally a multi-sig. And so you see this mechanism everywhere, right? And I mean, this is just, what the hell are we doing, right? This goes kind of against the entire ethos of crypto. And like, what is the ethos of crypto? Like, the ethos of crypto is that, look, we have this incredibly useful, decentralized, neutral platform to build on top of, and we have the ability to make trustless applications, right? This idea that code is law, right? And users don't have to trust external parties, right? You just trust the code as written, right? And we believe that we can get this kind of mechanical, deterministic behavior, right? And then what do? We don't do that, right? Like, the whole reason for crypto in the first place, right? The whole reason that Satoshi Nakamoto even came up with, right, Nakamoto consensus was exactly because of the 2008 financial crisis, right? And what happened? Well, there was our public institutions failed us, our private institutions failed us, there was a breach of trust, and we ended up bailing out all of these institutions, right? It's fundamentally unfair. And so then we look at crypto, right, and we tell ourselves, right, that no, right, the reason we're building is because so we don't have to trust institutions like that, right? The reason we're building is so we can get rid of this trust component. And then you look at events that happened recently, right, and you realize we're exactly the thing that we despise, right? We saw recently, right, a bunch of the CDFI kind of platforms failing, right? The collapse of UST kind of triggered a bunch of these CDFI lenders, to go insolvent, right? So you look at something like Celsius, right? Celsius promised its users, right, that, hey, you can deposit your tokens with us, and we'll give you some yield, and we're not doing anything risky, we're being super safe, right, and we're giving you the yield. What was Celsius doing, right? They were engaging in extremely risky investment activities unbeknownst to their users. You look at, and this is not unique to Celsius, right? You look at Voyager, same exact thing. You look at BlockFi, same exact thing. You look at Nexo, same exact thing. They were all essentially participating in this fraud, right? And they all brand themselves as we are crypto native institutions, but no, they're the exact parallel of these fraudulent traditional finance institutions, right? That we say, you know, that we're different, but we're really not. And what happened, right? Well, Celsius went bankrupt, but you look at some of the other ones, and you're like, oh well, you know, they're still around. Well, what happened? Well, FTX bailed them out, right? FTX extended them hundreds of millions of dollars in credit, so they would have the liquidity to withstand a bank run, right? Without that bailout, without this, you know, repeat of exactly what happened in 2008, all of those institutions would have gone under. They would have needed to, in the bankruptcy proceedings, they would have needed to liquidate all of those holdings to pay back their creditors. And, you know, if you want to imagine what that means to have billions of dollars of crypto just kind of dumped on the market, like it means a bloodbath, right? It's like financial Armageddon. So, you know, Satoshi Nakamoto is probably rolling around in his grave, like watching this unfold, right? So, I've probably, you know, made things sound pretty bad, right? Like I'm here like a doomsayer, like preaching in front of you that things are terrible and we suck and we should all be very ashamed of ourselves. But I want to introduce you to this concept of community consortiums. And when I explain it to you, like, you're going to be like, this is so simple. It's really stupid. Like, this is not novel at all. But it's still really powerful. So imagine this multi-sig, right? And so when it's a small multi-sig, or when the number of signatories, when the number of validators, when the number of price submitters, right, is small, you have the centralization of power, right? You have, from a mechanism point of view, right, you've inserted this trust element. But I want to make the case that there is an inflection point, that once this signatory set, once this validator set, once this price submitter set becomes sufficiently large, that instead of being a trust adding mechanism, it's actually a trust reducing mechanism. And so the reason why I call it a community consortium is because essentially you want to onboard everyone in the community, every possible stakeholder, in order to reach consensus, and have this consensus essentially be a public good. And what you do at this point is any kind of application that is dependent on this community consensus, you're essentially betting on the industry not to decide to murder itself, which I think you'll find is a bit of a ludicrous, right, assumption. So I want to kind of briefly go into like how we're using community consortiums at Maker today, and then how we kind of want to develop them in the future, and then how all of you can be a part of this, right, and help kind of secure our applications and secure our ecosystem and secure our communities and secure our tokens. So Maker's oracles today work based on a community consortium. So I don't know if you've ever like thought of this, like, so if you're using DAI or using Maker, right, what are you trusting right now? You are trusting a community consortium. And I'll kind of go, in a little bit, I'll kind of go into like who exactly is in that consortium and who are you trusting, but you are trusting a consortium for all of the oracle prices in Maker. Later this month, we're going to be releasing what we call Maker Teleport. Maker Teleport is essentially a bridge from any chain to any chain. And so essentially, what do you need here? Well, if a user wants to, say, transfer their DAI from Ethereum to Optimism, right, you need to have some kind of consensus that something happened on one chain, right, so you can affect some kind of action on another chain, right? So if a user burns their DAI on Ethereum, right, there needs to be some validator consensus that then tells, Maker on Optimism, hey, give this user, some new freshly minted DAI, right? If someone on Starknet, right, wants to transfer DAI to Arbitrum, right, you need consensus that some event happened on Starknet, right, that a user burned their tokens, right, in order to then trigger the minting of the DAI on the other chain. And kind of what's really cool about this mechanism is it actually, and kind of what makes this bridge unique versus other bridges, is one, it uses the same community consortium consensus as the oracles that Maker uses. So there's no extra trust assumptions that you're making, right? There's no compounding trust assumptions. It's just the same exact trust assumption that already exists today. But more importantly, this lets you kind of avoid this 1 week kind of exit delay that you have when it comes to rollups, right? So if you're like, if you have some ETH or, some tokens on Optimism or on Arbitrum or on Starknet, right? When you try to exit, that chain, right? There is a dispute period, right? That has to happen, right? And typically, I think this is 1 week, right? But that parameter is kind of dynamic, right? And in that 1 week, if there was any kind of fraud, right? Someone is supposed to be able to submit a fraud proof on layer 1, right? Asserting that, this transaction is fraudulent. And that's why you have to wait this 1 week period. But what you can really do is essentially, because Maker has the ability to mint DAI, what Maker can do is essentially underwrite that risk if it knows the transaction is not fraudulent. So you can, if a user wants to withdraw, say some DAI off of Optimism, okay, normally they'd have to wait a week, but instead what they can do is the community consortium can look at that transaction that happened on Optimism. It can run the transaction on its own and verify, each individual in the community consortium can verify, hey, yeah, that transaction is legit. And then once you have enough of consensus reached, right, that this is a legitimate transaction, right, Maker can just go ahead and mint you the DAI on the other chain that you want to exit to. And essentially what you're doing then is after the 1 week delay, Maker gets the actual DAI, right, that you exited, right, from that 1 week challenge period, right, and then we destroy it, right, so the accounting nets out to zero. So it's like a really interesting way, I think, to avoid some of the UX challenges of roll-up chains, while not actually giving any additional risk or any additional types of fees to the user, right? It's just Maker underwriting this risk, right, that the transaction is fraudulent, right? And like I said before, right, there's no additional trust assumptions that Maker is making, right? So if the community consortium is corrupt, right, Maker was already screwed to begin with. So, what is this community consortium that I've been talking about, right? I've been talking about it in abstract terms, right, as this nebulous kind of group, but who is it today? So it's all of the ones that you see up there. This community consortium is not new. We have had this effectively since the launch of multi-collateral DAI, which was about, what, 2.5 years ago at this point, right? So big thank you to all of like the OG partners, right, that are part of this consortium. But this is not good enough, right? I talked about at the beginning, right, this theoretical inflection point of like, oh, you have a small validator set, right? This sucks. This is just a multi-sig versus you have an extremely large validator set. Right now, it's a community consortium. This is not yet a community consortium. This is not representative of enough of the stakeholders in this industry. Like, to build an actual community consortium, which I don't think a single one exists yet today, you really need to get everyone, right? You need to get everyone's reputation. It's almost like staking your reputation, right, as a protocol, right? To participate in a community consortium and then to, you know, potentially, right, commit some kind of malicious action, right, that reflects on you as a protocol, right? But even more so, right, the challenge of getting a getting consensus around a malicious action becomes a coordination problem, right? It's how many people in this validator set can you convince to be malicious with you? And I would argue that if you can get every single reputable protocol, every single reputable stakeholder in the ecosystem to be a part of the community, like the community consortium, you will never be able to get the community to turn on itself, right? And it ends up becoming this flywheel, right? The more places that uses the community consortium for their consensus needs, right? And the more of even the users of the community consortium are part of the validator set in the community consortium, right? You just have this compounding flywheel effect. And that's what I'm kind of here today for, is I want to convince all of you to join this community consortium. I want you to help not just secure Maker, but I want you to help secure the entire ecosystem. So we can get away from these flimsy architectures that are based on multisigs and get towards this, and I know this sounds a bit utopian, but bear with me, right? Almost like a community-owned public utilities, right? That are powered by community consensus. So, if what I said today interests you and you want to join the MakerDAO consortium, I would love to talk to you. Come find me here, or you can reach me on any of these socials, on Twitter, Telegram, shoot me an email. Also, if you're interested in working with Maker, we're always hiring talented individuals. It doesn't matter what you do, we just want the best people. So if that's of interest, please come find me, come hit me up. Let's talk. Awesome. Thank you very much.
I think I got it. Okay. You can hear? Yep. All the way in the back? You can hear? Okay, cool. Hello, my name is Graham. I'm the CTO of Mira. You might know me on Twitter, Strange Chances. I'm curious to know who here knows Mira.xyz. Maybe you've seen a link or something. Okay, cool, a fair amount. It's really important to know because I don't know whether to do like a super intro or to go into something more technical. So what is Mira.xyz? It's a Web3 publishing platform. it's become one of the main places where people make announcements in Web3. So we have examples like Optimism presenting next. They described their token on Mira. They did the announcements for that. We have a lot of pretty famous and well-known writers in the space, like Polinia. He talks a lot about L2s and Ethereum in general and blockchain technology. Chase Chapman. We also have investors like Chris Dixon and some other pretty well-known people blogging on Mira. So what makes it Web3? I said it's a Web3 publishing platform, and there are a few things. So for one, writers log in with their Ethereum accounts. And we view the Ethereum account as the primary identity of the internet, of the new web. That means we don't use login with email and password. So if you use something like Medium or Substack or Naver here, for example, you're going to log in with an email and password, and we just think that the Ethereum account is the new identity of the internet, and you're going to log in with that instead. And I think that that is something that's very surprising to a lot of people who are new to the space, who view the crypto wallet just as something that holds cryptocurrencies and maybe NFTs. But we're actually seeing all these non-financial use cases where people are logging in with their Ethereum account, and they're using it for things like messaging, signing content, verification of identity, and that's actually going to be very important. The same private key that you used for doing financial transactions, you can actually use to verify content and social messages, and that's really important. So we're going to play this video here, and this is going to be, in lieu of giving a demo, it's just going to be a video of signing in to Mira, and I'm going to show you some of the basic features. So if we could play the video. Yeah. Okay, cool. This is the Mira XYZ homepage. Or I should say it was. As of this morning, we updated it, so rugged. But it basically looks like this. We have some projects that have written things on Mira. And if you go through, you'll see, you know, ENS, for example, announcing their token, and a bunch of thought leadership pieces on Mira as well. And if we click into this, you can see, it looks like a blogging platform, and it's, what you kind of typically would expect from something like a Medium. It, has a nice title, etc. But then there are some other things as well that you'll be able to see that are really interesting. So for example, you can embed blocks, like Web3 blocks. For example, NFTs, you can just embed in. We've had people embed things like crowd funds, etc. If you click on the byline, the user identity of the post, you'll see it's an Ethereum address, and it links to Etherscan. And so you can start to see the interoperability between other platforms. And so that's sort of like the social network of Ethereum itself is based on the address as the primary identity, and that's something that is, just front and center of the authorship experience on Mira. Here you can see Brantley.eth. This person wrote this post with their ENS address linked, and they wrote about ENS, and they were a prominent figure in the ENS community. And that form of identity and authorship is a lot more trustworthy than something like an email and password login. If ENS were to do this post on Medium, how would you really know that it's ENS? Because you can't tie it to an address, and you can't verify signatures. And so you want something like this, where the content is very valuable, to look a little bit more like financial transactions than just a blog post that's hosted anywhere. Okay, so here I'm showing you signing in. You can sign in with Wallet Connect, MetaMask, Coinbase Wallet, and it's pretty easy, what you'd expect. Here, you're signing a message that is generating a token for you to basically use to authenticate on the website. And from here, you'll be able to, this is my account, so these are some of the posts I've written, and you'll be able to edit these or create new entries or update your settings. And every time you do any of these actions, you'll be signing the action with your private key. And so any change that you make on Mira is tied to a verifiable signature that anyone can go and verify. Yes, this person did mean to post this from this account. They wanted to change their settings, and so on. And so we'll be able to decentralize all of that content because it's always verifiable. You don't have to trust our website. You don't have to trust our database. So, as I said, the Ethereum address can sign messages, and then all the content is signed with the address and is verifiable through the signature, and then gets stored forever on a decentralized file storage system. So we are using Arweave at the moment, and we put a link to the bottom of every post to an externally hosted copy of all of the content, including the signatures from the author. So why is this so important? It means that the posts will always be available, even if Mirror goes away. The authorship can always be proven from the account signatures. And so once something is published on Mirror, we don't have ownership over the content. And the writer can always rebuild their publication from that externally hosted content and the signatures, and would be able to validate that that indeed was what they meant to say and what they were posting at the time. This is just simply not true of Web 2 platforms. So if Twitter bans an account, or if it goes out of business, then the authors lose all of their data. And that's something that's happened quite a lot. It often happens in political contexts. For example, the President of the United States, the previous president, was banned from Twitter and then lost all of their data. And there was no way to rebuild his account. And that happens quite frequently with lesser known examples as well. And I think you should also consider cases where people will post from a Twitter account, but it's not really the person you think it is. And one example I have is the CEO of Twitter, Jeff Dorsey, once had his Twitter account hacked, and people posted things from his profile that he didn't actually say. It was somebody else who had hacked into his account. And so that sort of thing wouldn't happen if it was private key based. You might still have hacking, but the security guarantees are probably better. So in total, we don't believe that the platform should have ownership over the user's creative work. And here's another video we're going to play of the optimism post. And I just want you to think a little bit about what I've been talking about in light of this post, which is so important. It was Optimism, which is one of the most important projects in the space, announcing their governance model and their token, introducing the Optimism Collective. And when you think of all these things, like being able to rebuild the publication, being able to have that content decentralized and stored forever, and have all of the provenance of the signatures available, that becomes so important when you think about these historical documents that are starting to be generated in the Web3 space. So we want to use these new technologies to do important things, and I think that this is one of these cases. So this is optimism, you guys. Okay. So as I said, at the bottom of every entry, there's a link to a Arweave transaction, and we call this the nutrition label of the post. So it's going to basically show you where that file is stored on Arweave. And so here we have a link to the content, and anybody can go and view this. This is not a Mirror website. This is external, and all of the content here is hosted externally. So this is a big JSON file that has all of the content in Markdown, and also includes all of the authorship information that you would need to verify the authenticity of the post. So it has, signing key, signature, the type of signature that was used, and so on, as well as some information about on-chain data, which I'll touch on in a minute. Okay, this is the Mirror development blog. So this is where we just give updates about things that we're working on here, introducing subscriptions, etc. And I wanted to show you that we wrote a post about how to retrieve the posts directly from Arweave. So you can just very easily use the Arweave GraphQL endpoint to go and pull this data, which means that it's permissionless for people to go and build on top of this publishing platform, this protocol. They can just use JavaScript SDK. The code is very simple. They can go and pull all of their data. And so if at any point a person wants to grow out of the Mirror network and wants to go and build their own front end, they can do that very easily just with this SDK. Okay. So we also focus on making an excellent user experience, and we think that this just makes it easier for anyone to start publishing in Web3, even if they don't understand complicated topics like DeFi. Not everybody wants to be a trader or do speculative things in the space. So if we really want to have mainstream adoption, we can not only have things like NFTs and cryptocurrencies. On Mirror, all you need to do is have a wallet to log in with, and you can start publishing. So I think that this makes Mirror an excellent place for people to start having a voice in Web3. If you want to do things like governance and political things, you need to start having citizenship, and I think that that starts with people having a voice in Web3. And Mirror is a good place to start because it's free to use. All you need is a wallet to log in. And there's always going to be a clear way to exit from Mirror if you prefer something else. Right? Okay. So I'm going to get into some other features. We're going to play another video. Yeah. Next time, live demo. This time, video. Okay. So I'm just going to show you for a second here about just making it a good user experience. We focus a lot on making it pretty similar to a Web 2 experience. So what does that mean? It just means that the things that people are used to doing for a publishing platform, they should be able to do on Mirror. It should be very easy to create an entry. It should look nice and user-friendly. You should be able to, drag and drop images to create the cover image. It should have good SEO. And all of those things, we focus on and we take very seriously. So we're not merely a protocol company that's highly focused on just the abstract technicals. We think about the product a lot and we invest a lot in design. So all these things that you would expect from an editor are there. But then we also have these extra things. So you saw, blocks, you can embed things like edition sales. So you can actually sell NFTs like from a blog post. You can create a story, and then at the end you would embed a crowdfund or something like that. So it blurs this line of funding and publishing. Here's an NFT embed, so you can do things like that too. If you have an NFT on Zora or Foundation, you can just embed it into your post, really user-friendly, and then people can interact with it and see some of the metadata about the NFT. Here I'm saving it as a draft, all functioning correctly. Yeah. Okay. Then I'll go back to my dashboard, and the first one was saved as a draft. I'll just clean it up and remove it, nice and tidy. Okay. Cool. Does anybody have any questions at this point? Okay. As I alluded to, there's a lot more that you can do with a Web3 publishing platform than just to publish content. So every post on Mirror is collectible as an NFT. We call these collectible entries. So for example, one author, Chase Chapman, minted a post of hers as a collectible NFT, and she set a limit of 333 editions that could be collected. And she had a bunch of fans in the community, and she probably didn't even realize this, but a lot of them wanted to collect her post as an NFT, and she raised $5,200 from the entry. She had this amazing quote in the piece. She said, to co-own something is to have a connection with someone. And so while individual ownership is great, collective ownership is the social primitive of Web3. And as I said, 333 people co-own this piece of hers, and that sort of forms a community of collectors who are gathering around ideas and writers, and they are funding work and building up a library of entries that are meaningful to them. And so this is really important because while giving funding to the writers that people love, they're also building identity in Web3 by collecting things that are meaningful to them, ideas that are meaningful to them, and then in the future, you'll always be able to go and see what people have been interested in over time, and that breeds a lot of trust and reputation and credibility for people in the space, which is always going to be important for things like governance and other things that we want to achieve in Web3. Here is the founder of Pool Together. He's just saying that the new collection feature on Mira is his favorite crypto thing because he loves ideas, he loves reading, and now he's able to give authors a couple of dollars that he would usually pay for a book. He can collect an entry on Mira and use it as like a bookmark, and he's supporting the work, and it's just something that's pretty cool to be able to do. It's sort of like tipping in the space. Here's some people on Twitter just like talking about their collections. So they're just saying, what's your library? Like, if I go over to your house and you have a bookshelf of books, I can understand more about you through what you like to read, what authors you like to read. And we don't have that on the internet. There's no way to really look at somebody's like bookshelf, maybe something like Goodreads. But NFTs could be a really interesting way to do that. And of course, NFTs exist out of a particular platform, and so you'll be able to see them on your wallet, like Rainbow Wallet or Coinbase Wallet or wherever you're using. By getting funded through NFTs, the writers can also keep their work public and open. So this is really important because online publications at the moment, they often have a subscription model where you have to pay to subscribe, and then only if you're a subscriber can you actually access the content. So that happens in academia, but it also happens in products like Substack. Oftentimes you really want to read a piece in the New York Times, and then you can't get to the third paragraph because there's a big box that says you need to pay and subscribe in order to see the content. And that's the state of the internet right now. But with NFTs, the work actually becomes more valuable to collectors the more that people read this. This is sort of the Mona Lisa hypothesis, where a work that everybody knows is more valuable than maybe an artistically better work that not many people know. So the more the meme spreads, the more value it often has. And so collectors actually want people to read the content, and so they pay for it and then make it open and accessible. And so we can have an internet where the information is free, but the creators still get funded and paid. Okay, so in this video, I just go and show how you mint NFTs as a blog post. And a surprising fact here is that it's still free to mint. So authors don't have to pay to make their entries collectible. All entries are just collectible by default. So we do that by basically having the creator sign all of the data, but they don't have to post it on chain until it gets collected. Here, I'm specifying some funding. So if I want to enable funding and make the collection paid, then I can do so and I can set a price. So here I'm setting $1 with a maximum supply of 2,000. It means that 2,000 people will be able to collect the post for $1 each, and I will make $2,000 or something on that blog post if people collect it and it sells out. I'm going to show some examples. So this is Chase Chapman's blog, which I was speaking about a little bit earlier, and I'm going to scroll down to the post where she sold 333 NFTs of the post. And so, just like a lot of other platforms where you would see the likes, how many likes a post has or how many claps, a like doesn't get you lunch. It doesn't get you paid as a writer, but collecting NFTs really can. And so here I've clicked on the list of collectors, and you can actually see these are real identities in Ethereum. You can go and see, this is David Phelps, he collected this piece. I want to go and see what other pieces are in his library. I'm so curious about what he's reading. And I can go and take a look at his wallet. And in future I'll see the art that he's collecting and the entries that he's reading and collecting it. And that sort of just creates a much better community experience for creators and collectors, and we can form identities and networks and communities around ideas and artwork and things that are just more cultural on chain. So here's a list of Polinaya's, his library, which is so cool because he's a thought leader in the space. So I want to see what thoughts are influencing him and is causing him to think about the things that he's writing about. And in this post, Chase is really talking about exactly this sort of concept of ownership being contextual, relational, and social, and its ownership is actually connecting people into these communities and groups. An evolution in human connection. So as we create digital communities online, NFTs and on-chain records are going to be part of the ways that we do that. And they don't always have to be speculative, although they can be. But oftentimes they can just be free. It's just a token in your wallet to show that you care about something. This post was fully collected. She raised 3.3 ETH, which is, $5,400. It sold out. And people can actually go and collect this now on a secondary market. Because it's an NFT, it doesn't exist just in Mira. It exists everywhere on Ethereum. And so you can see people are actually reselling the NFT of the post for a higher price. So there is some speculative aspect to this too, which can juice the funding. So, if an author is very well known, maybe they choose to make the NFT mintable for free, but then it goes for a much higher price later on the secondary market. And that can be something that's very interesting to their readers. Their readers might really appreciate that. And so it sort of incentivizes people to pay attention and read and take authors seriously, which is something that can bring efficiency to the writing market, if you will. Does anybody have any questions on this? Yeah. Yeah. Yeah, okay, so I'll repeat the question on the mic. So the question is, who pays for this if the writer doesn't pay? And the answer is that the collector pays. So in a lot of situations, it's the collector that's incentivized to pay the gas fee because they want to own something. And a lot of the times, the writer, we just want to make it as easy as possible for them to get onto the platform and put content out. So we make it free for them to publish. We store the signature that can mint the NFT, and then we allow, it's almost like an off-chain order book, like we allow the collector to go and execute that against a contract and then mint it. And we'll decentralize all of the signatures so that you don't have to rely on Mira, but it's a process to get there. I think a lot of writers will be the first person to mint or will want to mint their post immediately, and we want to move to that world as soon as we can, but it's still a little bit expensive. The other thing I should say is that all of these NFTs are minted on Optimism on an L2. So we were one of the first larger projects to migrate onto an L2. We picked Optimism because it was ready and the community was quite favorable towards Optimism. And so we moved onto that platform, and it's working really well, and it costs about $1 to collect an NFT on Optimism. So all of these posts are collectible for pretty cheap, and that's how it works. Okay, so I feel like this is... Okay, so the last thing I want to talk about is subscriptions on Mira. Web3 subscriptions. So, traditionally on like a Substack, you're going to subscribe with your email and password. It works really well. It's like a notification mechanism. The writer gets to see all of their subscribers and see all their emails. And in some of the platforms, they can download all of their emails and send other marketing messages to them. It's really important. On Mira, we decided to have email notifications, but the real subscription happens through the wallet, through the Web3 wallet. You actually use an Ethereum account to subscribe. So that makes the community of subscribers Web3 enabled. What does that mean? Well, it allows the writers and projects to engage with their communities in new ways. When you're communicating with someone, not just through an email address, but through a wallet, there's so much more power that you have. For example, if you want to airdrop NFTs to your community, you can do that. And those NFTs maybe give them special access to content or to events. You could have an event like this where maybe I'm speaking and then I could airdrop NFTs that give free access to the talk to all of my subscribers. And so that's going to give an incentive for people to go and subscribe to writers that doesn't exist. And all of these, subscribers that people will have, they have other things in the Web3 ecosystem that they're doing. They're collecting other posts, they're collecting other NFTs, and the writers can go and explore that and understand their audience better. They can do all kinds of new data analysis on the subscribers that they have that they would never be able to do with email addresses. So the wallet is just going to be a much, much more powerful way for subscribers to get access to content and interact with their creators. And then also for the creators, they're going to want to build up a base of subscribers that are wallets, a community of wallets rather than email addresses. And then, of course, up-and-coming products. So I'm sure you guys have heard of, peer-to-peer messaging products. Lit Protocol was one that was mentioned earlier. There are going to be so many products that rise up that do social communication for wallets. And again, having that base of wallet subscribers is going to be more powerful because you'll be able to use those tools with your subscribers, and you won't be able to do that with email addresses. So drop your email, drop your ENS. Yeah. Okay. Anyway. Okay, so one one last video that's just like a demo of the subscriber interface, and then I'll be done. This is Erica's blog post, and so I hadn't subscribed yet to her before, so I'm going to use this as a demo. So I'm putting my email address in, and so I will get email notifications as a subscriber. I think that's important. And then I'm signing that with my wallet. And so this is saying my address is subscribing to Erica's address, and then I will get email notifications, and Erica will receive my wallet address as a subscriber in her dashboard. And then I can do that with other posts as well. And it's easier the second time because you've already signed for your email the first. Anyway. And then I'll go back to my dashboard, and I'll just quickly show you what it looks like as a creator at the moment. We'll add more things in the future to this to make this more powerful, but at the moment it's very simple, and it just, you'll have your list of subscribers here, and you can go, and they're, real Ethereum addresses, so you can go and look at their profiles, see what they're writing, see what they're collecting, go to their Etherscan, check their balance, etc. So this is one of my subscribers, and I'm looking at his list of entries and collections. Okay, so that is the end of my talk, and I would encourage you to please check out Mira, write a Hello World post, and see how easy it is to get a voice in Web3, and then see if you can get some collectors. Once people collect, it goes on to other, it goes onto the graph protocol that you saw earlier. All those things get indexed. It's all on Ethereum, and it's all interoperable with other protocols as well. So really fun stuff. Okay. Does anybody have any questions? Yeah? Okay. 감사합니다.
Better like this, yeah. All right. Hello, everybody. I'm Norswap. I do research and development at Optimism. And what I want to talk to you about today is how we secure the Optimism blockchain. So Optimism is a layer 2 rollup. So first of all, if you're not familiar with rollup, I'm going to give you the real short version of how an optimistic rollup works. So the issue with Ethereum is that it doesn't scale. it doesn't scale for a very good reason, is that they want to stay decentralized. And so sort of the line in the sand that was drawn is that everybody should be able to validate the Ethereum blockchain at home using only a laptop and maybe some extra equipment, but it should stay relatively affordable and hassle-free. And that's pretty good, but we still have a problem that people want to transact and there's not enough transaction space available. So rollups are a way to fix this, and the way rollups works is that you have your L1 blockchain, so that those are the little computers you see there. And if you're a L1 user, you're rich, so you have a top hat and a mustache, and you can transact directly on Ethereum. If not, you're L2 user, you can transact with one or multiple entities known as the sequencer. And sequencers are big entities, and there will be much less of them than L1 nodes. So what the sequencer do is that they process the L2 transactions, just like they were normal transactions. Then they send the data of the transaction to L1. Only a transaction, these transactions are not executed on L1, they're only executed on L2. They also send to the L1 blockchain the result of executing a transaction. So that's a state root that commits to the whole state of the layer 2 blockchain. Then you have these other actors called verifiers. And what the verifiers do is that they download the L2 transactions that have been posted to Ethereum, they re-execute them, and then they check if the result that they get is the same as the result that the sequencer got. If they get the same result, it means everything is fine and the sequencer did a good job. If the result is different, it means that there was a bug in the sequencer, or the sequencer attempted to do some malicious action to steal funds or something like that. So if they detect such a case where they disagree with the result of the sequencer, what they can do is something called a fault proof. So this is a process in which on Ethereum they are going to challenge the result. And this presentation is really about explaining how this fault proof process works. How can we be secure, right? So there is one compared to Ethereum, it's almost as secure. There's only one security assumption that is added, and this security assumption is that there's at least one verifier that exists that is honest. You only need the one, and then you're fine. Okay, so the next step is explaining these fault proofs. So as a recap, optimistic rollups are secure if Ethereum is secure, and we rely on this single verifier. The fault proof is played through something called a challenge game, and it's played between two actors, a verifier and the sequencer. We also sometimes call them challenger and defender, but for simplicity you can think of them, the verifier that detected the problem and the sequencer that posted the result in the first place that is being challenged. So the guarantee is that as long as Ethereum itself is secure, then this process will work, and then the challenger will always be able to challenge the sequencer successfully, assuming he is indeed right and the sequencer misbehaved. And so if you, given this property, it means that using the main bridge of optimism, you will never be able to transfer stolen funds back to Ethereum. So this is the same thing, but in a graphical way for those of you that are more graphical. So you have L1, Ethereum. The verifier reads the batches, so these are groups of transactions, of L2 transactions. He executes them and creates these output routes. He also downloads the output route from L1. Then he compares those. If they're the same, everything's peachy. But if they're different, then he does this challenge game, this fault proof on L1. So now we run into a problem. So we have determined that executing the transaction leads to different results for a sequencer and a challenger. How do we decide who's right and who's wrong? If you were to take a naive approach, what you want to do is re-execute all the transactions on Ethereum. The problem with that is that it's extremely expensive. So the very simplest approach you can take is to rerun the block on Ethereum, so in an EVM interpreter that is itself running on the EVM. There are huge overheads in doing so, and it's not possible because you're executing a whole block worth of gas within a transaction that is itself limited in gas. And because you have overhead, so a multiplier in the time of execution, it's just not possible. So another solution would be to say, well, blocks on layer 2, they are actually EVM, right? Like on the Optimism, we use the EVM. And so the code that we're executing is the same that is being run on L1. So what if we could just execute that code directly? That's a good idea, but there is a problem. The problem is that there's a lot of opcodes and operations that depend on the context of the blockchain. And so a very simple example of that is the block number opcode. So when you run block number, on L2 you will get the L2 block number, but on L1 you will get the L1 block number. And so there is a way to fix that, and it's that you need to patch the opcode to remove this and put a call to a contract that holds all the context. And you run into similar issue if you're trying to read the blockchain memory, for instance. This is still way too expensive. But what if we did this, but instead of challenging a whole block, we would just challenge a single transaction? So this works, and this is what Optimism tried to do the first time we tried to do fault proofs. We tried to do exactly this. There are a lot of nasty issues with this. It's still expensive, and to give you just an example of one nasty issue that happens with this, so Ethereum has a limit on the size of contracts. So the number of opcodes that you can put in a contract is bounded. And the problem is that we need to patch the opcode. So we take the L2 contract and we replace some opcodes by some calls to special context contracts on L1. And these patches, they are bigger than the original thing that we replace. So the contract size grows when you deploy it on L1. And that means that effectively, your L2 contracts are much more limited in size than the L1 contract. So this is a very, very bad user experience because you try your contract, on L1 it works, but on L2 it doesn't work because it becomes too big. So this was very nasty. So what is the solution? It's to use something called a challenge game. So now we're stopping with the idea of executing the whole block or the whole transaction. What we want to do is figure out exactly where we disagree in a small part of the computation, and then we want to execute only that small part on Ethereum. And so well, we will call this a single step of disagreement. So the goal is to find the single step of disagreement. And what is a step? There's different ways you could do it, but the two most common ways are one EVM instructions or one assembler instruction in the program that validates a block and executes the transactions. I'm going to explain both of these things. So our fault-proof and challenge game system is called Cannon. It was originally designed by George Hotz, who was a very famous hacker. He was the first one to unlock the iPhone, and he also hacked one of the PlayStations. And now it's under development by Optimism, so including me. It's not the first system of this kind, so Cardizzy does something different, Arbitrum, also think TrueBit. So this is an idea that has been around. It's the idea of verified computation. So you do off-chain computation and then you verify it on-chain. However, it is the first system of this kind that supports EVM equivalence. So anything that works on Ethereum also works on Optimism. You can reuse all the tools, Hardhat, Foundry, whatever you use to do your development, it will work on Optimism out of the box. So to figure out where we disagree, the challenge game performs something that is called, for the fault proof, you do something called a challenge game. And what a challenge game is, really, it's a bisection on the execution trace. So what is the execution trace? when you run a program, you run a bunch of instructions one after the other, and the execution trace is just the list of all the instructions that you're going to execute. So, but what's being executed? So there's two ways to do it. You can think of EVM execution, then your trace is a bunch of EVM opcodes. But validating a block is more than just executing transactions. And so if we go this way, where our trace is EVM opcodes, we need to do the rest of the block validations in specialized EVM contracts that we have to write. The other way to do it is to say, well, the program that we execute is not the EVM execution of the transactions, it is the validator software. So Go Ethereum or Aragon, all those, they validate blocks. So what if we could take those software and run them, and that's our execution trace, and that is what we'll be able to challenge. And so that's the approach that we're taking, and we have this piece of software called minigeth. So it's a subset of Geth or Go Ethereum that is patched to support our system and compiled to MIPS. And the difference between Go Ethereum and minigeth is very, very small. So we just removed a bunch of codes, that's very easy, and then we made like a very small amount of changes so that it supports the system. And that's important because it means that whenever Go Ethereum is updated, we can always update minigeth very easily. So how to figure out the step of disagreement over this execution trace? The general principle, and I'll give a graphical illustration of this after, is that you want to hash the memory of your program at different points of the execution trace. And you're going to start at the midpoint. So at 50% of the execution, after half the opcodes, you take your whole memory, you create a hash of it. So for those of you that are familiar, there's actually a Merkle root. And you send that to the L1 challenge contract. The verifier does this, the sequencer does this, and they compare the results. If the results are the same, we go to 75% of the execution trace. So that's like half of the remaining span. And if it's different, it means that we disagree before, and so we go to 25%, right? So if you agree at 50%, it means the disagreement is after. If you disagree at 50%, it means the disagreement is before. And we can keep doing this, cutting the space of possible disagreement in half each time, until we find a single instruction where we agree on the memory before, but we disagree on the memory after. So executing this single step against the memory will tell us who is right and who is wrong. So once we find this step, we need to execute it on the blockchain. And so we compile minigeth to the MIPS instruction set, and we use MIPS because it's a very simple instruction set. So we have an on-chain MIPS interpreter that is less than 400 lines of solidity. And we use that to execute the instruction. But this instruction will need to access the minigeth memory, right? And the minigeth memory is not on layer 1. It also needs to access the transaction batches, and those are on layer 1, but they need to be accessed. So accessing memory is relatively easy because we already have a hash of the memory. We have a Merkle root of the memory, and this Merkle root lets us prove any possible piece of memory against it, right? So a Merkle root is a tree structure made of many hashes, and the property of it is that you can say, well, this byte is this value, and you can submit a proof of that you can verify on-chain. And a single MIPS instructions is not going to touch a lot of memory spots, maybe 2 or 3 at most, and so you only need to provide 3 of these proofs, which are relatively small, to be able to execute the instruction. So to access the batches, and I should have said, these transaction batches, they are posted to Ethereum, but they are not stored in the EVM memory because that would be too expensive. Instead, they are posted as cold data, so they live with the transaction, within the transactions. And to access them, we use something called pre-image oracle, and this is what I will explain next. This was already like a lot of content, so I want to pause to see if there's like any questions, or, you know, there's no stupid questions, so don't be afraid. I know I look very intimidating, but I'm very nice, I swear. Everybody all right? If you're really too shy, you can come find me afterwards and ask your questions. So, all right, this is an illustration of the challenge game graphically. So, these boxes on the top and the bottom, these are the execution trace of the challenger and the defender. So every single box is one assembly instruction. So you start at the middle, you are going to take a hash of your memory, you submit it to Ethereum, and you compare. In this scenario, we're going to say it's the same. So the disagreement is after the midpoint. So you go to 75%. Again, you take a hash of the memory, you compare it. In this scenario, it's different. Again, you cut it in half, 62.5. And you keep doing this until you find a single instruction that you disagree on. All right, so the next thing we need to talk about is the pre-image oracle. And this is the way, the pre-image oracle is a way in which you can access any data on the Ethereum blockchain ever, and you can prove that this data existed there. So how does it work? So the interface of the pre-image oracle is simply a function that, given a hash, returns a pre-image of the hash. So the pre-image of the hash is the thing that needed to be hashed to produce the hash. And so, assuming that you implement this in a contract, so it's very important to say that if you're using a cryptographic hash, it's normally impossible to do this. You cannot take a hash and find the pre-image, because there are many possible pre-images. And also it's computationally infeasible. But if you give the pre-image in advance to a contract, then you can query these pre-images that you've stored, say, hey, here's the hash, give me the pre-image. Why is this useful for us? It is useful because in Ethereum you get a lot of hashes that commit to important information. So you have an opcode that gives you block hashes, and a block hash is a hash of the block header, which contains useful information. Each block header contains the hash of the previous block header. So that's also something that you can use. And so using those, you can already see that if we have the pre-image oracle, we can walk the whole blockchain backwards. By starting with a hash, we get the header, then we can walk, we have the hash of the previous header, so we can walk there, then we have the hash of the previous header, so you can just traverse the whole chain using only this simple interface. So I already see that's quite powerful. And the other thing you can do is you can prove any state in any block, so any state that the Ethereum blockchain had over all the blocks, or any transaction that was ever included. And that's because every block header has a Merkle root for all the transactions in that block, and a Merkle root for the whole state of the blockchain in that block. So you go to the block you want, and then you find the Merkle root for the state at that time, or for transactions at that time, and you can go down there and prove via the pre-image oracle any state. And this works because a Merkle tree is a tree of hashes, and there will be the next slide will show this graphically, so it will be a bit more understandable. Okay, access and annual one data, that's what I just said. Okay, so this is the graphical slide. So these two trees at the bottom, these are Merkle trees. And the way a Merkle tree works, so this is a binary Merkle tree, so each node has two children. And basically, each node can be represented by the hash of its children. So if you start from the bottom with pure data, right, you can see that you have a piece of data L1, so maybe this is a transaction. And the node hash 00, that's just the hash of the data L1. But then to create the node hash0, you hash the two children hash00 and hash01. And these two are only hashes, right? And then to create the top hash, you hash hash0 and hash1 together. And so you can see it's a tree of hashes all the way down. So to take an example of walking this, so say I'm interested in getting a transaction or a transaction batch that lives in block 41. Say I'm at block 42. I use the block hash opcode to get the latest block hash. Then each green arrow here is a use of the preimage oracle. So I have the block hash opcode. I use the preimage oracle to get the block header. Then from the block header, I get the hash of the previous block. And I use the preimage oracle to get the previous block header, so the block 41. In block 41, I get the transaction Merkle root, and I use the preimage oracle to get in the tree and get the children. And then for each children, I each time use the preimage oracle to get the child until I can get the transactions that I'm interested in. And this is exactly what we use to read those transaction batches that contain all the L2 transactions. So concretely, in minigeth, which is our re-implementation of the, well, not, or modification of Go Ethereum that validates block, we use this to re-implement the database, right? So normally if you have a Go Ethereum node, it has a database of the whole state of the blockchain, of the blockchain you're validating. And it turns out you can use the preimage oracle to re-implement that. And we actually have 3 implementations of the preimage oracle, and this is where it gets a little bit tricky. It's implemented on-chain, and this is used for the single-step execution. And on-chain, we simply submit the preimages and store the hash to preimage mapping. Very simple. It is. We also have one implementation of this in that we compile to MIPS, and this one is necessary. So we need to run minigeth in MIPS off-chain because we need to hash the memory for the challenge game. Otherwise, we need to run MIPS off-chain, but we need to get these hashes so we can do the actual challenge game. And these uses prefetched hashes. So the preimage oracle is similarly like we already know the hashes in advance, and so we just read from a hash to preimage mapping. And but then we also need to run minigeth in the, normal instruction set, whatever runs on your laptop or server. And for those, we need to get the preimages, and we use the JSON RPC methods that online nodes expose. In particular, we use get block by hash, and we use this thing called ETH get proof, which we use very creatively. There are some challenges there. But basically, get proof gives you a Merkle proof or of any piece of state in Ethereum. All right, so small summary. Optimistic rollups are secure as long as they're an one-less validator. The validator, if it disagrees with the sequencer, can initiate a fault proof using Canon. That's our fault proof system. So the validator and sequencer, they play a challenge game, and they find a single step of agreement in the execution of the validator, which is compiled to MIPS. So this is called the challenge game. And finally, the single step is executed on-chain, and we can access the memory of the validator through some Merkle proof, and the batches of transactions that are being executed can be read using the preimage oracle. And yeah, that's how it works. Oh yeah. The final slide, very important. Where are we with this? So this is actually not fully implemented yet. This is the design. The design is fixed. We know how to do it. But George gave us a prototype which allowed us to challenge L1 blocks on L1. This is useless because by definition, L1 blocks are correct, right? But it's a proof of concept that shows that this can work. And so what we're almost done with is changing L2 blocks on L2. So it's a simple transposition of this concept, but it shows that whatever changes we made to the original Go Ethereum that we're using on Optimism still doesn't break the system. And then the real thing that we want to do is challenge L2 blocks on L1, right? That's the whole point. And for doing this, we need to add something called L2 chain derivation to Minigeth. And that's the part where we take these transactions that have been posted on L1, so the L2 transaction on L1, and we create blocks from them. And that's a logic we already have written, and we can import it fairly easily because everything in this stack is in the Go language. So we can use the Go module into our node directly to do that. And so this will be probably our next focus after we release Bedrock, which is the next version of Optimism. There you go. If you have any questions, again, feel free to ask them now or find me later.
Hello everyone, I'm Vivian from EFPSE team, and I want to introduce the UniRep, which means Universe Reputation. And yeah, why we use UniRep? Because nowadays we have a lot of applications. Their own reputation system. For example, we have followers in a subscriber in YouTube or Airbnb and Booking.com reputation. And also we have Karma in Reddit. But how can we integrate them together in one reputation system? So UniRep is introduced here. And now I took an example. If Alice is an Airbnb user and she wants to prove to Booking.com landlord that she has enough reputation to live. She has enough reputation in the Airbnb, but the landlord of Booking.com doesn't believe she has enough reputation. And now how can Alice prove to the landlord in Booking.com? The easiest way is that Alice can take a screenshot of the history of his Airbnb history. But now Alice's privacy will be compromised. And it's really easily to forge. And so that the landlord of Booking.com is hardly to be convinced. But now UniRep can solve this problem. UniRep is a private and non-repudiable reputation system. So user can give others reputation, and also he can voluntarily prove how much reputation he or she has. And also user cannot refuse to receive bad reputation. And now I will introduce the protocol behind the UniRep. So there are two actors in UniRep. The first one is the attesters, who will not be anonymous in this system, like Airbnb or Booking.com. It represents user to give reputation, like they can issue reputation token, and the users, which means the Alice or a landlord in Booking.com, and they are anonymous, and they can receive reputation and also prove their reputation. So others will never know that who received this reputation. Yeah, so it can achieve privacy. And in this system, we define an epoch key to receive reputation. And also we define a period of time called epoch. For example, 7 days. And then in each epoch, user can have k epoch keys to receive reputation. And the epoch key is like a hash, so it will it is hardly to link to an identity, which is like Alice here. And in this system, when user signs up, and we use the identity system called semaphore. And semaphore consists of a private identity and a public identity commitment. So the user use the public identity commitment to sign up in a Unirep smart contract here. And there's a global state tree is computed, and it's computed by hash of identity commitment and the user state tree root. So we will introduce what is user state tree root in this protocol. User state tree root is how much reputation a user has in the Unirep protocol. So the index of the tree is the attester ID, and the leaf value is hash of all the reputation data. For example, the positive reputation, negative reputation, and graffiti, and also a sign-up flag. For example, if a user has signed up in Airbnb, and he will get a sign-up flag here. So the tree is street leaf is the hash of the reputation. And the global state tree is, we said before, is the hash of ID commitment and the user state tree root. And when user signs up, and it will insert a leaf in the global state tree in this protocol. And also, a user state transition will cause a new leaf inserted in. And we will introduce the user state transition later. And also, we introduce how the attester can sign up in this protocol. So now the attester is non-anonymous, so the attester can use the Ethereum wallet or a smart contract to sign up in the Unirep contract. And the Unirep contract will assign an attester ID to the attester. Like if the Airbnb is the first attester to sign up in the Unirep protocol, and it will get the attester ID 1. Yeah, so it is the overview of the sign up in the Unirep protocol. The user used the ID commitment to sign up, and the attester used its Ethereum wallet address or smart contract address. And we said before, user used the epoch key to receive reputation. And the epoch key is hash of identity and epoch and nouns. And the nouns is 0 to k minus 1 to let user have k epoch keys in this protocol. And how can we make sure that the user is the owner of the epoch key? And how can we make sure the user doesn't compute the epoch key of it is not a random number of the epoch key. So we use the zero knowledge proof to let user convince others that the epoch key is computed correctly. Yeah, so it is what in the zero knowledge proof circuit. So we take the epoch and the identity and announce here and check if the ID hash, the user state tree root is together with the Merkle tree proof to see if the global state tree root is matches the protocol. And also we check if the epoch key is computed by the ID hash of ID and epoch announce. And the red words here is the private information, and the green words here is the public information. Yeah, so the other user can check that the other user only knows the proofs output epoch key and global state tree root and the valid epoch. Yeah, so when user generates epoch key and epoch key proof and others verifies it is valid, and then the attester can send the reputation to this epoch key through the Unirep smart contract. And now if we want to make sure that the reputation it cannot be ignored by any other every user, so we use the hash chain to prevent the prevent users to do this. So we hash the reputation together with the attester ID, positive reputation, negative reputation, gravity, and setup flag. And each epoch key has its hash chain. So whenever the epoch key receives a reputation, and the hash chain will be computed. So if the user ignore any reputation here, the hash chain result will be totally different. Yeah, so now if the Alice received the 5 reputation from Airbnb and 3 negative reputation from Twitter, but now the Alice user state tree hasn't been updated now. So in this protocol, we use a epoch transition and user state transition to let Alice proves that he owns this epoch key and process this reputation and receive this reputation. Yeah, so in the epoch transition, the hash chain of the epoch key will be sealed to make sure the epoch key cannot receive the reputation anymore. Yeah, so and then the epoch tree will be computed, and the index of it is the epoch key, and the value of it is the sealed hash chain. And this tree is also used to prevent user ignore any reputation. Yeah, so how can user receive the reputation? For example, the user want to the user will perform a user state transition from epoch N to epoch M. And then it is what she will do. The first one is that he will prove that he has signed up or he has performed the user state transition in epoch N and process all the attestation. And final, it will compute a new global state tree leaf in epoch M. Yeah. And it is how the user state tree updated. Like, for example, in a initial user state tree, it will be empty. And if a reputation comes, and we update the fourth leaf, and it index 3. And the leaf will be hash of the positive reputation and negative reputation and rest of it. And also compute the hash chain. And the second reputation comes, and we update the user state tree according to the attester ID, and also compute another hash chain. Yeah, so after we process all the reputations, we will have a hash chain of all epoch keys and the updated user state tree root. And then in the circuit, we will use the identity and epoch, and we iterate all the nouns, all the possible nouns, and to calculate all the epoch keys the user has in the current epoch. And then we use the epoch tree to compute the epoch tree root. Like we check the epoch key and the sealed hash chain in its leaf, and then to check all the epoch key and sealed epoch hash chain match the same epoch key root, epoch tree root. Yeah, and then remember that we have updated user state tree root, and then we will compute the new global state tree leaf with hash of identity and the updated user state tree root. And we also compute nullifiers called epoch key nullifiers. And it is used to prevent user from performing double user state transition. Yeah, so if the user generate the user state transition ZKP proof and submit it to the Unirep smart contract, and everyone in this protocol can verify if the proof is correct, and then if they are correct, then update the global state tree. Yeah, then after user receives this reputation, and he can voluntarily really prove how much reputation he has. For example, we can prove the reputation is bigger than the minimum reputation we set here. For example, if Alice have 100 positive reputation, then he can choose to prove I only have 10 here. And also the pre-image of gravity. And the gravity can be set of any string. Yeah, so it will make the reputation system more you can have more option to prove things in the reputation system. And also user can prove that if the user has signed up in the attester's application. And the idea to prove the reputation here is that we can compute the user state tree leaf by hash of the reputation, and also check the user state tree root and hash of identity is one of the global state tree leaf. We can see in this picture. Yeah, the left-hand side is the user state tree root, and its leaf is hash of all the reputation from one attester. And the right-hand side is the public global state tree. And the user's leaf would be one of the leaf in the global state tree. Yeah, so here's the overview of Unirep protocol. The user with the public identity commitment will sign up in the Unirep system, and the attester can sign up with its Ethereum wallet or smart contract address. And then user generates an EPA key and EPA key proof and submit it to Unirep contract. And then the attester will give reputation to this EPA key. Then it will every certain EPA length, the EPA transition will be performed, and the EPA will increase by 1. And all the EPA keys will be sealed, and EPA tree will be computed. Then how user receives reputation is that user will generate a user state transition proof according to all the EPA key he or she has and process all the reputation. Then the user will, according to the reputation he has, to update the user state tree. And then check the EPA tree rules if they match the same one. And then others see this user state transition proof and verify it is valid, and then update the whole Unirep state. And if user has one of the leaves in global state tree, and he can prove that how much reputation he or she has in the Unirep protocol, and use a reputation proof to convince others. And there is one of the example of Unirep protocol. We built a social media called Unirep Social, and it is a decentralized and anonymous social media. So user can publish a post and comment others, and also upvote and downvote others' posts or comments or post or comments. And user in the post can optionally reveal how much reputation he or she has. And instead of user has a real name or account, it will reveals only the EPA key, and it just looks like a hash of it. So it can preserve the author's privacy. Yeah, and we build this system we build the anonymous social media with a reputation system is to force users to take responsible for what they say in the decentralized social media. Yeah, and this is one of the example of Unirep protocol, and more applications that with reputation requirement is also welcome to build upon the Unirep protocol. And here's our GitHub and documentation. Yeah, and also welcome to join our Discord to discuss this protocol with us. Thank you.
Hello, everyone. I'm Guilty Gyoza. I go by Guilty or Gyoza, both fine. I'm a co-founder of Topology. We are building games fully on chain on Starknet. Okay, we're going to talk about a lot about video games today, and we think that there are a lot of past evolutions in the game industry, right? And every time video games transformed, right? Last time around, mobile came, and we have mobile casual games, and mobile give us access to games 24/7. But we think that blockchain will transform video games in a very different way. We think blockchain will bring significance to gaming, because blockchain is the place where things are immutable, they are permanent, they are hard. And so things happening on chain has significance, and so it will transform video games in a very unique way. We think that the game industry right now is akin to Web 1.0, so we're kind of calling it Game 1.0. What Game 1.0 means that there are very few people creating video games, and the majority of people are consuming the video games. So there's a massive skew towards read. Very few people write to the game as a medium. This is like recent statistics in the United States. For every one employee in the game industry, there's 1,000 gamers in the US. And so, when we think of gamers, we think of people, the persona where people are consuming the content and game logic provided by the game developer, while the game developer creates the content, program everything to give you the experience. All right, so a bunch of video games here. On top left, we have Fortnite. When you play Fortnite and you basically, that's port of 4. You basically click your left mouse button, aim, and release your left mouse button, and you deploy a castle. And all you do is engage with your mouse, but the game developer did all the fun stuff, right? Modeling the castle, programming, creating the computer program that would model the castle, place the geometry in the scene, and so on. All the wonderful stuff. And you as a gamer are only enjoying the mouse clicking action. That is kind of unfortunate. We think the game developers are enjoying so much by creating games, and gamers are thus far still passively consuming what is provided to them. On the right, you have Street Fighter, and so when you're using your special Hadoken in this case, you're pressing a combo of keys, and you're triggering the computer logic programmed by the developer. You're not doing anything more than that, right? But the computer programmers did a bunch of interesting things, drawing the animations, programming every little bit of the logic to give you that experience. Same for Ghost Recon Breakpoint, same for Witcher 3, CDPR. There's just a lot of things that go behind the scene game developers did, and we as gamers are consuming the content and experience provided by them. This sounds terribly like game Web 1.0, right? And so how do we go to Game 2.0? Well, one way is to think about System 1 and System 2. This is thinking fast and slow. And so when you play video games, a lot of fast twitch, keyboard and mouse, that's System 1. System 2 is like slow thinking, strategic thinking, right? Burning your brain sort of thing. In fact, a lot of the 10,000-hour games, so-called games with incredible depth, they are engaging System 2 intensely. So this is the beloved Age of Empire 2. We are looking at the famous MBL, placing a town center next to the opponent's town center. This is the famous Persian douche, right? And so by playing Persian, you enjoy like half resource placing your town center, or building your town center, and your town center has double HP. And so you can basically pull this troll off, right? So kill your town center, move all your villagers to the front, and rebuild your home right next to the opponent's home, and just shoot down your opponent's TC. This is a funny thing. And game developers programmed everything. Program the logic, program setting all the parameters that define what each civilization means. As a gamer, we engage our system through, we think strategically about these different strategies to utilize the logic provided by the game developer. But still, we cannot touch the game code, right? Well, other than modding, right? But the canonical primary game operated by the game developer, we can't touch it. We can only modify the game as fans. Okay, so when it comes to players creating things in game, we have to talk about UGC. Right? We just have to talk about it. User-generated content. And when it comes to UGC, it has a very long history. So this is Ghost Recon Future Soldier. as FPS player, we love customizing our guns. We love to customize how our scope is, how our muzzle is, our magazine size, all that stuff. Another kind of customization is the appearance editor. So this is a Naraka Blade Point. People love to customize their avatar, how they appear in games. And this customizer gives you the ability to sort of parametrically play with the sidebars to tune every little details about your facial expression and your body appearance. Just to give you a benchmark, so this is a game with like Chinese kung fu wuxia kind of background with some Japanese influence. But with the parametric facial editor, gamers are creating ridiculous stuff, you know, like Iron Man, Geralt from the Witcher 3 series and so on. It's like incredible stuff. Right, so we have felt this trend where gamers want to actively participate in creating games, creating things that exist in games. We have to talk about Roblox if we talk about UGC. So this is the Roblox editor where an interface is provided to gamers, mostly young kids, very young kids, that are using this interface to design their little worlds and design the little games for other kids to play. And furthermore, there's a scripting language embedded in the interface, which is the Lua scripting language. So young kids are learning Lua in order to play Roblox and create games for their friends to play. So this is very cool. And let's come back to blockchain for a little bit. Dark Forest, we have to talk about Dark Forest if we talk about on-chain games. And what's really fun about Dark Forest is we have a whole part of the game that is not provided by the game developer, right? Gamers are writing plugins and scripts that are automating various different things. And there's like whole marketplace also created by gamers, not the developer, that are hosting these different plugins. And these are all user-generated content, user-generated scripts. So this is really fun. But can we take it a step further? So I like to use this mental model, thinking in like schematic terms. So let's start with this. We have a set of rules, the rules of the game, and basically the rules would spawn a space of play. Right? So if, like in linear algebra, you will have like a basis spawning a vector space, kind of like that concept. Right? So the rules define the boundary of play. Outside a boundary is illegal. You can play within the boundary. Now let's put the people here. So we have gamers playing in the space of play, and we have developers that are building the rules, and the rules exist as computer code. Right? That's what video games is. And the way gamers can influence the rules thus far is indirect. Right? So the gamer can choose to play or not play a game, or the gamers can go to Steam and upvote or downvote a game or put negative comments to influence the developer to change the rules of the game. And so gamers have indirect way of influencing the game, and it's basically engaging market forces and capitalism so that, you know, game developer would sometimes are aligned with gamers. They would change the game towards what gamers want. Sometimes they will fail and the game would die. Now let's put blockchain into the picture. So what if we run the rules of the game on chain, right? So rules define transitions from game state to game state, and their computation, right? So we can write this computation in the form of smart contracts and put it on chain. So we have games running fully on chain. When the rules are enforced on chain, we have an on-chain game, like Dark Forest, Conquest, Xgracia, and so on. What's interesting here is that because the rules are on chain, they're transparent. People can audit it, and we can also govern it. So we can say, well, no change can be made to the on-chain game unless some community, you know, reach a consensus to approve it or disapproves it, right? So we can put an end gate there. That logical end says developer can develop new feature, but it is gated by some governance decision. Players have to pass that proposal for the new feature to be implemented into the game. And because the game is on-chain, we can govern it in a fully transparent way. And notice that the stroke color of play is the same as stroke color of govern. We think it's important for the gamers to govern the game, not coin voting, not people with you know, a capital power. And so you have to play the game to have a share to govern the game. And basically, we can just replace the gate with the DAO. So that right there is a DAO, right? We can have a DAO that governs the game where every change made to the game has to be approved by the gamers, and gamers would get governance right by playing the game, not by buying DAO tokens on the market. And I think Dark Forest establishes a path here, which is gamers themselves are developers. They write programs that enhance the gameplay, that expand the gameplay, and so we can perhaps break that boundary. We are all gamers, building games, playing games, and governing the games. Lastly, I want to add one last component there. So far, we have established that in order to change the rules of the game, we need consensus, right? So the DAO will form some kind of consensus to approve a new feature to be added to the game, a new character or a new special ability or nerfing or buffing something. Another way to change the rules, perhaps, is through some autonomous route. So imagine some meta rules beneath the rules that are just completely immutable. And they dictate some kind of algorithmic change of the rules. One example I can think of is, imagine Darwinism, evolution. So the meta rules will be the Darwinian evolution, and the rules will be the species, what exists in the world. Right? And the evolution doesn't change, but the species change over time. Right? New species come up, some species goes into extinction, and so on. But there's some kind of algorithm, the meta rules, that govern the autonomous evolution of games. And this perhaps can be called as autonomous games. Okay, so we're making this thesis that we think game right now is at game 1.0, and we are moving towards game 2.0, which we think will have such significance. It's a different kind of reality, and we're calling them on-chain reality. And it has a couple characteristics. First of all, the core game systems are fully on-chain, so it's fully transparent, auditable, smart contracts. It's immutable by default, and it's only immutable either by some kind of consensus reached by the community, and there should not be coin voting involved. That's why it's called merit-based consensus, or by some kind of autonomy of smart contracts. So smart contract runs some algorithm that dictates the change of rule, and the algorithms are immutable, and so no one can change the laws of the universe, basically. In order to demonstrate these concepts, we at Topology have made a on-chain game or on-chain reality called Isaac. Isaac is the first name of Isaac Newton, because we're running basically the three-body problem in a smart contract. And for people who have read the three-body problem story, it's by a famous Chinese sci-fi novelist. Essentially, imagine a solar system where there are three suns. And there's like a planet that revolves around these three suns, and it's a very poor planet. Right? At any given moment in time, you may be crashing into a sun or getting too close or too far away from the sun, so you will be either too hot or too cold, and so on. It is a very harsh environment. And so players have to work together to change their fate. And so Isaac is a game inspired by these stories, the three-body problem, and also the Wandering Earth by the same novelist, and also the famous Factorial building game, resource management game. Documentation open source, smart contracts all open source, and we're currently doing closed alpha. All right, so the game can be understood as three suns and a planet. Everyone is on the same planet, and everyone is building these production pipelines that are harvesting resources and transforming resources, and eventually they build planetary engines. This is the Wandering Earth story. And so imagine planetary engine as a rocket, right? And you basically mount your rocket on the surface of the planet, and you launch the rocket. And by Newton's third law, there will be a reaction, right? So you can drive your planet by launching the rocket. That's essentially how players work together to build rockets, place their rockets, and launch them to drive their planets here and there, to dodge the sun and evade the sun. And eventually, they can escape the sun if they can accelerate their planet to escape velocity, so they can just escape from this hellish environment. And that constitutes a win, right? So the game treats escaping the solar system as a win. All players win together. And when the planet crashes into the sun, all players die and lose together. Okay, so this is a screenshot from the front end. We have three suns and a tiny planet. This is the screenshot of the front end where players are building pipelines that harvest resources and transform resources and so on. This is in closed alpha. Okay, so again, all players are united against a common objective. There is no PvP. It's entirely co-op PvE. And what's special about this, technically speaking, is that the physical laws is operated in a smart contract. And also the regulations that dictate the logistics, how much resource is harvested, is transformed, every single tick, and so on. All these different things are enforced in a smart contract. So what do we mean by physics? When we talk about suns and planets, right, orbital mechanics, we have to talk about Newton's law of gravitation. So we have the inverse square law, right? The further you are, the less gravitational pull you exert on me, and so on. And we are approximating this using the standard numerical method, right? So for anyone taking classes in numerical simulation, you will know this is the standard, very simple fourth order Runge-Kutta method for approximating the differential equation of the gravitational law. And we are running this, basically this numerical simulator in the Chiral smart contract on StarkNet, on Ethereum, so that's the layer 2. There's also a chaotic system. All right, so three-body problem is a chaotic problem. Right, so we are living in a solar system with two bodies, we and the sun, and everything is pretty stable. We just go around in circles and ellipses. But in a three-body problem, things are very chaotic. You can't really project far enough into the future where you are, and that's why it's easy to go into destruction. But when we run everything on a blockchain, everything is transparent and deterministic. Right? So as a gamer, I can take the contract from the blockchain and run it locally, basically run it forward by like 1,000 ticks, and I can perfectly predict what will happen in the next 1,000 ticks. Everything is deterministic. Okay, so that reduces the difficulty. So we can put back to chaos by injecting some randomness. And again, randomness, oracle, the rabbit hole. So we're not doing any oracle. We are deriving random numbers from player actions. If you know Fiat Shamir, we're taking inspiration from Fiat Shamir. Randomness is derived from sort of hashing together a bunch of player actions in the last tick. And so players either optimize their actions and forget about gaming the randomness, or they game the randomness, but they make a bunch of unreasonable player actions. So either one or the other, which we think players would definitely choose to do the right action and forget about gaming the randomness. So this is the Fiat Shamir idea. Again, there are production lines and there are power grids, and so the problem is about players working together to solve this optimization problem at the civilization level. So it's a massive co-op factorial game. Multi-ingress, we like the idea that when we make a game, we want people with different backgrounds and interests to come in. Right? So you think about Counter-Strike. It attracts people that love muscle twitches and shooting people, and that's not everyone. Right? And so this game caters to different people. People want to look at circuit layouts, engineers. People want to look at production throughput, right? People working in like heavy industries and just, or oftentimes just nerdy about throughput optimization. People that have interest in physics and want to look at the orbital mechanics, they can come in and look at that. And finally, there's the human coordination problem, because everyone needs to work together to pilot their planet around, right? And imagine a planet with 1,000 people all in the same Discord channel, and they're all discussing who to do what when. That's a human coordination problem. And so people who love to do that can join the universe and help coordinate people just by talking. They don't play the game. And finally, just like Dog Force, this game is client agnostic. So game running on chain, everyone can build a front end that interfaces with the game and visualizes the game. And so this also presents a client building game, how to build the best client that visualizes the game in an optimal and enjoyable way. Just as a bonus, we are doing open alpha soon, and we put up this on-chain puzzle constituting 50 different puzzles, and we're saying that one account can only solve one puzzle, and only when you solve a puzzle can you join the Isaac later. And so if you haven't already solved the puzzle, when later we do open alpha and you send a transaction to join Isaac, your transaction will revert. So this is kind of a way to say, well, you need to have already solved the puzzle to be able to participate in our alpha, and it's all on chain. And finally, coming back to governance, we think governance is super important here, and we want to explore non-coin voting mechanism. So we're pushing this idea called CARS DAO. CARS is coming from James Cars, the author of the proposer of the concept infinite game. CARS DAO is essentially a governance pattern where you govern in order to govern more and play more, instead of you play in order to win and stop playing. So this is a concept of infinite game. Okay, so the schematic of CARS DAO is you as players on the top left will play the game, which is the subject there, and if you play the game well, you would earn voice in the DAO, right? And the voice will be mapped into votes, and you can vote on proposals. Proposals are exactly on-chain changes to the on-chain game. So everything is fully auditable. They're smart contracts. In order to have governance right, or voice in the DAO, you must play the game well. The voice is not some token on the market you can buy. So you have to play Isaac well to get voice, to have votes to vote on proposal, to govern the change of Isaac on chain, in order to play Isaac better and repeat that process, right? So you play more to play better and so on. Instead of having this sort of DAO token mechanics where if you buy DAO token, you would somehow vote for proposals that would get the price appreciate, and then you will exit, and then you will stop governing. That's finite game, and we are all about infinite game. So this is the architecture diagram of Isaac. So Isaac implements the card style pattern. You have the DAO governing the game on chain. The proposal contract, the charter contract, everything is on chain. So every change made to the DAO needs to be approved by the voters, and voters are gamers. They play the game. And finally, we want to mention our partners. Yagi builds the ticker on Starknet. You can see it as a clock, basically the Gelato network on layer 1, but on Starknet layer 2. And Apibara is the indexer that listens to all events emitted from the Isaac contracts and put up a nice backend for the front ends to query efficiently. Okay, and lastly, we want to talk about our upcoming unannounced project. We want to explore more the space of play. We are very inspired by Dog Forest, the ability for gamers to write scripts and automating things and expanding the complexity of play. We want to do something like that. And we also want to explore meta rules. So meta rules, again, are these algorithms on chain that are immutable. They would evolve the game algorithmically. And so the rules of the game are evolving by some algorithm. You can call that autonomous game. And we want to build this on chain, obviously. And we are exploring the fighting game mechanics. We love fighting games. And, oh, it's not repeating. And so what you're seeing is a female character with a katana. And can we repeat the video again, sorry? Yeah, thank you. Yeah, so there's a female character with the katana. And what she did is, a forward dash, a backward dash, then a forward dash, but she cancels the forward dash into a sequence of attack animation. So, for people who play fighting games, you will know what I'm talking about. And what's special about this game is there is an AI that drives the character. So this sequence is not controlled by me pushing keyboards and mouses. This sequence of action is driven by some very rudimentary AI in a smart contract that dictates the behavior of this girl. Also, the physics is in a smart contract, obviously. So, the characters move forward and backward, accelerate, deaccelerate. The physics is enforced in a smart contract. Yeah, so this is our next experiment, and we are very excited to explore the paradigm of Game 2.0. We think we are moving into this new paradigm, and in order to build this, we are in need of talents. So we're looking for a smart contract engineer, we're looking for research engineer, and also front-end designer. If you're interested in this vision, come talk to us. Thank you.
Well, good afternoon. Hi, I'm Jeff from Ethereum Foundation's Privacy and Scaling Explorations team. I'm helping out with an Ethereum project, the KZG Trusted Setup Ceremony. If you've been following on the roadmap for Ethereum, you'll be familiar with EIP 4844. That's proto-dank charting and data availability sampling for rollups, and that's all driven by KZG polynomial commitments. And those polynomial commitments need a trusted setup. So what we want to do as a community is get everyone contributing to this trusted setup. Now, once upon a time, or I learned that Koreans don't say once upon a time. They say back in the days when tigers smoked long pipes. Sounds like a great time to be around. So anyhow, back in those days, trusted setups were a pretty complicated, difficult sort of thing with lots of complicated interactions between the participants. But these days, the protocol's quite a bit simpler, and the other things we have going for us in this situation is we don't have a zero knowledge trusted setup. It's just it's a polynomial commitment trusted setup, and it's only for a relatively small number of points, like 2 to the 16 or 2 to the 15 is our largest sub ceremony. So it's like much smaller than if you've contributed to trusted setups before. This is quite a bit smaller than those. So it's going to be nice and easy for people to contribute to. It'll be a fairly quick computation. Maybe the actual computation should be a few seconds, maybe 10 seconds or something, and then less than a minute to upload and download and do the computation. So everyone is going to find it really easy to do. It's going to run in a browser, be quick sign-on protocol, and then just let it run. So nice and easy for everyone to do. We need to get each contributor we can only have one at a time, and there'll be a coordinator collecting these contributions and then figuring out who to pass it on to. And so it's one at a time. The contribution is passed along around the participants. And the security properties are that if we get one person who successfully discards the secret that they put into this computation, then it's going to be secure. So just an analogy to understand how that works. If you have a private key and you do the elliptic curve multiplication and you end up with a public key, and if you pass your public key to me and I mix it with my private key, we end up with a new public key. And if I then throw away my private key, then we can't derive that new public key again. So we'd need to have both those, yours and my private keys together to rederive that public key. Now, if we multiply that situation by hopefully thousands of times, then all we need is one of us to actually successfully throw away the secret that we put into that private key that we put into the computation, and then we're secure. So that's what we're aiming for. We need to defend against attacks. We need to make sure that the whole process is secure. So our main avenue for defense is to get lots and lots of participants. So we're going to make it nice and easy for people to just do the contribution, and hopefully we'll get thousands. So, if we got a chain of 1,000 contributions, all we need is one of those people to successfully hide their secret, and we're good. We will, however, think of other possible avenues of attack. If somehow the software we're using is compromised, then we need to think that someone might be siphoning off all those secrets. So we need to defend against that. So what we're going to do is have lots of variations in the actual software that people are using. So we're going to build APIs So people can write their own client, and we'll publish our own client so that people can just use it out of the box, or people can use the APIs to build their own. And then we get some variation in the stack that people are using to do this ceremony. And by that mechanism, we hope to get better resilience against attacks. It won't just be the actual client. The client will do like interactions with the coordinator to maintain their queue position and accept the download and do the upload. We'll also have an SDK that purely does the computation part of it. So, if you're, for anyone who's interested in building some of these components, we'd welcome all contributions, and we'll publish the APIs so you can do it fairly easily. And as well as that, we'll have security checks around each contribution to make sure each one is valid. We can check that the contribution is valid, that there's no that it's a valid sequence in the chain of contributions. You will get a fingerprint for your individual contribution as a contributor. So, and you'll be able to match that against a public record of all the contributions. So we'll make all this data public. We'll have a big dashboard that will show people contributing and a link to a permanent record of all the contributions. So you should be able to remember your signature for your contribution and look it up in the public record, and that ensures that the coordinator is not swapping in their own data and corrupting the ceremony that way. Yes, so the actual process of contribution is there'll be a simple sign-on, very simple, 3 clicks, probably sign in with your Ethereum address. Then you can join the queue at a time of your choosing. And as I said, we'll have a dashboard and it'll show how long the queue is. We're hoping that the queue will be fast-moving, but of course this is going to be quite widely publicized, and we're hoping for lots and lots of contributions. But so there could be a bit of a queue, but it should be quite fast-moving because this is a very quick contribution. So you'll join the queue. When you come to the head of the queue, you'll request the latest valid contribution from the previous contributor. You'll generate some randomness, and that's your secret that must not leave your environment. With that randomness, you'll feed it into the contribution. You'll update the data, and you'll send that back to the server. And then make sure the randomness is thrown away. So all of this, for an ordinary user, this will all be behind the scenes. You just do those couple of clicks to sign on and click a button to let it go, and then the browser will look after the rest. But if you're interested in building a client API, these are the steps you'll do. We'll have APIs for all of these things. So yeah, there's lots of ways to contribute. We want to get everyone just doing a contribution in the browser, but if you're interested in doing a hackathon project or just doing a side project on your own, we'd love your contributions. Build a client. You can build a compute engine. You could build a fancy client. It doesn't need to be a client that runs in the browser. You could run it in a CLI. You could run it in a Google Colab workbook. just go wild with that. When we're doing the bulk contribution phase, we will have time limits. So we'll have some sort of expectations around how fast this should turn around. But we're going to have multiple stages here. So there'll be that bulk contribution stage, and then we'll go into another phase where we're a lot more tolerant about the timings, and we're just inviting like open slather on how you want to generate the randomness and compute it. And people, if someone wants to put their laptop in a Faraday cage and have a radioactive banana with a Geiger counter to generate randomness and whatever, just think of crazy ideas, and we'll have a time for you to contribute like that. The ceremony, I think, looks like we'll start in October, around the time of DevCon. Probably that bulk collection phase, I forget the timings, maybe a month or two. We just need to get this completed in plenty of time for the Shanghai upgrade, which is like sometime next year. Yeah, and there's other ways to contribute too. Like this thing will need verifiers. If you want to build your own verifier to verify people's contributions, that'd be great. Or build yourself a dashboard. So if you want to, we'll have a dashboard, but if you want to build your own, that'll be great. Yeah, so there's lots of opportunities to build things around this. And every contribution, especially in those computation phases, is going to be a really valuable bit of diversity that we can build into this ceremony. So yeah, this is really one of those upgrades that, it's not just the boffins in the back rooms who are developing it. It's one that we can all be involved in some way or other. So look out for notifications about when the ceremony will start. If you want resources for the APIs, the specifications for the data format, the planning meetings, they're all on this link here. And please, you're welcome to come up and talk to me and find out more. And if we have time, then we can have some questions if anyone's got any. Or else, have fun with the ceremony, and we'll look forward to your contributions. Thank you.
안녕하세요. 네, my name is AJ. I'm a co-founder at Radius. Actually, we did a grant program of Ethereum Foundation called MEV Resistant AMM a few months ago. So today's talk is about the result of the program. So what's MEV? You probably heard a lot about MEV, but MEV is maximum values that can be extracted when building a block by censoring or inserting transactions or changing the orders of transactions in a block. So we hear a lot about MEV in blockchain and DeFi space, but the history actually goes back to traditional finance. Michael Lewis wrote a book called Flash Boys to tell us that how maliciously Wall Street institutions use insider trading information to make a huge profit at the expense of regular trade. So, for example, if you want to buy an Apple stock, your trade doesn't go directly to exchanges. Some entities called high-frequency trading firms sees your transaction first and then they buy all the Apple stocks at the exchange. So you will probably end up buying Apple stocks with higher price than you expected. So, and then this kind of user fund stealing was brought up to media again a few years ago with Robinhood. When Robinhood came into the market, it attracted millions of users with commission-free stock trading. But actually, the Robinhood make a profit by selling your trade to high-frequency trading firms that runs dark pools to front-run your trade. So that's why they can provide some kind of trading fee-free. And then, so actually they manipulate your transactions to make a huge profit. So the key point that I want to emphasize from these examples that if there is anyone who knows trading information in advance and is able to change the order of transaction, is actually has a power to steal another person's money. So MEV is also happening in blockchain space. The set of transactions on the screen shows that the most common type of MEV, which is sandwiching attack. Sandwiching occurs that an attacker places two transactions before and after unopened transactions. We call it a victim to make manipulate price and to take profits. So I brought some statistics on the sandwich attack. More than 1,000 transactions are attacked on daily basis, and then MEV searchers or miners actually can make a huge profit from them. The more important thing is that users pay more. When they trade, users pay more than they would have without being attacked by sandwich attack. Ranges from as little as 2% to at most 87% of your trade. The worst part is that actually people don't realize that this type of MEV attack actually happens. So they actually, it leads to financial losses on your assets. So, but there are certainly a harmful effect of MEV, but there are also alternative perspective of MEV having a positive effect. So there are two kind of different types of MEV been discussed recently. So malicious MEV, such as front running and sandwich attack, are definitely harmful to users. They are just to take money from your pockets. And then benign MEV is harmless to you. It's actually an essential part of in DeFi space. So we are not trying to prevent all kinds of MEV. We just prevent the bad ones and maximize good ones. So yeah, a benign MEV such as the arbitrage or liquidation is the essential part in DeFi space. Bad MEV, the malicious MEV, we see that as biggest threat on Ethereum, and especially layer 2 protocol as well, because layer 2 has the only single sequencer to make a block, so they has more power to censor or reorder transactions when they make a block. And we refer to hidden slippage, that you pay more when you are MEV attacked. So, and then as you can see on the graph, MEV extraction is growing at a significant scale. So you need to be aware of that. And also, users pay a really high transaction gas fee because of MEV. MEV such as compete each other with a high gas fee to take a good position to front run or take profit. So the users usually use a gas estimator. Estimator use this PGA inflated the gas thing. So you usually end up with paying a really high gas fee when they compete each other. So that's the result of, that's from the bad MEV. And then the worst part is that it actually affects consensus as well. If MEV, if miners or sequencers capture some kind of opportunity to make a huge profit of MEV, they might reorg transactions history to take the profit. So it leads to it encourages consensus instability. So that's why we see that the bad MEV is kind of a threat on Ethereum. Someone say that it's like a predator in dark forests. So our team's approach is that we want to bring a true information symmetry to create a fair trading environment. So like in traditional financial system, we had to accept what was given. Trading systems aims for efficiency, and so that's why we give all the authority to centralized institutions for the efficiency of our trade. But ironically, we are forced to pay some kind of tax due to the exploitation on our trade, high frequency trading that I just mentioned before. So in blockchain space, we have the choice to what's right. So that's why we want to build some kind of fair trading environment to bring a true information symmetry. So I will explain our approach to make. So as I said before, MEV is all about the ordering of transactions. MEV happens because your transactions is open to anyone. So the naive way to prevent MEV is that just encrypt your transactions to hide it from MEV attackers. But if transactions are hidden, the problem is that the transaction is hidden, the global state also unknown. So it's really difficult to make transaction with unknown state. So that's why people say that it's kind of difficult to make private Uniswap. So that's why we came up with a delay encryption, in which encrypted transactions are automatically decrypted after a specified amount of time. And before this time ends up, sequencers or miners have to confirm the transaction order without seeing the contents of the transactions. So that's how we build a fair ordering also. And then To build a delay, we adopted a time lock puzzle. Time lock puzzle is just a specified number of sequential computation. So, and then the solution to this time lock puzzle will be used as an encryption symmetric key to encrypt transactions. But encrypting transactions leads to another problem, especially on the sequencer side. For example, malicious users submit encrypted transactions with invalid key with invalid transactions. The sequencers can't distinguish if it's invalid or not because it's encrypted. So that's why we need some kind of verification to prove that this encryption process is done correctly. So that's why we came up with some kind of validity proof with the ZK, the zero knowledge proof. So if with this ZK-based proof, sequencers verifies this proof, and then if verification is true, then try to solve time lock puzzle to get the decryption key. Without this ZK-based validity proof, sequencers might waste their computing resources to solve invalid time lock puzzle. So. Okay, the boxes are checked for preventing the user funding stealing and prevention of DDoS attack on sequencer side. But generating this GK-based validity proof should be done on user's side with limited computing resources. So we need to make more practical. So that's why we come up with some kind of the tricks. And first, to delay. As I said before, the time lock puzzle is based on sequential computation. Actually, it's RSA, the hidden order group. So, but a user is the one who generates this time lock puzzle, which means they know what the hidden order is. So they use it as some kind of trapdoor to solve time lock puzzle really fast. So we said it's practical on the user side. And then as for validity proof, it turns out that it's really, it's almost impossible to turn those time lock puzzle and encryption into ZK snark. So that's why we combine the ZK snark and Sigma protocol to make the generating validity proof process to be done on general MacBook in 5 seconds. So that's the result of the approach. So that's how we came up with the PVDE, practical verifiable delay encryption. The most important part is that on step 3, when a user submits transactions with validity proof, a sequencer verifies this validity proof, and then if this verification is true, a sequencer responds to users with order commitment. It's some kind of a promise that your transaction will be included in a specified order in a block. And then users can make a claim when they find out that sequencers break the promise. So that's how it works. So let's deep dive into PVDE scheme. As I said before, we developed this scheme when we are doing a grant program of Ethereum. So thanks to OneSup and Barry Whitehead from Ethereum Foundation, we measured the proving time to generate this validity proof, especially a time lock puzzle in ZK socket. So, and then we run it on the general MacBook, so you can see the specs on the screen. There are 4 approaches to make the time puzzle into the GKP to generate the validity proof. The simple way is that just to put the time puzzle function in GK Snark's circuit. You can see that RSA, we are using the RSA-based the hidden order group. So to achieve 182-bit security, we need to set up generator G as a 2048 bits. And then if we want to make a 10 seconds delay, we need to set the specified number of steps, which is 2 to T, is 8 million bits, which is ridiculously large. So we can't make it to be integrated inside the circuit. So actually we failed to get some result. So we thought that okay, let's reduce the number of steps to make the timer puzzle. So that's why we come up with the trapdoor. As I said before, the users know the trapdoor, which is the order of RSA group that is used to make the timer puzzle. As the users know the hidden order group, a hidden order, so we could reduce the steps for timer puzzle, but it turns out that what matters is not the steps of timer puzzle. Actually, it was the size of a variable for the steps to be stored in the circuit. So actually, it also failed. And then another one is actually we are getting the number for proving time. We tried to reduce the size of the variables for the steps to be stored in the circuit. So actually we run trusted setup. So we generate the parameter 2 to T, and then we used the number of steps as 128 bits as a secret value. So as easily can see that G to 2 to T to S is the same as G to S to 2 to T, which will be used as an encryption key. So, but as you can see in D, we still need to calculate the 2048 bit scaling 128 bits twice inside the circuit, which is why we've got the 540 seconds to generate proof. So it's you can see that it's not practical, especially on user's side. No one wants to wait for that amount of time to make a single Uniswap transaction. So that's why finally we actually managed successfully to generate this GK-based the validity proof within 5 seconds. As I said, it's difficult to just use only the GK Snarks. So we used not only Snark and also Sigma protocol. So finally make it, we think is practical. So we will tell you the details of the scheme after we are done with writing a thesis, and then also the previous experiment, the result as well. So okay, so another thing that I want to point out that is PVD scheme is actually agnostic, which means that we make separate the transaction ordering and transaction execution. So you can deploy PVD-based some kind of dApps on anything. So when we did our grants program, we actually built PBD-based DEX on Optimism. This is the architecture that we did at that time. So you can see that there's a transaction order management based on MMR and the order contract management as well. So, and then also a few months ago, we participated in a hackathon called the Hack Money 2022. At that time, we also built, we modified the Uniswap and deployed this MEV resistant DEX without any hidden slippage on Polygon. So at the time also we had a great result as well. And then lastly, we published technical articles on Ethereum Foundation Forum. So you can check out that. This is the ultimate goal of our project, which is the MEV resistant ZK rollup with PVDE. MEV is happening not only in DeFi space, but also actually in happening NFT and bridges as well. A few months ago, actually, the Bored Ape NFT is attacked by MEV as well. So that's why we want to build some kind of ZK rollup. I mean, the ecosystem, not just only one specific type of the dApp. Okay, so this is the end of my talk. If you are interested in MEV resistant or PVDE and or the ZK rollup, please leave a comment on the articles on Ethereum Foundation, or just contact me, our team at the Radius. We believe that some people say MEV is inevitable, but we believe that MEV is not inevitable if we choose to prevent it. Yeah, thank you.
Hello. Hey, everyone. Thanks for joining. My talk is about building X-chain, cross-chain applications with Connext. Oh, sorry. Okay, so just as an intro, my name is Rahul. I'm the co-founder and CTO of Connext. I've been in the space since about 2017. We started Connext in 2017, so we've been around for a long time. Been doing a lot of different things in this space, like state channels, fiat on-ramps, DAOs, and now we've actually moved into interoperability, which we think is a really cool space. So just to give some background, this is how the old world, you know, like back in the day in 2016, 2017, et cetera, used to look. You had ETH, you had Bitcoin, you have these very like kind of distinct and separate ecosystems where there was no real way to link between them. Like if you have funds on Ethereum and you want to get to Bitcoin, really the only thing you could do pretty much is go through a centralized exchange. And now what we're seeing come together is a multi-chain world. So you have these distinct clusters of different chains that are popping up all over, and they have these very distinct ecosystems between them. So you have ETH plus the rollups, they're sort of forming this own little cluster. And then you have Cosmos, which has its own little cluster as well. And you also have Polkadot, and now you have even things like Polygon is launching like these things called supernets. Avalanche has subnets. BNB has these app-specific chains. So you're really kind of starting to see multi-chain as in a multi-cluster ecosystem. And with that, we get to what bridging means in this new multi-chain world. So the first type of bridging is intra-cluster bridging. So that means you have like these little connections within these little clusters. And some of these ecosystems have done this really well. Like for example, Cosmos has built IBC. So from the get-go, they wanted this thing called intra-cluster communication. So they built inter-blockchain communication as the IBC protocol. Also, Polkadot has XCM. So these, in between these little clusters, you have this communication that's a very powerful communication tool. Polygon, Avalanche, all these other cluster-based ecosystems are all building bridges in between like this. But then you get to this harder problem where you have like this problem of how do you get from rollup on Ethereum to this chain on Cosmos, then to Polkadot, then back to some other rollup. So that's where you have like kind of like a harder problem that is not solved by these intra-cluster bridges. Now, like what exactly is a bridge? So let's back up and figure that out. So a bridge is you have Alice who's on origin chain A wants to send a message to a destination chain. So she will say something on an origin chain, then something happens, some kind of magic process, then you get something to happen on a destination chain. And then this can be like sending tokens, this can be sending messages, this could be like sending data, this could be a smart contract call. It doesn't matter what it is, but something has to happen. So let's dive in and figure out what is this magic. So there's a few different ways that you can bridge, and I'll try to talk about some of the main ways that we've thought about bridging so far. So natively verified bridges, that means a chain's own validators verify the TXs. So this, if we go back to this, sorry here, I'm going to back up a little bit, but this intra-cluster bridging is built using natively verified bridges. So in practice, a natively verified bridge means that a chain's nodes are running light clients of all the other chains within this cluster. Like if you go to rollup bridges, all the Ethereum nodes are actually verifying the transactions that are going on in rollups. If you go to Cosmos IBC, every Cosmos node that has an IBC connection to another Cosmos node is running a light client validator of that other chain. So this is probably the most secure and best way to bridge. But the problem is it's not generalizable. Like you can't have Ethereum validators validating transactions on Cosmos. That's just never going to happen. So the problem with this, the trade-off that you get with this type of bridge is that it's not generalizable. If you want to solve that trade-off, you can do this other kind of type of bridge, which is called an externally verified bridge. This means you have a third party of validators. So you have this set of validators that uses proof of stake, multi-sigs, other things like that to validate a transaction from one chain to another chain. And this solves the generalizability problem, but now you get into an issue where this is not trust minimized. You have to actually trust the validators of this bridge. And then you have another way you can do it, which is a locally verified system. So this means you have an off-chain counterparty that verifies from one to the other. So if you want to bridge from, let's say, chain A to chain B, you will run some kind of off-chain client that verifies that the transaction was done on chain A and can be done on chain B. So an example of this is like an atomic lock or a hash lock-based bridge. So these have been pretty popular in the past. They're really good for like just transferring funds, but the trade-off here is that they're not extensible. So basically the bottom line is each of these kinds of bridges comes with their own different sets of trade-offs. That brings us to this thing called the interoperability trilemma. As you know, we're all in the blockchain space, so we love trilemmas. So this is the trilemma that comes with interoperability. You have on one side, you have extensibility, which means I want to be able to compose my bridge with other smart contracts, essentially make it like a DeFi building block. You have generalizability, which means I want to be able to paste this bridge and connect to every single chain in the world. And then you have trust minimization, which obviously you want to be able to not have to trust some set of parties that doesn't have your best interests at heart. So you can see the different kinds of bridges that we've outlined before. You have the MPC Oracle Validator Bridge. On one side, you have the Atomic Lock-based bridge, which is the locally verified system on the other side. And then you have Light Client Relays, which is the natively verified system. So all of these different bridges, unfortunately, have trade-offs. So how do we solve this trilemma? Well, there's a new kind of bridge design that has kind of become popular fairly recently, and Connext has kind of like written a lot about this, so I'd really encourage you guys to look into some of the writing that we've done about this. So this is an optimistically verified bridge. So this system is slightly different because you have a message that's going from chain A to chain B, and then this is not like an instant system. So before the message on chain B is determined valid, you have a set of actors in the middle one of n that can prove fraud. So they're not in charge of like holding funds or like, you know, they don't have any control over funds. What they can do is they can basically pause the bridge if anything goes wrong. And then this brings its own trade-off where it's not instant. So now we go from a trilemma to a quadrilemma, which, you know, that's annoying because, you know, you're just adding a new trade-off here. But there is a solution for this as well. So this is kind of like the holy grail type solution. So you have an optimistically verified bridge, but in the middle you have this little pink thing, which is a liquidity provider. So the liquidity provider can come in during the fraud period and basically like front run the fraud period to actually send the funds to the user on behalf of this optimistically verified bridge. And so essentially the liquidity provider takes the lockup period, but the user does not have to experience any type of lockup. So with fast liquidity and optimistic bridging, we can basically solve this quadrilemma. Okay, so this brings us to like hacks. You know, bridge hacks are kind of like the flavor of the month or the flavor of the past few months. Everyone is aware that bridges have been getting hacked left and right. I think what this shows mainly about our space is that bridges are a huge weak link in the system. They're pretty new technology, so they're like a huge honeypot of attacks. You know, what I think is that like this is just new technology that is being experimented with still, and it is a huge basically target, and it's kind of going through a trial by fire process where blockchains themselves have been through this trial by fire process. They're battle tested technology now. Bridges are kind of going through this trial by fire. But with that said, I think this optimistic version gives us a very good way to sort of like mitigate the effects of hacks and security because of this fraud-proof window. So like I said, you know, you're gonna have some time between message A and message B to actually do some kind of checks. So these watchers in this fraud-proof based system are looking for fraud, but they can also look for other things. Like if you say some stablecoin got depegged and you want to immediately like stop the bridge, you can do that with this kind of like fraud period. So the watchers can check for more than just fraud. They can check for suspicious activity and bring us to this thing called a circuit breaker. So basically you can just like stop the bridge and stop the process, and you can basically mitigate the risk of users losing funds, liquidity providers losing funds, and kind of this whole like crazy consequences of these bridges being hacked. Now we're going to get into developing Zaps, which is cross-chain apps. This, you know, going on this whole X motif, connects, we have developed this new interface and this new paradigm called XCall. So this is a low-level primitive to facilitate asset and or data transfer across arbitrary chains. It's designed to mimic Solidity's built-in call method. The way we're approaching the developer experience for cross-chain applications is that we want it to be as easy as possible for developers to pick up and learn the process of cross-chain. It's you know, what we've seen when we've gone to hackathons and we've interviewed developers is like a lot of them are interested in the idea of cross-chain, but they find it really hard to wrap their head around what it means to actually develop a cross-chain system. So we're trying to make that as easy as possible by creating this new primitive that matches basically the built-in version of Solidity, so developers don't really have to learn anything new. They can just kind of like augment what they already know in terms of like how to develop decentralized applications. Okay, if we want to look at a little bit of code, I apologize if this is small, but this is basically the XCall primitive in action. So as you can see, what we're trying to show here is that this is a very simple function signature. It has a bunch of params in it, and there's a single call. So all you do is you initialize your connects handler contract, and you call XCall. And the args in here are quite straightforward. So I'll just go through some of them. The two addresses, who is going to receive the funds on the destination side. Call data. This is something that's very important. So what you can do here is you can pass data through. So if you say, I want to call a contract on the destination side, what you would do is you would encode the data. So you can see we're just calling encode with selector, then we're hashing the name of the function. So this is the function signature hash. So this is exactly what gets called in Solidity on the destination side. So we're calling a function called update value. It takes a uint 256 and is calling it with some number we want to update it to. Then you have origin destination domain. So this is just encoding of what the chain you want to go to and from. Agent recovery. So this is kind of just some like fallback parameters. So in case the transaction fails on the receiver side, then you have a way to like get the funds back. Force slow, receive local, these are kind of like not very important parameters that are kind of like advanced configuration parameters. Callback fee, we'll get into this a little bit later. This is also important. And transacting asset ID and amount. So basically what we've done is we made it really easy to send funds across chain and also send data if you want. So transacting asset ID and amount are basically the token that you want to send. So if you're saying you want to send like DD token on Goerli chain to Mumbai chain, which is what the origin destination domain are, this is basically the signature you have here. So what this is going to do is it's going to send this amount of this asset to the destination domain and as well as call this function. So when we get into call data, when I talk about data passing, you have distinctive flavors of data. So it's important to know that there's like two different types of data. When you're passing data, there's a type of data that's called authenticated data. This means the destination target needs to verify the origin, source, domain, and address. So you need to be able to verify on the destination chain that this came from a specific address on the origin chain. For example, if you're voting in a DAO on chain B from chain A, you need to know that the person on chain A actually voted in that DAO. So that's very important to verify that this came from the bridge. So in this case, that needs to come through this fraud-proof window. So you can't bypass the fraud-proof window in this case. However, there's another type of data called unauthenticated data. This means this is like a meta transaction. So the destination target does not need to verify the origin, source, domain, or address. So for example, like, and these use cases are actually more than you might think. So a swap can be done by anyone. It doesn't check message.sender. If I want to deposit into Aave, I can say I want to deposit on behalf of somebody else. So that doesn't check message.sender. If I even want to like check that an EOA on chain A signed a message, I don't need a message.sender. I can just check a signature. So this is these are all examples of things that can actually be done very quickly through a liquidity provider. So the whole key to this is that you don't know who is going to fulfill this transaction on the receiver side. It's not going to be done through a bridge contract. It's going to be done through an external actor who is a liquidity provider. So because the data is not authenticated, this could be done fast, and you can see this little like pink guy there can instantly do this. So if you want to essentially do like a cross-chain swap where you swap USDC for like Ethereum, you can do that by doing this fast path. So it'll send the USDC through the bridge and then it'll swap it immediately through the liquidity provider calling a Uniswap contract or something on the destination side. Then you get into a thing about gas. So how are you going to pay for gas? Like, essentially we want the system to be sustainable, so we don't want to be doing gas subsidies. A lot of other bridges do things like gas subsidies and things like that, but this is not sustainable. We want all the gas fees, everything that everyone who is a relayer in the system or liquidity provider, all their gas should basically be reimbursed by the user. So that's one of the desired properties, is that the user pays for all the gas fees. Another desired property is that the user does not need gas on the destination chain. This is super important because we want this UX to be extremely abstracted. Basically, our end goal at Connext is that you don't even need to think about what chain you're using. Like XApps, dApps should be building cross-chain systems that basically abstract the entire process of chains. So you should say like, I want to deposit from any chain, do something on any other chain, get the funds back on any other chain. And like all that process should be handled by the bridge itself. So the main point is that users don't need to have gas on any of these destination chains. But at the same time, we want to make sure that relayers are properly incentivized to submit these TXs. So we don't, like I said, we don't want any kind of subsidies or things that are not going to be really sustainable long term. So this is kind of a complicated diagram here, but we can walk through pretty easily. So on the origin side, Alice is going to pay for the gas fee on the origin chain in the native asset. So for example, if the origin chain is Polygon, Alice is going to add some extra Polygon, like in addition to what the transaction fee is for this transaction, which is going to basically be locked on the side, on the origin side, as a claimable relayer fee. Then we go through the bridge. The relayer, who is the one who does the fast liquidity stuff on the destination side, will basically complete this transaction, send it to the user on the end user on the destination side. Then once they do that, they will actually submit this proof back through the bridge. So it goes back, and then they are able to claim the relayer funds. So they prove that they sent the transaction on the destination side, and then they're ready to claim the funds on the sender side. This brings us to asynchronity. So when you're doing cross-chain app development, you can't assume synchronity anymore. So what does that mean? So blockchains are synchronous. That means everything happens in one transaction. It's an atomic transaction. So either the entire transaction goes through or it doesn't. So you don't have to like worry about anything. And this gives us basically all the properties of blockchains that we like. Like you can do Uniswap swaps. The reason Uniswap works is because it's synchronous. The reason flash loans work is because it's synchronous. So when you're doing cross-chain stuff, you actually lose that synchronity, and you have to kind of think about how you're programming stuff very differently. But the interesting part is that like we already do asynchronous programming everywhere. So if you're a developer, you're developing in JavaScript, you're developing anything on the internet with distributed systems, you don't have synchronous environments. You have basically, you send a call somewhere, you do some work with the callback, essentially. So you just send your call out, and then it processes something later. So this is a very common pattern in functions like Java, or in languages like JavaScript. For example, you have this .then call. So you do some work, which is an asynchronous process. You have a callback that you attach to this function. So now this .then function gets called sometime in the future. You don't know when, but you have some handler function written that can handle it when that happens. Okay, so now if you want to do this same thing in a cross-chain world, it looks a little different. So you have your origin chain, you do some work on the origin chain, then on the destination chain, you will do some work back on the origin chain once that process actually happens on the destination chain. So basically you're going to like tell something to happen on the destination chain, and then you're going to get the result of that back on the origin chain. And that's basically how a cross-chain callback works. So how does this work in Connext? Like I mentioned before, there was this callback parameter. Let me see if I can go back to this slide. Sorry, I'm going to go back here. I just want to make sure. So we have these parameters called callback and callback fee. So this callback, if you set this, you can set this to address this if you want this address to actually implement the callback. Sorry, I should have included that in the parameters. But there's a very simple way to basically set it so that you're going to get the result of the call that you make on the origin side from the destination side. So for example, we're calling this function called update value. If update value returned a result, basically like a true or false or something, whether or not it was updated, then you would get the result of that on the callback address if you specify something other than address 0. So in theory, you would specify address this. So let's go back here. So then we have our xcall function, which does some stuff, and then we have callback. So all we have to do is specify a function called callback, and then we specify only promise router, which means we're going to verify that this data is only going to come from the bridge. And then we have some handler which in this contrived example, all it does is update the data on one smart contract with the result of the callback value. So this is a very simple interface for implementing asynchronous solidity, essentially. And what are people building? So, I think this kind of unlocks a really cool set of use cases for cross-chain apps, and we're starting to see now that there are more and more things that are being built with cross-chain applications. For example, Superfluid is a company that's building on Connext. They're building cross-chain money streams. We have Keeper, which is building cross-chain Uniswap TWAPs. This is really important. This is going to be like a DeFi building block. So essentially you have a Uniswap TWAP which has liquidity on one chain, but you want this price to be carried to other chains as well. But you can't guarantee you have liquidity on these other chains. You can only guarantee you have liquidity on the chain where you have liquidity. So instead of fragmenting the liquidity and making the whole TWAP more unsafe, you can just move the TWAP price from chain to chain. FujiDAO is another project we're working with. They're doing cross-chain lending aggregators. So like I said, we want to be able to make the cross-chain process kind of completely abstracted from the user. So that means users should be able to get yield from any chain they want without even thinking about what chain they're getting. So FujiDAO is helping make this happen. NFT Hashi is another project we'll be collaborating with. They do multi-chain NFTs. So NFTs are something that should be able to be on any chain without really worrying about which chain they're minted on. So they're making this happen. And DAO governance is a really important thing. So you want to be able to vote from one chain to a DAO on another chain. This is just something that should be there and should exist. So why not? And then this brings us to what we want to see next. So we want to see builders taking this to the next level and really figuring out what the next applications of cross-chain are. So, the world is basically the oyster at this point. There's a lot of things we haven't even thought about here. So cool, thanks for listening, everyone. These are the links here. If you want to get more involved with Connects, please reach out to me. If you have cross-chain app ideas, we'd love to talk about it. And yeah. If anybody has any questions, happy to stick around and answer, or can find me later.